So how did you do that? Well, I mean, I guess I know what that is.
What did you say?
I'm saying what was wrong. Where's the mic that I'm talking through? Is it this one?
Yeah.
Yeah. So what was wrong in the end?
Say again?
In the end, what was wrong?
I don't know.
Yeah. But it worked when you did it, so fine.
Don't worry. I'll be there in 20 minutes.
Okay.
Look at presentations and be sure that you have the ones for the first session. In the meantime.
Sure. I've got the Dropbox open now.
See you later.
Hello. Nice to see you. So you guys are going to be in person?
But I have no idea where it is.
Oh, nice.
I texted.
This also smells like rosemary.
That's this.
Okay. Can the people online hear me? Is the next speaker ready? Oh.
Yeah, sorry. The first one will be in person.
Ah, the first one is person.
And then the next.
Oh, okay.
Next
Okay. Okay. The floor of the two is going to give it the actual total.
Someone was saying something.
Up here.
Yeah.
Perfect. Try that. Try see something.
Well, it's the connection.
Oh yeah, just
Yeah.
clip this onto your pockets.
Sorry about that. I think we're ready to start. So welcome to the third day of ACT. So the next speaker is going to be Raise and Shake with work together with Stefano Gogioso about categorical semantics of Feynman diagrams.
Thanks, Paulo. So as I said, I'm going to talk about categorical semantics of Feynman diagrams. And this was a joint work with Stefano Gogioso during my master's at the University of Oxford. Okay, so I'll start by motivating why we care about this problem. So the best theory we have describing the universe comes from quantum field theory. And Feynman diagrams are an important ingredient of quantum field theory. So if you have particles and those particles which are described by fields interact, that interaction can be depicted pictorially using Feynman diagrams. And then we have Feynman rules that allow us to convert those diagrams to probability amplitudes. However, Feynman diagrams are usually just used as calculation tools, and we don't know how they appear, or I mean, we know, but like we don't have a formal derivation of them arising from the underlying field operators. So what we are going to do in this talk is give this formal description, where we'll start with the field operators describing the interactions, and then by describing it in terms of string diagrams, we'll show that the string diagrams that you get can be represented just like the original Feynman diagrams. And since we are at ACT, we'll also ask, what does it mean to compose these diagrams? So the traditional Feynman diagrams are just graphs, and it doesn't really mean much to compose them because the Feynman rules don't respect this composition. But here, when we'll get a picture with operators instead of just some diagrams and rules, we will be able to compose them because our diagrams will be just linear maps in the category. So we'll see what it means to compose these diagrams and what interesting things appear from that. So there will be three topics I'll cover. First, I'll give the background of quantum fields in terms of category theory and string diagrams. Then we'll start with this operators describing interactions and show how the Feynman diagrams arise from them. And finally, we'll look at composing Feynman diagrams. So before we go to quantum fields, we need to look at the classical fields, and to go to quantum fields from there, we can quantize the classical fields. And one way to view scalar classical fields is to view them as having a simple harmonic oscillator at each point in the momentum space. So just imagine there's this whole space for the universe, and at each point, there is a simple harmonic oscillator. And now if you want to go to the quantum field, we simply need to quantize these harmonic oscillators. So for the quantum field, we will have a quantum harmonic oscillator at each point in the space. Now, if we want to do this quantization, we ideally would like to do this in the category of Hilbert spaces. But the category of Hilbert spaces, also known as Hilb, is not nice. It does not have cups. It does not have caps. It does not have spiders. So if we want to do diagrammatic things with it, it's not very convenient, or it's not very useful. So instead, we'll work in a category called star Hilb, which is the category of hyperfinite dimensional Hilbert spaces. And star F Hilb behaves just like the category of finite dimensional Hilbert spaces, F Hilb, and that means it's dagger compact, which means it has cups, caps, and spiders. And moreover, any result that we prove in star Hilb can be easily transferred back to Hilb using a simple functor. Okay. Now, let's see what a quantum harmonic oscillator would look like. Well, so quantum harmonic oscillator, it's like an infinite series of like energy levels, or you can also interpret them as particles. So, so like just as we would describe qubit by C2, and we'll say this is the qubit, we would similarly say that the quantum harmonic oscillator is this object HK, where K is some hyperfinite dimensional natural number. Now, with these, with the quantum harmonic oscillator, we have a creation and annihilation operator. And this creation operator would take you from the nth energy level to n+1th energy level. So in the QFT language, it would mean like it's creating a particle. Similarly, we have the annihilation operator, and it does the opposite. It brings you from nth to n-1 state. Okay, now, as I said already, that quantum field, scalar quantum field, can be viewed as quantum harmonic oscillator at each point. So all we need to do is simply take a tensor product of all of them. And when we take this tensor product at each point in momentum space for the quantum harmonic oscillator, we get another object, and that object, we'll call that the quantum field. And we can recover the usual Fock bases, the number states, by simply taking particle number at each point and tensoring them up for all of the momentum space. Now, for Feynman diagrams, we will need two ingredients. One is the creation annihilation operator for the field, and the Feynman propagator. So, okay, let's look at the creation annihilation operators first. Now, for the field, since we have quantum harmonic oscillator at each point, if you want to create a particle, you need to specify where I want to create it. That means these operators take P, the point in momentum space, as a parameter. So when I specify P, I can create a particle at point P, and it takes you from beta n to beta n plus delta P, which means it's just creating a particle at P. Similarly, we have the annihilation operator, which does the opposite. So it destroys a particle at point P. Now, these operators are, so if you were to draw these diagrams as diagrams, we'll have a box with this operator, and we'll have a parameter P inside the box. So instead of having one process that does the creation or annihilation operator, we'll have a family of boxes. And it would be really convenient for us if we could package them in just one operator. That's why we will define the coherent versions, coherently controlled versions of the field operators. This means that here we will, so here the top wire corresponds to the quantum field, and the second wire below it corresponds to the control. So you can imagine that when you give some value to the control, it will result in the original operator at that point. So this is the coherently controlled creation operator, and this is the coherently controlled annihilation operator. And when you plug in the momentum basis state, so here I'm plugging in P, I will get the respective original momentum operator, original field operator at that point. But the interesting thing we can do here is that instead of plugging in the momentum eigenstate, what if I plug in the position eigenstate? Because since they are coherently controlled, all of this makes sense. And when we do that, we actually get the Fourier transform of the momentum operators, and they simply correspond to the position operators. So we get this very nice unified view where you just have this one box with two wires, and one of them is acting on the quantum field, and the other is a control wire. And by plugging in position eigenstate or momentum eigenstate, you can get position field operators or the momentum field operators. Okay, so that's one ingredient that we'll need in our Feynman diagrams. The second ingredient that we will need is the Feynman propagator. A Feynman propagator is a quantity, it's a number, it's describing the probability of particle traveling from a space-time point X to space-time point Y. So if I say there's a particle at X, what is the probability of it being at point Y? And these are space-time points, so like it's traveling from point X at time 0 to Y at time t. And this quantity, well, it's a scalar quantity. So the top wire here, which again corresponds to the quantum field, it will do nothing to that. So it's an identity on that. And we'll simply take in the parameters of the controls and calculate this number, which is the probability of particle going from X to Y. And for Feynman propagator, probability of going, for Feynman propagator, going from X to Y or Y to X is the same because that quantity is we make sure that they correspond to the same thing. That's why we choose this diamond shape, which embodies that property diagrammatically. All right, so now we have the necessary ingredients that we need for our Feynman diagrams. So now we'll look at how we can use those to get categorical Feynman diagrams. So for this, we'll take an example of a very simple theory called the scalar Yukawa theory. Scalar Yukawa theory is actually a simplified version of Yukawa theory, which describes strong force between nucleons. So nucleons are particles that you find in the nucleus, like protons and neutrons, and there is strong force between them, and the theory describes that force. But this is just an example to set up what should probably work in any other theory for any other scalar theory. So in this theory, we'll have three particles. One is nucleons, and we'll represent that as n plus. And for Feynman diagrams, it will be an arrow pointing to the right. The other particles are antinucleons, and we'll represent them symbolically as n minus. And in diagrams, there would be an arrow pointing to the left. And we'll have mesons, which will represent by this dashed line. Okay, so let's look at a very simple example of a Feynman diagram. In this Feynman diagram, we have two nucleons, and you read this from left to right. So there are two nucleons coming in from the left, which you can see by the two input arrows pointing to the right. And then they interact in the middle by a virtual meson. And that can be seen through the dashed line in the middle. And then they scatter away. So you can imagine that there are two nucleons, they come in, they interact, and then they scatter away. Now, this Feynman diagram actually corresponds to this term in the, if you look at the Fick's expansion, which describes the interaction terms. Now, this looks very complicated, but let me simplify it. Let me explain it. So there are the first two terms, n plus dagger x1 and n plus dagger x2. These correspond to the creation operator at point x1 and x2. And then we have next two terms, n plus x, n plus x1 and n plus x2. These are annihilating two nucleons at point x1 and x2. And then we have the terms with m in it with a bar on top. And this bar represents a propagator for mesons going from x1 to x2. And what we want to do is take this term and write it as a string diagram. So I take all these operators and put my ingredients that I've already shown before and write them as a string diagram. So this is what we get. So we have the coherently controlled version of the creation and annihilation operators. I'm plugging in my input eigenstates for points x1, x2, and so on. And at the end, we have at the last split, we have the propagator, which is identity on the field, but takes in the parameter space and gives a scalar. So this is cool, but this does not have any of the intuitive beauty of Feynman diagrams. It's just like a linear thing with like a series of operator acting on the same wire. And that's because like we only have one wire for quantum field. So to get this nice representation, which corresponds to the same linear map, but also has this nice intuitive understanding of the Feynman diagram, what we need to do is we need to somehow make this diagram two-dimensional. And to do that, we will introduce split and merge maps. So a split map takes in the quantum field and creates k copies of that. So it creates some number of copies of that original quantum field. But when we do that, we need to be careful. We need to be careful that the number of particles that were there in the original field matches the sum of all particles in rest of the wires. So when we take this copy, we don't want to create extra particles. We want to conserve the number. So, but how do we decide which particle goes in which wire? Well, we take a superposition of all of them. And that's what this split, that's what the split map does. And you can imagine that the merge map does the opposite. So if you have some wires in some particles in different wires, it will simply merge them into one quantum field and put those wires in the same wire. So now we will be able to like create multiple copies of the wire and then also merge them back. Now for Feynman diagrams, we will need three properties of split and merge maps. So the first is, if you split, do nothing, and merge it back, that's as if you never did anything in the first place. So splitting and then merging is the identity. The second rule is, if you have a split map and then you have annihilation operators, you can simply slide the annihilation operator to any wire on the split map. Similarly, if you have the creation operator on the right, you can simply slide it to any wire on the merge side. So using these ingredients, we'll go back to our problem. So we got stuck here because our diagram was just a linear string diagrams with nothing interesting. And now to make it 2D, we will introduce this pair of split and merge maps here because they correspond to identity, so I can put it anywhere. And now, from this diagram, what I want to do is I want to slide those annihilation operators from the left-hand side, creation operators from the right-hand side. And when I do that, I get a diagram that looks like this. So this is already better because now we can kind of start seeing the pieces of how things are, how things might correspond to in the Feynman diagram. But this still doesn't connect the whole picture. You can see that there are parameters floating around, there are propagators, and it still doesn't have the exact correspondence to Feynman diagrams. But now we'll notice that for the parameters, let's say x1 and x2, we're actually summing over all of x1, and we're also summing over all of x2. And when you sum over all of the position eigenstates, that corresponds to the Z spider, the green spider from the generalization of ZX selfless. So we take all the places where we have x1, and because since we are summing over x1, I can replace that with a spider. Similarly, I can replace the x2 with another spider. So we get this diagram, and now sum is already part of the diagram itself. So it's not floating externally. And we know that the spiders in ZX merge, and we can pull the wires. So we end up with this diagram. This diagram looks like the original Feynman diagram we started with. So just to spell it out, we have two nucleons coming in the original Feynman diagram, and they correspond to the annihilation operators for the nucleons. We have two nucleons going out. They correspond to the creation operator for the nucleons. And we have the meson, virtual meson in the middle. And that virtual meson here is represented by the propagator. And all the vertices in the original Feynman diagram become the Z spider, the green spider. Okay, so this was good. Now, can we do this for more complicated examples? So here's the Feynman diagram with loops, and loops are usually tricky to deal with, but we'll see that if you follow the same procedure, it's actually not difficult. It's actually the same thing. So we start with this Feynman diagram. We look at the corresponding the operators, which include the creation and annihilation operators and the propagators. And we do the same thing again. We write all of them as this linear string diagram. And now from the string diagram, to make things 2D, we can introduce the split and merge pair in the middle because they correspond to identity. And the same story again, we slide the annihilation and creation operators. And when we do that, we get a diagram like this. And we replace the position eigenstates for each x1, x2, x3, x4, because we are summing over them with spiders. And finally, we take this diagram, we merge the spiders and pull the wires. And we get this diagram, which again looks like the Feynman diagram we started with. Okay, so I have more examples here. So these are the two you have already seen, and there are a few more here. So the first example here is when a nucleon and an antinucleon scatters. So you can see that there is a nucleon on top, an antinucleon on bottom, and then they are interacting again via a virtual meson. So an antinucleon and a nucleon come and they fuse and become a meson, and then that meson splits at a later point. So that's the first one, and you can see that the Feynman diagram on the left and right, all of these correspond to each other. The second example is for the meson decay, where meson splits into nucleon-antinucleon pair. And the last one is for the case where two mesons scatter. Cool, okay. So we can represent Feynman diagrams via the operators. But one of the main use of Feynman diagrams is to calculate amplitudes. And the question is, does this thing that we did here, can we calculate amplitudes from that? And the answer is yes. All we need to do is to plug in the initial states and the final states. So let's say initially I had two nucleons at point P1 and P2. I can plug that in on the left here as the input. And let's say for the output, we have two nucleons again with momentum P1 prime and P2 prime. And I can put that as the effect. And when I sandwich these, this Feynman diagram with initial and final states, I get like a closed diagram. And this closed diagram corresponds to some number. And we can use rewrite rules and calculation to show that this number, so I won't show you all the steps, but you can see that it works out. And the number that you get in the end corresponds exactly to the traditional Feynman diagrams. So here you see the term in the middle. That's the term you will get if you apply Feynman rules to the bottom Feynman diagram. And turns out that's the same number you get from the top. So yeah, amplitudes work. So we are not taking away anything from what we originally had. But what is the new thing that we are gaining? So one thing is that we are now representing the Feynman diagram as a process in the category. So as a transformation, as a linear map, instead of just something that corresponds to amplitudes. And we know that processes compose. We can, if you have two morphisms, you can put them together to get a new morphism, as long as everything type checks. So we can compose Feynman diagrams. And so let's try to do that. So we'll start with this nucleon scattering examples, because I believe you are already familiar with that. And we want to compose the categorical versions of the same two nucleon scattering diagrams. So we'll write the categorical versions of that diagram here. And then and now we want to make things linear. And when we write that in the linear way, this is the diagram we get. And for something to be a Feynman diagram, it needs to have all the annihilation operators on the left, all the creation operators on the right. This is something called a normal order. This is something called the normal order. And once the terms are in normal order, they should correspond to Feynman diagrams. But we can see that here the terms are not in normal order. And to make them in normal order, we would need to commute these operators. And to commute these operators, we need to use the commutation rule. And this commutation rule says, if I commute the creation and annihilation operators, I get an extra term in the sum, which is identity on the original quantum field. So it doesn't change the particle numbers, but it gives you the propagator on the parameter space, on the parameter wire. So we apply this commutation rule to our linear version of the Feynman diagram, and we get these two terms. And we see that we still haven't moved all the annihilation to the right and creation to the annihilation to the left and creation to the right. So we apply it again and again. And when we repeatedly apply that, we end up with a sum of diagrams. So at the bottom, you can see there are many terms of the categorical Feynman diagrams, and I've drawn what they correspond. I've drawn the corresponding traditional Feynman diagrams. And when we're composing these two nucleon scattering diagrams, this is all the terms we get. And you can see that this actually corresponds to all the possible ways of graph theoretically combining the two Feynman diagrams. So the first term here looks like as if you just put the Feynman diagrams in parallel and did not join any edges. The second one is when you join one edge of the first with the other and merge them, join the legs. And you can see that these are all the possible ways you can join the outputs of the first with the inputs of the second. So we have we come up with a very compelling description of sequential composition of diagrams. So Feynman diagrams represented as linear maps actually when you compose them, actually corresponds to the superposition of all graph theoretic combinations of the Feynman diagrams. So I find that very compelling and interesting, and something we couldn't do, or something that wouldn't make sense with the original diagrams. And the reason it wouldn't make sense is that when you compose and apply Feynman rules, you just get different results. So anyway, so let me conclude and go over what we have done so far. So we started with a Feynman diagram representing amplitude. We came up with a categorical version of that, represented as a string diagram, which represents the process of interaction instead of just the amplitudes. But we can calculate the amplitudes back by simply plugging in the initial state as the state and final state as the effect. Now, I think this is like this is a shift in perspective. So the perspective of original Feynman diagrams is this syntactic graph theoretic things, and we have surpassed that to go to this notion of compositionality, which is semantic and categorical diagrammatic. So I think this is a very important shift in perspective, and something that has allowed us to meaningfully answer the question of what composition means in terms of diagrams for interacting processes in the quantum field. So there are two things I would like to do next. So first is that these diagrams that we get that correspond to the categorical diagrams, categorical Feynman diagrams, well, they look like, so these are string diagrams. And I think we can use these diagrams to do quantum simulation of particle physics, because I can simply take these abstract circuit-like things and say, and somehow define a functor to quantum circuits. And so this this thing could be an intermediate step in taking the interacting processes and going to quantum circuits by simply taking the Feynman diagram, writing the categorical version of it, which is very straightforward without going through all the process of deriving it. So write the categorical version of it and then send that, which is made from the operators, to quantum circuits. And I think this could be a very useful application. And so today I only talked about scalar fields. We would like to extend it to fermions, in which the particles don't stack, but instead it can only be particle can only be there or not there at a position. So bosons, the scalar bosons that we looked at today, correspond to things like photons or light. Fermions correspond to the matter particle. And so we'd like to extend to that. And finally, also like to extend to the vector bosons. So we only consider the simplified scalar bosons today, and it would be great to extend to vector bosons. And I don't think this is a complicated step. You just need to take care of some bureaucracy that arises. Yeah, that's it for me. Thanks for listening.
Okay, we have time for questions. So, okay, let's first do the in-person ones. Let's say,
Good. Right. Okay, thank you for the talk. So, so there's sort of a history of Feynman diagrams, say in Chern-Simons theory. I mean, so Feynman diagrams in that field, right? So that's the thing I know about. I don't know the sort of general Feynman diagram picture, but in Chern-Simons theory, I mean, the Feynman diagrams are typically interpreted as just being morphisms in the representation category. I mean, are you familiar with that picture?
I am not familiar with Simon's theory.
Yeah, so there, I mean, you're just working in, so in Chern-Simons theory, you have some gauge group or something, and the Feynman diagrams are usually interpreted as just being morphisms in the representation category. So is it not the case that, sort of extrapolating, that in more general theories, these Feynman diagrams are just sort of tensors in the representation category of the gauge group? So,
I'm not sure.
right, okay.
Yeah.
Yeah, well, I can tell you about the Chern-Simons theory.
Yeah, maybe we can talk about this in the break.
Right. Thanks. Right. Next we have Felice.
Hello, very nice work.
Thank
Very
you.
amazing. Finally, I know what a Feynman diagram is. I have a slightly technical maybe question. When you showed the sliding rules for creation and annihilation operators, are they like can you basically slide whatever across slide and merge, or you have some like bureaucracy of some sort, like so you can, like if instead of A, I have A dagger in the first rule, does it work anyway? So they're completely symmetric?
No, it doesn't. It doesn't work. You can only slide annihilation from split. And the reason is that when we do the split, we are distributing the number of particles in all these different copies. And if we annihilate a particle first and then do the split, it's the same. But if we create a new particle, we get like extra terms. So it doesn't correspond to the exact same
so you
thing.
scramble the superposition basically.
Exactly.
Because it's not a real copy, it's a superposition of things. Okay.
Yeah, it's a superposition of things.
The second question is there some sort of Feynman diagram that you think it will be very difficult to do? Like, is there something that feels like inherently pathological for this approach, or that will take huge work? Or
so I think there will be a So I've looked at fermions, and I think when you go to more difficult Feynman diagrams, the things that you need to do are find the string diagrammatic version of the creation and annihilation operators. So that's the difficult part. The second thing that you need to characterize is the interactions of them with the split map and split and merge maps. And it turns out that when you have different operators that do slightly different things, like for fermions, if you commute the particles, you get a minus sign, for instance. So these maps need to take care of that. So there is a little bit more bureaucracy, and the diagrams might get slightly more complicated. But I don't think there's any pathological reason that would stop us from
okay, so
doing that.
Gallagher really depend on the particles you are defining.
Yes.
Okay, thanks.
So so they are creating particles of some type.
Okay,
so
cool. Yeah, thanks.
Yeah, really cool. So can you say, can you go to example one or one of the picture or the gallery?
Oh, okay.
Sorry. A picture that has your version and the okay. So in that, okay, so in all these, the like on the left, the way Feynman drew it, he imagined things coming from different parts of. He imagined that things are coming from different parts of space and then leaving in different parts of space. But for you, there's like this splitting and merging. Can you say something about like intuitions that people have about space that are like, you now have different intuitions about how space works because of that difference? Yeah.
So when we have the diagrams on the left, so there we are saying that, okay, there we have two particles and then they are coming in and going out. But the diagram on the right it does not have any particles. It's just representing a process. So if you plug in particles at different points, it will do this interaction between those particles. So there are actually no particles in this picture until you plug in the state on the left side. So, and the reason why it doesn't matter where this is because you're integrating over all possible points in the space, which are the spiders. So if you plug in the initial state, which will have the information about where the particle is, it will do the corresponding thing to that. Does that answer the question?
So location is really not what's going on somehow physically.
Yeah.
It's not that important. I don't know.
So physically, this just represents the interaction, and to specify the location, you need to tell it where the particles are. And when you do that, you need to plug in the state. And when you do that, it just says, okay, there is this quantum field, which has only two particles, and for these two particles, it will do this interaction. Now, what if it has more than two particles? Let's say it has like 20 particles. And when we have more particles, you can see the split map will give you superposition of all possible splittings, which means, so this means that when you have more particles, you will have superposition of this interaction happening to all different combinations of those particles. So this is simply representing the interaction. If you have more particle, this will give you the sum of interaction happening here to these particles, interaction here to these particles, and all of that in this diagram. But if you only care about some specific ones, you can give it initial and final state, and it can pick out those specific ones. So it's strictly more general than the diagrams on the left. Yeah.
So what is the physical interpretation of your composition order? Because it's very suspicious to me because you're taking two processes and you're somehow producing a sum of, if you go to your expansion of the different diagrams that you get at the end, that one there, you can see that you're trying to add processes which take 3 particles in and 3 particles out with processes that take 2 particles in and 2 particles out. So this feels like this doesn't this makes me very suspicious of the composition being meaningful. And I'd make a counter argument to a claim that you can't compose Feynman diagrams meaningfully. I'd say the interpretation there would be that if you compose Feynman diagrams, you're saying that this is the transition amplitude conditioned on at some point having this set of particles with this set of momentums between your input and output states. So what's the composition in your case?
So first, what I mean by composition not working is that if you had two Feynman diagrams, and if you were to apply Feynman rules to them individually, and so that means you'll get two different amplitudes. And if you want to put them together, you'll get some, let's say you get some amplitude for the composition. Now, if you compose them first and then apply the rules that, to the second diagram, the thing that you get does not match the thing initially. So Feynman rules before composition, and so apply Feynman rules before composition and then combine the amplitude is not the same as combining the diagrams and then applying Feynman rules to get the amplitude. So that's what I meant when I said they're not very compatible with Feynman rules. But yeah, I mean, of course you can like join diagrams and draw new graphs, but I believe for it to be meaningful, it should also respect the Feynman rules. So that's one thing. The second, why are there different inputs? Well, as I said, the Feynman diagram doesn't have any information about the number of particles. All it's saying is that, let's say there is this interaction of this type, and there's this other interaction of this type. So let's say this interaction happens to some particles in the space. And then after that, this different interaction happens to particles in the space after the first one. And it doesn't say that it has to happen to the same particles. So let's say there were three particles, two of them interact via one interaction, and then one of them goes away far in the space. There's one particle that interacts with the third particle with the same type of interaction described by the diagram. So when you have that, that would be like the second diagram here. That will look like the second diagram here. So we don't look at the particles, we look at the processes and interactions. So we just say, let's say this interaction is happening somewhere. And what happens if you have another interaction that happens after that, also somewhere in the field? Because you can't localize, all you can say is that if there are initial, so if you want to pick out the terms here, and you say, okay, there are only three particles in the quantum field. In that case, you won't get a different number of diagrams with different inputs. It will simply pick out all the diagrams that have 3 input legs and 3 output legs. So if you plug in the correct input states with the information about the number of particles, the amplitudes that you get for the ones with different numbers would become 0. Does that answer your question?
No, my question is more about a physical interpretation. It sounds like you're saying if I have 2 processes, how could they act on a state? Whereas when I'm thinking about Feynman diagrams, I'm thinking about that you want a sum of different Feynman diagrams to do the tree version, the first loop correction, second loop correction. And if you sum up all these, then you get the true amplitude transition from input to output.
Right. So
like,
yeah. So
that was what I was originally imagining.
Right, I see.
Somehow correcting for, but that's not what you've done here. It's,
no, I wouldn't say so. Yeah.
Kind of need to, yeah.
So I mean,
I'm sorry. I think we should move this discussion to
this might be better to speak that up
because yeah, we're out of time. So there are more questions. I suggest the people that have questions in person to move those to the coffee break as well, and the people online to write them in the chat. And if you can please connect to Zoom and answer those questions from the audience online, that would be nice. Okay. All right. So for now, let's take a okay, are the next speakers there?
Yeah.
All right, perfect. Is it Younesse? Are you going to give the talk?
Yes.
Right. Okay, great. So the next speaker is Lemay, and he's going to talk about
Wait, I need
differential categories.
Someone has to allow me to share my screen.
Oh, should be good now. Should be good now. All right, try now.
Thank you. Yep.
Okay. All right. Please take it away.
So I can start?
Yes.
All right. So hi, everyone. Thanks for letting me speak. So today I'll be talking about monoidal reverse differential categories. And so first off, this is joint work with these people, Geoff Cruttwell, Jonathan Gallagher, Dorette, Pronk, and myself. And this talk is on our paper, also called Monoidal Reverse Differential Categories, which is on the archive. So what's the motivation behind this talk? Well, essentially in programming, there are two types of derivative operations. There's the forward derivative and the reverse derivative. Now, the forward derivative is the one that most of you probably know about. It's the one that we use in classical math, like in differential calculus, differential geometry. And it's also used all over the place in computer science, and in particular, differential linear logic and the differential lambda calculus. Now, the category theory story about forward differentiation is captured by what's called the theory of differential categories. And the theory of differential categories is on the upswing. It's sort of gained in popularity recently, and there's lots of research done on it, and there's lots of papers. On the other hand, there's the reverse derivative, which is more practical and used in fields like automatic differentiation, machine learning, and differential programming. Now, the categorical side of the story of reverse differentiation is captured by what's called, reverse differential categories. And these were first introduced in a paper by myself and my co-authors in CSL 2020. And really, the story of reverse differential categories is really just getting started. And what I've been super impressed about is the fact that reverse differential categories have already found applications in machine learning and automatic differentiation. So that, in particular, the very first talk at ACT was about reverse differentiation by Paul. But what's today's story about? So in that paper that I talked about reverse derivative categories, it introduced the notion called Cartesian reverse differential categories. Now, the forward counterpart to these are just called Cartesian differential categories. And these capture, multivariable calculus over Euclidean spaces and the differential lambda calculus. But there's another part to differential categories, and those are called monoidal differential categories. And these sort of capture the more algebraic foundations of differentiation and differential linear logic. And probably the first big result in the theory of forward differential categories is that the Coe-Kleisele category of a monoidal differential category is a Cartesian differential category. So today's story essentially is that we wanted to introduce the notion of a monoidal reverse differential category, which are precisely those categories where the Coe-Kleisele category is a Cartesian reverse differential category. Okay, so the first question you should ask is, why did we think that this was actually possible? Why is the notion of a monoidal reverse differential category, sound legit? And the answer is because there's a link between forward differentiation and reverse differentiation. So if there's one slide to take away from my talk today, it's this one right here. So this is probably the most important slide. It's that reverse differentiation is equal to forward differentiation plus a transpose operator. And from a category theory perspective, this transpose operator will actually be give a dagger category structure. So again, what this means, this is again the most important part of the talk, is that from a reverse derivative, to define a reverse different derivative is the same thing to define a forward derivative plus a transpose operator. So can I make that a bit more precise? So very, very briefly, a Cartesian differential category is in particular a category of finite products, which comes equipped with a differential combinator D. where for every map from A to B, its derivative d of f is a map from A times A to B. On the other hand, a Cartesian reverse differential category, again, in particular has finite products, but also comes equipped with, this time comes equipped with a reverse differential combinator R, where this time, given a map from A to B, the reverse derivative is going to fit the B into the domain and the A into the codomain. So now R of f is of type A cross B to A. So down below, I put here a really simple example of a function from R2 to R. The forward derivative essentially is given by the sum of its partial derivatives, while the reverse derivative is given by the pairing of its partial derivatives. So how can we define one from the other? Well, the key to this is the notion of a linear dagger. So in any Cartesian differential category, there's a natural notion of a map, what it means for a map to be linear in a certain argument. And this notion of being linear is sort of the same as the classical notion from linear algebra. But if you want to express it in terms of differentiation, it's essentially a map that when you differentiate in terms of that argument, you get back the function you started with. So very briefly, a map from C times A to B is linear in its second argument A, or linear in context C, if when I take its derivative and I evaluate at 0 in the middle arguments, which is how you define the partial derivative from the total derivative, well, you just get back f. And these linear maps form a fibration over any Cartesian differential category. And to say that a Cartesian differential category has a contextual linear dagger is to ask that each fiber of this fibration is a dagger category. So explicitly, for any map which is linear in context C, there's a way that I can swap the B's and the A, swap the B and the A, which I'll call F dagger. And this dagger, well, it gives you a dagger category, so it satisfies, contravariance, involution, and also preserves linearity in the second argument. And so the main theorem about Cartesian reverse differential categories is that Cartesian reverse differential categories are precisely Cartesian differential categories with a contextual linear dagger. So this was a story for the Cartesian differential categories. And we're going to use that to pave the way to how we're going to define monoidal reverse differential categories. So to do so, to define monoidal reverse differential categories, we need to understand the following for just monoidal differential categories, which is what are the linear maps in context in the Copley's category, and how do I define a contextual linear dagger in this case? And therefore, what we're aiming to get to is that a monoidal reverse differential category is just going to be a monoidal differential category with a contextual linear dagger. Okay, so again, just very briefly what the definition of a monoidal differential category is. Well, it's going to be a symmetric monoidal category, which is enriched over commutative monoids. So I can add maps and I have 0 maps. And because it comes from differential linear logic, this means that it's going to come equipped with the comonad bang, such that bang of A is a co-commutative comonad. So I've drawn the structure maps in string diagrams, which should be read from top to bottom. So the first two is the comonad structure, while the second two, the second two on the right are the comonoid structure. And what makes this a differential category is it also comes equipped with a deriving transformation, D, from bang of A tensor A to bang of A. And these satisfy basic axioms of differentiation like the Leibniz rule and the chain rule. Now, if you recall, I said that the Copley category of a monoidal differential category is a Cartesian differential category. So recall that for comonad, the Copley category has the same objects as the base category, but where a map from A to B is actually a map from bang of A to B. So how do I define the differential combinator in the Copley category? Well, if I give you a map from bang of A to B, its derivative, d of f, which is now type bang of A cross A to B, is defined as follows. So what you do first is you copy bang of A cross A. Then on each wire, you do a projection where pi0 projects out the first argument and pi1 projects out the second argument. Then on the second wire, you're going to do epsilon, the co-unit of the comonad, to go from bang of A to A. Then you're going to do your deriving transformation, which is the part that's sort of differentiating F, and then you're going to follow that up with F. So what are the linear maps in this Koch-Fliesly category? Well, so in our paper, our first main new result is the fact that we classify precisely what it means for the linear maps in context in the Koch-Fliesly category are. And it turns out that they actually do have a nice description. So a linear map in context in the Koch-Fliesly, for example, bang of C cross A to B, correspond precisely to maps of the form bang C tensor A to B. And this is actually, this is sort of expected because in linear logic, the notion is that bang of C is the nonlinear part, while A without a bang is the linear part. So this makes sense. So how do you get this equivalence back and forth? So if I give you a map in context, which is linear in context from the Koch-Fliesly category, the way I get to a map from bang of C tensor A is, well, I use the injections because my product is actually a byproduct. And then I do use the deriving transformation. So it was necessary to have a deriving transformation to get out this result. And the way we express this in our paper is in terms of an isomorphism of fibrations. Okay, so now that we have the linear maps, how are we going to define a contextual linear dagger? Well, because we know that the linear maps are of the form bang C tensor something, well, to give a contextual linear dagger is equivalent to giving a combinator on maps of these types. So if I have a dagger now that takes something from bang C tensor A to B and spits out something from bang C tensor B to A. So I don't have to work in Koch-Fliesly category anymore. And it turns out what's actually a bit surprising is that under very minor assumptions that any model of the differential linear logic satisfies, to give a contextual linear dagger is actually equivalent to asking that the base category is a self-dual compact closed category. So by a self-dual compact closed category, we mean a compact closed category where A star is equal to A and also where the twist equations hold. So this means that I have my cups and caps, which now go from A tensor A to the unit and the unit to A tensor A. I've got my snake equations, and I also got these twist equations. Now, I should point out that the twist equations aren't strictly necessary, but we found that it greatly simplifies the string diagrams, and all the examples that we have so far satisfy this. And actually, if you go look in the literature, we found that a lot of people, when they define the notion of a self-dual compact closed category, they do include the twist in the equations, especially when they talk about the self-dual compact closed prop. Okay, so how do we define a contextual linear dagger? Well, we use the cups and the caps. So if I give you an F, well, I'm going to use the cap on my A and the cup on my B to define my dagger operator on these linear maps in context. So essentially, a monoidal reverse differential category is going to be a monoidal differential category, which is also self-dual compact closed, which replaces the contextual linear dagger. But that's all nice, but you know, it's a natural question to ask: can we define the reverse differential separately in this context? The answer is yes, but it might not necessarily be more practical. But just to get the complete story, a monoidal reverse differential category is going to be a self-dual compact closed category, which is again enriched over commuted monoids, comes equipped with a comonad such that bang of A is again a co-commuted comonoid, but this time comes equipped with a natural transformation called the reverse deriving transformation, which we call R, which is of type bang of A tensor A to A. And these are going to satisfy reverse analog to the reverse deriving transformation, but instead involving the comonad structure, it's going to involve the adjoints of the comonad structure. I should also say that unlike in the Cartesian case, it doesn't seem like the transpose comes free from the reverse differential structure, and we do actually have to impose a self-dual compact close. We found it very difficult to express the axioms without having cups and caps to start with. So here's the main result that we were hoping for, that a monodal reverse differential category is precisely a monodal differential category, which is self-dual compact closed. And the way that you define the reverse derivative deriving transformation from the deriving transformation is again using these cups and caps and essentially just applying the contextual linear dagger. But the main result that we really wanted to get was this one. It's that the Kokleisly category of a monodal reverse differential category is a Cartesian reverse differential category. So for a map bang of A to B, its reverse derivative, which is the type bang of A cross B to A, well, you can express it either in terms of the reverse deriving transformation or the deriving transformation. So on the left, I use the reverse deriving transformation, where this funny snake equation with F in the middle is usually what's called F star, the adjoint of F that you get from the compact code structure. On the other hand, if you want to express it using the deriving transformation, well, you pretty much do more or less how you defined it before, but using the cups and caps as well. So Kokleisly categories of monodal reverse differential categories are suitable models that we can apply reverse differentiation and hopefully apply, machine learning algorithms like supervised learning, automatic differentiation, etc. One cool thing that we really wanted to mention is that surprisingly, it turned out that monodal reverse differential categories have some ties to categorical quantum stuff. So for example, we found that a model of a monodal reverse differential category is Selinger and Vladimir categorical model for quantum lambda calculus. We also found that every monodal reverse differential category where bang of A was actually the co-free comonoid over A was actually a model of Jamie Vickery's categorical quantum oscillator. And it'd be interesting to see if in future work, study the categorical quantum oscillator from the point of view of differential categories, and also see what reverse differentiation adds to, categorical models of quantum lambda calculus. There are other examples of monodal reverse differential categories, like the category of sets and relations, or the category of finite dimensional vector spaces with a chosen basis over Z2. But we kind of struggled with finding other examples because they really aren't easy to find. In particular, just the notion of self-dual compact closed models of differential linear logic are difficult because the intuition is that, bang of A sort of has an infinite dimensional flavor, while cups and caps, on the other hand, sort of usually have a finite dimensional flavor. But there is a sort of refinement that you can do to, from any monodal reverse differential category, pick out a Cartesian reverse differential category. And the way you do that is you take a subcategory of the Kokleisly category, where you only take the objects that are self-dual in the base category. And you can do the same constructions that I showed before, because being self-dual means you have cups and caps to get a Cartesian reverse differential category. And this is an interesting construction, but the main goal of our paper was that we really wanted a model where the entire Kokleisly category was a Cartesian reverse differential category. So to finish up, what I wanted to point out is that another reason that we are interested in this is that in the theory of differential categories, what's really cool is that, the main components of the theory of differential categories are essentially all connected. There's a map of differential categories. And so each of these components are connected via some construction. So today I sort of focused on, differential categories to Cartesian differential categories via the Kokleisly arrow. And so what we're hoping for is to build the map of reverse differential categories. And so today, again, the main part, today's story, we added the Kokleisly arrow, but we're hoping that in future work, we're able to fill in this map and also fill in this bottom quarter called reverse tangent categories, which is so far still in the works. And I think that actually some people at StratPod are actually working on this too. And so, yeah, so we're hoping to chug along and keep mapping the world of reverse differential categories and keep finding new models of reverse differentiation and suitable models for machine learning and differential categories. And that's it. Hope you enjoyed. Thanks for listening, and merci.
send you some questions. And this time, let's start with the online. So, any in-person questions? Yes.
Hi, thank you for the talk. So I would ask you to elaborate a bit on why the quantum harmonic oscillator is a model for cabinets. That's because the bosonic, the Fox-based functor that's used there is it's an infinite dimensional space variable.
Sorry, could someone repeat the question? I really can't hear.
Yeah, try to repeat maybe. Can you hear me?
I can hear you.
Okay. So I wanted to ask you if you could elaborate on how the categorical the harmonic oscillator is a model for monoidal reverse differential categories, because there they use the Fox-based functor, which I guess you could interpret as a bank. Can you hear me?
Yep.
But it gives an infinite dimensional Hilbert space which doesn't have caps and caps. So yeah, how does it work?
So in Jamie Vickery's paper, actually, he doesn't require cups and caps. I think he only requires dagger structure. So in our case, it's a very specific model of the quantum harmonic oscillator. But in our case, we use the dagger of the cups and caps. But in general, a quantum harmonic oscillator is always going to be a forward differential category where the band is the Fock space. And I think the differential is given by, annihilation and creation.
Okay, thanks. So in particular, these monoidal reverse differential categories, they don't need to be compact closed. Or do they?
No, monoidal reverse need to be compact closed, but Vickery's categorical quantum oscillators do not need to be compact closed.
Okay, thank you.
All right. There seems there are no more questions, so let's thank our speaker again. All right. So next up should be a software demo. Do we have the speaker? Okay. So next in, well, I have to share the people from my own research group. Okay, so we have Younesse Kaddar with statistical programming with categorical measure theory and LazyPPL software demonstration.
Great, thank you, Paolo.
So you may want to wear this.
Yep, sure. Is there a way that I could connect the Mac to? This thing is there HDMI? Can I connect it?
No. I think probably easiest would be if you go from the Zoom call on your laptop and speak.
Oh, okay. Do I have the link for the Zoom call? It's a question. 1, 2, 1, 2. It's working. Right. Okay. Where's the Zoom? Yeah, it's UQAD, YOUQAD, YOUQAD @gmail.com. Thank you. Yep. YOUQAD @gmail.com. Thank you. Thank you. Awesome. Great. Working. I mean, it should be. Oh, yeah. I have to sign in. That's right. Okay. Sorry for this, everyone. Right. Now, if I go there, launch meeting. Show my video. Awesome.
Probably don't need the video, right?
Yeah, you're right. You probably don't need it, but it's okay. Yes, got it. Oops, share screen. Gonna share the whole screen. Right. Okay, should be okay. Perfect. Thank you. Thanks. Just minimize this. Minimize this. Does it work? Okay. Awesome.
Okay, so we now have Younesse Kaddar with LazyPPL demonstration. Just so you know, since we started late, we will have the coffee break at 35. Okay.
Okay, I'm gonna try and be as quick as possible. Thank you very much. So, hello everyone. So my name is Younesse. I'm a PhD student at the University of Oxford, supervised by Sam Staton. And today I'm going to talk about a joint work with Swaraj, who's there, I think, Hugo, Paquet, and Sam as well. LazyPPL, which is basically a probabilistic programming library in Haskell. I mean, in Haskell, to do probabilistic programming, and it's inspired from categorical measure theory, as I'm going to hopefully show you. All right, so first, a little primer, very quick on probabilistic programming, just in case. So what is probabilistic programming? So the way I like to think about it is, you could say it's a paradigm for programming whereby you sort of there's a clear separation between writing statistical model and doing inference, basically. So I won't talk about the inference at all because it's not the venue. We don't have the time. But the idea is you can think about it a bit like trying to reason from consequences to causes. So let's say I observe something, I don't know, in nature. I don't know, like observe a phenomenon, a physical phenomenon, for example, or symptoms, you could say in a medical diagnosis or something like this. And I write a statistical model which is based on parameters that I don't know, which sort of leads to the outcome I'm observing. And the idea of probabilistic programming is that the statistical inference is done automatically for you. So you're going to constrain the parameters based on what you observe. So yeah, at some point, yeah, Bayes' law was called inverse probability because this is the idea of going from consequences to causes. So this is Bayes' law. And in probabilistic programming, you have basically a construct for every clause of Bayes' law, you could say. So sample, you have a sample construct to sample from a prior. So the prior is basically your knowledge, your belief about the phenomenon before observing anything. You have observe or score. I could have written score actually. It's score in LazyPPL, which is about likelihood. It's about specifying the likelihood. And you have infer and normalize, which is about normalizing the posterior, basically. And the hard thing to do is actually the infer, the normalize, because the thing is we don't actually know how to efficiently compute the normalizing constant. That's the hard problem. And what statistical inference algorithms are doing, some of them, at least the MCMC class of algorithm, is to still manage to sample from the posterior without even knowing, without calculating explicitly the normalizing constant. Okay, so this is a little example. I'm going to go back and forth with the VS Code to show you a little demo. So this is an example in LazyPPL of a generative model, or a statistical model. There's no observation, as you can see here in this example with linear. No observation, but it's very. So I sample from a normal distribution A, slope, let's say, a B, which is an intercept, and then I can return a function, a linear function, with this slope and this intercept. So first point to note maybe is that it gives you a probability distribution on a function space, which is something you don't really have in measure theory. So that's the first point to note. And it's very sort of functional programming language-like, right? Because we really want to have functions as first-class citizens. It's a tenet, a very important tenet in functional programming. Then how do you do inference on this thing? you can, so this is linear regression, right? The idea is to say, okay, the point I'm observing, and I'm going to show you some figure in a second, or maybe I can show you the figure right now, actually. Let me just put that away. All right, let's say, okay, so yeah, so I'm going to run the regression on this example. Hopefully it's going to work because it's doing the computation live. Let's see what's going on. Yeah, so here you have an example, little figure. So these are the black dots. Oh, is it working? 1, 2, is it working? Yeah. Oh, okay, yeah, so sorry. So black dot is your observations, the thing you observe. And the linear functions that you see here. So the thing that, so you get a whole posterior. You don't. It's not as in normal, let's say, frequency statistics where you get just one sort of maximum likelihood sort of result or outcome. Here you get the whole. Oh, it's not working. Okay. Oh. The battery run out. Thank you. One, two. Is low. Okay, works. Awesome. It seems to be working. It was better than earlier. Great. Okay, so the black dot that you see here are your observation, and after inference, these are the possible fits, and we sampled a couple of them, like 1,000 of them or something like this, and you can see how it's displayed. So this is regression. In regression, how does it work? So the idea is, of course, you can't really fit a linear function going through all of those points because they're not even collinear, right? So it's never going to work. So the idea is to say, okay, these observations are actually noisy. There's a noise, there's a Gaussian noise behind, and that's what you write when you do the regression here. You say, okay, I sample from a prior. This prior is linear in this first example. So I mean, it's a prior of the linear functions. So this is my sample. And then what I do is that I'm going to score. So this is the observed construct, the score construct I told you about earlier. But the likelihood, I'm going to score what I observe based on a certain like Gaussian distribution with a noise sigma, which is, I mean, a standard deviation sigma, which is specified by the user. And then you return your F. So this is okay. So this is the statistical model, and then you can do inference on this one. So I'm not gonna, as I said, I'm not going to go into details about the inference, but we run a Metropolis Hastings algorithm on this one, and then you can see the results. So this is a little example about simple linear regression. All right. Okay, so semantically, what's going on? What's going on semantically? The idea is that so probabilistic programs can be sort of interpreted from a denotational point of view as spans of this form. So what is this? Here you have a space, measurable space of hyperparameters. You have a space P of parameters. So these are the things, P are the things that you sample in your statistical model. The A and B are elements of this P, for example, that you saw earlier, the little a, little b that I have earlier. And then you have a likelihood function like this, which is a measurable function. So the likelihood is basically the scoring thing that I showed you earlier. So the likelihood, and you have a result function. What is the result? It's you based on what you, so for example, the result here would be computing this linear function based on the parameters A and B. This is what the result is doing. So you have a span of this form, and actually these span of these forms. I mean, the idea. So what is the inference doing? The inference is simply sampling a point in P. Or let's forget the hyperparameters for the time being. You're sampling a point in P by considering the likelihood as being a density function. So as if it was a density, and you can actually construct a measure on P such that L is a density for this measure. That's what you're doing. So in practice, this measure on P is going to be uniform, and you'll see why later. You can always sort of come back to the uniform function because of the noise outsourcing lemma. We're going to talk about this later. And then, okay, so you sample this, and then when you have your P, you just determine the results with R of P. You just apply this R here. This is what happens semantically. But you have some problems with this. With category theorists, we don't just want to talk about the objects. We want to talk about morphisms as well. What is what does the category look like? The big problem is that the category of measurable spaces, as I hinted at earlier, is not Cartesian closed. What does it mean? It means you don't have things like this in measure theory. You don't have an internal home. You don't have a space of functions. This is the first problem, because as you saw in LazyPPL here, we actually use a space of function. We could have done without it. You could have just done a parameterized version like this. It's a bit hacky in a way. It works in the case of linear regression because it's simple enough. But in more complex examples, it's going to be a problem not to have these higher order functions. So you don't have a function space. And another problem is that we don't know. It's a conjecture. So if any of you is inspired, you can try and solve it. We don't know if there's a strong monad of measures in this category. So basically, another way of seeing this is to say the category of S-finite kernels. So these spans that I showed you earlier, you can see these are they're equivalent in a certain sense to S-finite kernels if in probability. These categories have very good property for us, applied category theorists. It's distributive, symmetric monoidal, but we don't know if it's a Kleistli category or not. So in programming terms, it's a bit annoying because we don't know if we can model effect. We would like to model algebraic effects by a monad, right? We don't know if it's a Kleistli category or not. That's another problem. And so the idea is to say, okay, as I hinted at earlier, there's this very important lemma, very, very key and used everywhere. It's called the noise outsourcing lemma, or sometimes people call this in algorithmic form the inverse transform sampling, which is basically saying, okay, having any sort of if you have a random variable valued in a Borel space, so a nice enough space, which is going to be covering all our needs in probabilistic programming in practice. When you have this, you can see it, the distribution of this random variable as being the push forward of a uniform measure. So for example, on 0, 1, on a standard Borel space, and we can take 0, 1, for example. So in programming terms, you can, it's just, oh, I forgot a brace here, by the way. It amounts to writing things like this. If you have a kernel like this, you can say, okay, I'm sampling from a uniform distribution first, and then I'm applying a certain transformation to this. Oh, sorry, it should be U here as well. It should be U instead of P. I'm applying the transformation to get any distribution on any other space, basically. So the uniform distribution is enough for all your needs. And quasi-Borel spaces take this very seriously. They basically say I won't really define what these are, but it's a very well-behaved sort of category where you replace standard Borel spaces by quasi-Borel spaces. And a quasi-Borel space is basically a set which is equipped like with the notion of random elements. And this you have a space omega, a standard Borel space omega, which is basically thought of as the source of randomness it's exactly it could be the 0, 1 in the noise outsourcing lemma. So you take this as a primitive notion, and then you go from there. And this category has very good properties. It's Cartesian closed. There is a commutative monad of measures. And in LazyPPL, that's what we use to define two monads, a probability monad and an unnormalized measures monad, which give rise to two Kleistli categories, exactly what we didn't really have with the S-finite kernels. And another key point of LazyPPL is that we use laziness in Haskell. So laziness in Haskell amounts in category theory to having a terminal unit in the Kleistli category of a probability monad of prob here. So this laziness basically enables us to define models that are infinite dimensional or with unbounded parameters. It's called non-parametric statistics. It's very useful because it's extremely compositional. You don't need to restrict things arbitrarily. That's really the point. All right, okay, so I can skip this. I think I don't have time. And then you have this correspondence, basically. It's a bit like a Curry-Howard correspondence, but for probabilistic programming, you could think. That's what you have. Now, time for the demo, I guess, a little demo. So I showed you linear regression earlier with a very simple setting. Now let's exploit laziness really, because LazyPPL. Oh, by the way, I forgot to say, PPL stands for probabilistic programming library. I forgot to say, by the way, and it's pronounced LazyPPL. I guess, yeah, I don't know. We got inspiration from our own lives, I guess, for this name. Anyway, so the Poisson point process. Okay, so a Poisson point process is a simple example of a non-parametric, model in Bayesian statistics. What is it? So you have the real line. You take points on this real line. So, for example, these points could be at which time, I don't know, like earthquakes happen, for example, under certain assumptions. Or maybe, I don't know, like buses in a city probably not in the UK because the buses are deterministically late in the UK, but you know, in a city where there's some sort of randomness and you can't really prove, I mean, you have some sort of nice enough assumptions about the buses that are independent and everything. So this is a Poisson point process. So you can define it. So in a way, you get a distribution of, so the list here is really a stream rather than a list, but in Haskell they coincide, right? So it's really a stream because you're basically constructing an infinite list here. If you look at this, there's no base case in the recursive sort of definition. But it's not a problem. Why is it not a problem? Because when you use it later, when you do inference, Haskell is going to do the minimum amount of work possible so that what you write makes sense, like the minimum amount of computations possible. So it's not going to really compute the whole list, of course. I can give you an example. For example, if you let's talk now about piecewise regression. Okay, so what is this splice function? This splice function, the intuition is to say, I take a Poisson, not necessarily a Poisson one, but I take a point process as an input. I take a prior over random functions. So this prior could be, for example, the linear function that I showed you earlier. It could be the quadratic function like this. It could be anything, any class of function that you want, really, as long as you have a prior. And then the splice function is basically forming a function on each of the segments that are given by the point process. It's forming a function by sort of, on every segment, it's going to sample one function from your prior. So it's piecewise, it's defined piecewise. And now you can see, for example, that, okay, I can give you an example. Instead of, right, look at it, okay. So what we can do is to say, okay, I want to do, it's exactly the same infer regression function that you had earlier. I didn't change anything in the code, but I just changed here the prior. The prior is the only difference. I'm saying, okay, take a piecewise function for a Poisson point process with these parameters with the linear prior, which means my prior is gonna be a prior over piecewise linear functions. And then I do the inference on a data set. Okay, let's say data set 1 for, okay, let's see what it's gonna give us. Yeah, here it is. You see, so now the functions are piecewise linear, not necessarily linear. Many of them are actually linear because it's a pretty good approximation for our data set. But if I change the data set, if for example, I say, okay, I take another data set, and you're going to see the data set really are the black dots. Take another one here. So here you see it's definitely not linear, my data set. But it's not a problem now because my prior is piecewise linear, so I can still find piecewise linear functions. And the darker, the more probable, by the way. The darker, the more probable in this example. Okay, so another example I can give you is program induction or program synthesis, if you want, which is we can define a little DSL like this of expressions. So arithmetic expression, I have variable, I have constants, real function, I have an addition and multiplication, I have an if then else construct. And then, okay, so let's forget about this thing. Then I have an evaluation function. So for every expression, I can evaluate it. I can say, okay, this expression can be seen as a function on reals. And then again, it's just a matter of coming up with a good prior. So this is these two mutually recursive functions are generating a random expression. They're just based on the DSL I just showed you. So I can sample a random function based on an expression. And then I can do exactly the same thing. I can do exactly the same regression that I showed you earlier with the Gaussian noise. And I could take any other noise if I want. Not necessarily Gaussian, but Gaussian works well, let's say in practice because of the central limit theorem or something like this. And I can do the inference. Okay, let's see how it. Let's see what it gives you. Okay, do I have? Yes. Okay, let's say this for example. It's going to be probably a bit slower because, of course, in this case, it's not really. It's a bit more complicated to compute the prior, right? Then I wait for it to arrive. Hopefully it's gonna work. Oh yeah, because So this is an example. This is the example. Okay, where is it? Here you can see. So I just plotted 3 programs, of course, because plotting programs is a bit complicated. Thank you. Thank you. I was sweating a little bit right now. But yeah, 3 programs. So the darkest one is the most probable one. And you can see it's trying to find a program going through the points. And of course, in my programs are all linear, they're based on linear functions in this case. I don't have a quadratic construct. But if I, in my DSL, I had quadratic functions, I could see that here it could be approximated by a quadratic function, and here another one, for example. So that's how it works. And the idea is that it's very compositional. Why? Because at no point do I say in the Poisson point process, for example, what is the size, what is the number of points? I don't specify the number of points. The number of points is going to be specified at the very last minute when you want to plot the thing. When you put to plot, it's going to just compute sufficiently many points for plotting what you want. So all the models that I have here are non-parametric. I'm not bounding arbitrarily the space of parameters. Okay, so and these are some plotting routines. There's another example with the Wiener process. I don't know if I have time to show this one, but the Wiener process is basically, I don't know if some of you are familiar with the Gaussian processes, but it's basically like a Brownian motion, you could say. Okay, let's look at this. Can't remember what I called it. Yeah, regression Wiener. Okay, let's look at this. This one is probably going to be a bit slower, so maybe I can conclude. Oh, I think I'm already on the last slide. Okay, let's wait for it a little bit then. Oh, did it work or? Not a good sign, this thing. Keyboard interrupt. Oh yes, it works. Okay. So this is okay. So sometimes it's a bit unstable, but I mean it does work here. So here you can see that we're doing a Gaussian process sort of regression where it's really Brownian motion like, right? It's extremely it's much more sort of kind of a what's the word for it? I mean, yeah, it's differentiable. It's nowhere differentiable, actually. It's nowhere differentiable in this case. But again, this is infinitely dimensional, inherently infinitely dimensional, but you just compute the number of points you really need to plot it, basically. That's the idea. So yeah, so I guess the take-home sort of message is to say that we can really take this idea of laziness very seriously. It corresponds in category theory to having an affine monoidal category. So it ties in with the notion of, by the way, of Markov categories, or Underskog had in a syntactic measure theory of Underskog as well. But I mean, like in this case, it's much more categorical probability theory, because the affineness corresponds to having really a probability monad here. And so you take this very seriously, and this laziness basically enables you to not truncate arbitrarily your models. It's just truncated at the very last minute when it's needed for the viewport. So it's very useful for compositionality, because then you can compose, as I showed you, models without truncating them arbitrarily. If you did this for, yeah, so I'm done by last sentence. If you did this in an eager evaluation language, for example, you would have to say how many points you want for a point process, how many, like, where do you want to, how many points you want to sample for the Gaussian process as well. And you can do this for small models like this, but when it's you start to compose models, it becomes more and more complicated, I guess. Thank you very much for your attention. Thank you. Yeah, sure.
So yeah, we have time for like one quick question. There doesn't seem to be any online question. So let's do one question here and then move the rest to the coffee break.
Yeah, sure.
Great, thanks. Thanks for the great talk. I'm really excited about this. I've seen a few different foundations for categorical measure theory.
Yeah, yeah.
Can you talk about like what the different options are? There's kind of trade-offs. There's got to be a trade-off space.
Yeah,
right?
yeah.
And what your recommendations would be going forward if someone wanted to build on this work.
Yeah, that's an excellent question. Very interesting question, because so it depends what are your objectives, right? If your objective is to do practical probabilistic programming, then maybe you don't have the same objectives as people who are more motivated by the fundamentals, like what are the. So I guess yeah.
I'm in that first category.
Oh, the first category. Okay, okay. I guess I guess the key point is to. I mean, or at least that's what. I mean, Paolo is an expert on this, by the way. This was, the key point is to say, okay, so in this example, we're building a Kleistli category, right? Because we want to model effects in terms of monads, which is a very traditional thing to do in Haskell. And the property this Kleistli category should have is that it should be monoidal. Oh, sorry. And it should be affine as well, which means that the unit of the tensor should be terminal. It's a terminal object. That's the idea. So all of those, so you have so underscore who was saying, so I guess the key point is to say for monad to be a probability monad, really, what are the key properties it has to satisfy? It has to be commutative. So commutativity amounts in probability theory to having the Fubini's theorem. You can reorder integrals. And it has to be affine. Affine means that it preserves the terminal object, basically. And it's exactly saying that the Kleistli category is affine as a monoidal category. The units of the tensor is a terminal object. And this affineness in probability corresponds to having normalized probabilities. So it's not necessarily obvious to see like this, but it's exactly what it corresponds to. So I guess, yes, fundamentally, that's what's behind. And I guess in programming as well, you could say, okay, if you're interested in this last sort of column about probabilistic programming, you can actually exploit this affineness to, it corresponds to laziness, right? To discard the things you're not using. So for example, in this, all these examples with the Poisson process and all those things, I don't know, the Wiener example is a bit more complicated. I didn't have much time to talk about it, but in the Poisson process, you're discarding everything you're not using. And this ability to be able to discard what you're not using is exactly having an affine monad. It's exactly this that you're exploiting. Yeah.
And that kind of like uniquely identifies quasi-Borel as the right notion of measure space.
I mean, so it's a model. It's a model. I mean, the model. Yeah, quasi-Borel spaces. It's a good category where you have these properties, but it doesn't have all the good properties. By the way, it doesn't support stochastic memorization, for example. I didn't talk about this because I didn't want to talk about quasi-Borel space in this talk. But it's not perfect by any means. But it does the job for these 2 points, having Cartesian closeness and a strong monad of measures, I guess. Yeah. You're welcome.
All right. So let's thank our speaker again.
Yeah. Thank you.
And yeah, apologies for the delay.
Yeah, thank you very much. Thank you so much, Paolo. I was so stressed that I didn't get to Uber. Yeah, to you, it's completely obvious to you, I guess. Yeah, I think to me it was a good presentation because, but I'm using stuff for it. Yeah. But I think also for other people, it's like the point was yeah, I tried to make it as accessible as possible, but at the same time show the advanced notion in the I guess in the program as well. Thank you very much for it. Oh, sure, yeah. Very, very rushed sort of.
Why would you be stressed if you know Sean was from the audience?
Because I mean, he can double check everything I say on live. Absolutely, he could compile in his head all the examples, so I couldn't cheat. Yeah. Thank you very much. Thank you so much. I was so stressed because I couldn't get a taxi to come here. So I usually came by phone. I ran on the way. And I'm so scared. From where? It's not super well. I'm in Airbnb, and I was very late yesterday at night because the flight was delayed yet again. It was delayed, so yeah, it was a bit complicated. I'm still jet lagged from the US, I guess. David? Yes, yeah. Nice to meet you too. Yeah, it's really cool. Thank you very much. DSL and then. Oh, yes. You can't share it. So you could regularize. There was some sort of regularization. All I know is like the operator. Right? Yeah. Because first of all, it should be binding to those that you want to pick the one. Second of all, that's one. It's excellent enough because actually, so I was thinking I'm coming back from the US, and there was a conference about neuroscience programming. And it's exactly the new area of programming where so the big players on programs. Programs using statistics ideas. And one of the talks was about trying to use all kinds of race. You don't want to have
I mean, you don't overfit. That's the
You
problem.
know what the
If
file
you don't want
every possible,
like so it was called
it's like, no,
and you don't know this. So this was the tool example, of course. But that's very
sent it like this.
it's actually very easy. So the
part of my
Yes,
some sort of homologous complexity.
it was called H.
Literally the number
Monoidal
like the number of like I don't want a 0.64.
I can try to re-upload it.
One real number. I just want 0.6.
That's a very good point. But then you assuming that longer programs are inherently more complicated, which is not the case in my DSM. But sometimes you can have very complicated if you add some primitives to your program. Like your DSM can have, I don't know, like
Effectful Mario? Yeah.
yeah.
Which one? So the last one. And the one that I do first is Monoidal.
I don't know. That is not like I said.
Thank you. The other one,
I said like, you don't have to get
changes at last minute.
Probably some like actually good way to give it prior. And you have to go with whatever the one that makes the compiler happy.
Absolutely, it's an excellent question because it really ties into this idea of trying to find a good trade-off, not to overfit your thing. Yeah, it's always easy to overfit, but then you lose the generality after this. You're gonna fit your point very well in the example, but you won't generalize very well on a point that you haven't seen.
Yeah, the more you're using operators, yeah.
Yes, and what they do actually, this programming community, is that they actually use neural networks construct in the language. In the DSR, they can actually call a neural network. So this can be very complicated to estimate the difficulty of the program. Because calling the neural network once can have an enormous cost. Can be much more expensive computationally speaking, and when it comes to Occam's razors sort of standards, than having a little two conditionals that are nested, for example, something like this. And then what they come up with is regularization of machine learning. It's the idea that you're going to punish, you have a loss function on your program, and you're going to punish whatever this complex by having a regularized what they do. This is super interesting.
But you might be able to say, this is compilation this one.
Yeah.
I now want to I want to condition on small compilation time.
Yes,
and have the compiler itself be like improved automatically.
Yes, yes.
There's so much.
Yes, there's so much
singularity
happening there. It's inherently undecidable, right? Because you want it's really this sort of Turing problem of saying, okay, well, you can't really know when a program is going to stop. What you ask is a good question we're interested in, but from a fundamental point of view, it's undecidable. So you have to find approximation to
Also, how to use this microphone. Oh, I see. I'm carrying this.
This one, just open the mouth. I don't know what it is. Yeah, take this one in your pocket. Where's the second take gun? Second one. Yep. Can you hear me if I talk like this? Nice. Yeah.
Okay, so welcome back. We start with a distinguished talk. The speaker is Mario Román, and he will talk about monoidal streams and statistical programming.
Wow, thank you. Thank you very much, Dylan. And thank you to the organizers. So I'm going to be speaking about this notion of monoidal streams. So monoidal streams should be to monoidal categories what streams are to set, to the category of sets. And the thing I'm going to be presenting is this paper joined with Elena Lavore and Giovanni Felice, who are in the audience, so you can also ask them for questions. And I'm going to use here, I'm going to explain basically here the part of monoidal streams. I'm going to use Dataflow programming just as a motivation of why we want to do this construction. So let me start by this motivation. Dataflow programming is going to be a programming paradigm. So we have been seeing today probabilistic programming, but we can do things like differential programming. We can do things like functional programming or imperative programming. So Dataflow programming is a particular paradigm. And the thing that is peculiar about this paradigm is instead of having a declaration of a single value, every time we write a declaration of a value, what we are really doing is declaring a sequence of values. So somehow you should imagine that when you are doing Dataflow programming, every time you give some statement, the thing you're saying is not only what's its value, but also a value at every point in time. And that allows us to do this kind of inductive definitions, where we say, for instance, the natural numbers are 0 followed by 1 plus the natural numbers. This means I'm going to get a sequence of natural numbers indexed by something that we could think is time, so indexed by natural numbers. And we have 0 followed by then 1 and the natural numbers again. Or if I define something like Fibonacci, I will say that the Fibonacci numbers are 0 followed by 1 followed by the delayed Fibonacci sequence plus the Fibonacci sequence. So these are the two operators that make everything work. One is called followed by in Dataflow programming, and it allows you to define a stream by defining the first element and then the rest of it. And then we have an operator that delays by 1 unit of time a stream. But somehow we still need to preserve time. We cannot get any value from the future. So why is this programming paradigm interesting? Well, they have a good syntax. I'm trying to argue here that this syntax can be very elegant when you try to define sequences of numbers or sequences of values. They also use these trace-like diagrams, these signal flow diagrams. So you can find diagrams that look suspiciously like diagrams for monoidal categories, even in documentation of these languages. So the languages like Lustre or Lucid. And then they have very good semantics. These semantics are done in causal streams, so we call streams. And they recover all the structure we are talking about here. So I'm going to give semantics to them following Ustalvo and Bene. So they do this by speaking of causal stream functions, which are just streams, but now they can take inputs. And the idea is that we will have families of functions indexed by time again. And every function is going to take not only the input that occurs at this time, but also all the previous ones. So we are saying that the output y0 depends on the first input. The output y1 depends on x0 and x1. The output y2 depends on all the previous inputs and so on. So the nice way of saying all of this is that we have a monoidal category of causal stream functions, and it happens to be the co-Kleisli category of the non-empty list monoidal comonad. So we'll have a comonad on sets indexed by natural numbers. And what this comonad is doing is multiplying all the sets until the point where, right? So here we'll take x0, x1, x2, and we will have x0, then x0 times x1, then x0 times x1 times x2, and so on. Why are these good semantics? Well, they recover all the structure that we were talking about here. They let us do some notion of delay factor that takes a stream of types and gives us the same stream, but now the first one is going to be just a terminal object, and then we write the stream again. They allow us then to do a trace-like operator. So it's going to be a trace, but it's just having this delay here, and that prevents us to reliving a trace. So this is just saying that if we have something that doesn't get an input on the first unit of time, that's fine, because then we will generate the first input and use that as a feedback to the second input and so on. So they do something that allows us to draw diagrams like this with some notation of trace or feedback. And then they allow us to do co-algebraic reasoning and co-inductive arguments, which are usually very elegant. So we have all these programs, we can reason with them using causal string functions, and this is all good. But then we want to do the non-Cartesian case, because I was arguing before that these things look like monoidal string diagrams. So one could say, well, perhaps if I don't want to have the copy to be always natural, then I don't need to have a Cartesian case, a Cartesian category. It could work in any monoidal category. And we will have a syntax that looks the same. Just we need to be careful of what we mean when we repeat a value. So for instance, if we are using stochastic functions, I can say that a random walk will be 0, followed by the uniform distribution on 1 and -1. So I need to decide which one I'm going in this first step, followed by a random walk. So right, we have a good syntax for this. We imagine what this should be for monoidal categories. We also imagine how the monoidal string diagram should work here. But the question is, how do we do the semantics? So these are going to substitute the causal string functions in the Cartesian case, and these are going to be the monoidal streams. Right, so the first candidate for this generalization would be to take the classic category of the monoidal comonad that we had before and just transform everything into monoidal, right? So if before we had this non-empty list functor that multiplied all the inputs, let's just have a non-empty list functor that we tensor all the inputs. The problem with this is that this happens to be a monoidal comonad if and only if the tensor is a Cartesian product. So the if part is okay, because we were expecting to construct the comonad with Cartesianness. But the only if part was interesting. I was not expecting it at the beginning. And it happens that if you try to define this comonad and then you ask for naturality and uniformity conditions on the monoidal category, that allows you to construct a comonoid on every object. And by Fock's theorem, that's the same as being Cartesian. So you can construct the non-empty list monad exactly only in Cartesian categories. And even with that, I promise to you that today, if you give me a symmetric monoidal category, we'll try to build a symmetric monoidal category of stream processes on top of that still have all the nice properties that we were expecting from it. So we'll have an identity object functor from the category of index object on the monoidal category. We're going to have a delay monoidal functor. We're going to have some notion of delayed feedback or delayed trace. It will have still a co-algebraic description, and it will recover the previous cases. So if we have that C is Cartesian, then we will recover the classical causal streams. And when you have stochastic functions, I think you recover discrete stochastic processes. So it seems to recover some classical cases. And then I'm saying at the end that we can extend this. I'm doing this with monoidal categories, and I'm going to be talking today about monoidal categories, but you could repeat the same trick with categories with a bit less structure than that. So how are we going to do this? Is by giving you 3 definitions of stream, and then 3 constructions of them. And each construction will be a quotienting of the previous one. So we are going to give a definition, and we are going to be refining that definition until we arrive to the final definition of monoidal streams. Right, so these 3 definitions are going to be intentional, extensional, observational streams. So the first one is a naive definition that doesn't even form a category. And then we're going to be quotienting that definition. I'm going to try to argue why each one of these quotientings is interesting and is good. The second one, we're going to define as a free category with feedback for some notion of feedback that resembles a trace. And the third one is going to be a solution to a fixed point equation. So we are going to have a coalgebra characterization of that one. And the cases we recover are causal stream functions, so the classical case of streams, and then we recover stochastic processes or control stochastic processes. Right. So then let me start with the definition of monoidal streams. Let's try to construct monoidal streams. And for that, I'm going to start with the definition of streams, the classical one. And I'm going to start with this slogan that says that a stream of types should be A1, A0, A2, should be an element of the first one of these types, so an element of A0, together with a stream of types A1, A2, A3. And this is not circular, this is coinductive. And this means that if the thing we're going to do is to write this fixed point equation of functors, and then we are going to try to solve it. This fixed point equation will have a solution that is terminal, that will have a terminal fixed point, and that will be the canonical solution that we were talking when we said this slogan, right? So this is a way of translating a slogan like this into a mathematical construction. So how can we do this? We have a Lamec's theorem. So Lamec's theorem allows us to construct the final coalgebra of a functor. And not always, but in some cases. And the idea of Lamec's theorem is in the same way that if you want to compute the fixed point of a function, like a real function, you could try to repeat the function again and again to just iterate the function and hope that you end up in a fixed point. You can do the same thing with functors. And this is what Lamec's theorem has to do. So if you have some operator on functors, you can apply it repeatedly to the terminal one. And hopefully that converges to some solution. What Lamec's theorem says is that if you can compute this limit, and this is actually a solution of the original equation, this is the canonical one. This is the final fixed point. So every other fixed point will have a fixed point morphism to this one. And in some sense, this is like the correct interpretation of this slogan that I was putting there before. So if we do this in the classical case of streams, the thing we have is a limit of this change of projections. The limit is just the product over the whole stream of types. So the thing we get is that this is a solution, and this is would be the correct interpretation of this slogan, right? This is how we interpret streams generally. All right, but then we can do this not only for streams, we have no inputs, but also for stream functions. So the slogan now is going to be that the stream function from x0, x1, x2 to y0, y1, y2 is a function from x0 to y0 and communicating along a memory channel with a stream function from x1, x2, x3 to y1, y2, y3. So how this works is that now we need to have some communication between the first part of the stream function and the second part of the stream function. If we don't put this communication here, then it will be just separate functions that go from x0 to y0 to x1 to y1 and so on. Somehow we need to introduce some notion of memory that allows us to save some computation from the beginning. And then by Lamec's theorem, we can do the same computation to find what is the final coalgebra of this, the final fixed point of this equation. So we compute that is this one, and it works. And we call that we are going to call that the definition of causal stream functions. If you look at this is exactly the same definition that you recover when you do causal stream functions in the style of Ustalon-Bene, but also in the style of Sprunger and Katsumata, which is the one that we are going to follow, because it allows to generalize to monoidal categories. So now the generalization that we could not do by using the coalgebra, the comonad, we can do now. By saying now a monoidal stream from x0, x1, x2 to y0, y1, y2 will be a morphism communicating along a memory channel that is here with a monoidal stream. So if you think of monoidal categories as theories of resources, what we are saying is when we have some input x0, we can decide what we do with it. We could send it to the output y0, or we could keep it for ourselves for later in the memory M. But we need to choose what this memory is. And then again, by Lamec's theorem, we can compute what's the candidate solution for this, and it gives this formula here. So this formula is going to be our first definition of monoidal stream. A monoidal stream is going to be a family of objects, these memories, and a family of morphisms that go from the previous memory and the current input to the current memory and the current output. So that's the formula for that. And now we say that the set of monoidal streams, we computed it as the terminal fixed point of this equation. So it's a canonical solution to this functor equation. Right, but I am giving you here a formula, and perhaps it's easier for intuition if we try to draw what a monoidal stream should be. So if we try to draw that in diagrams, the pieces we have look like this. The first one is going to take the first input and then give a memory and an output. And then the second one is going to take this memory and some input and produce a memory and an output and so on. So somehow the interpretation we have of these things is that this memory M0 should be also the input to the second step of the stream, even if that's not said in the definition anywhere. So the diagram that we have in mind is something like this. I'm going to do F0 and I'm going to give something on the memory that it goes to F1 and so on. The only thing I don't know is what will happen with the input and the output that I'm leaving. So there is a hole there. There is a part that we don't know still. And if you like the coordinating diagrams from the other day, from the paper that Chad presented, you can do something like that, having these outputs that go to the boundaries. Somehow these things are not going to be in our diagram. We need to give them to some other process. Okay, but this is not yet formal. So what's the thing that we are trying to do? What we are trying to say when we draw these diagrams? So this is the idea of extensional streams, which also solves a problem with intentional monoidal streams. So I gave you the first definition, but I was saying to you that it was too naive. They even failed to form a category. And the problem is that when you compose memories, so every monoidal stream needs to choose the memories. And these are chosen very strictly. So if you have two memories and they are different, then your monoidal streams are different. And this is very bad because, for instance, you could have two memories that are isomorphic, but now the monoidal streams are not equal. And not only that, but the problem seems to be more subtle because even if you have some morphism that affects the memory before and after, then that makes already the monoidal streams different. So the idea here is, imagine you have two monoidal streams. One is F0 and then some R0 applying to the memory, then followed by F1 and R1, followed by F2, R2, and so on. And then you have another one that is F0, and then it's R0 applying to the memory, but after we had already declared what our output and input was, and F1, then R1 and F2, and so on. These two monoidal streams should be the same. They look the same in our diagrams, how we are interpreting them. And the only thing that's happening is that we decide whether to act on the memory before or after we yield it. So if we want these diagrams to do the same, what we can do is just to quotient. This is not even an equivalence relation, but we can take the minimal equivalence relation containing this and we quotient by it. What we get here is, instead of having a coproduct, we have something that is called a co-n. Right, but depending on audience, you may like or not co-ns. So I have a different justification for them. If you like co-ns, I think this is a beautiful justification. We use them to express this naturality of R sliding back and forth. But here you may complain and say, well, I don't like this framework. What are you doing? I could have some other framework that does feedback in some monoidal categories and axiomatize the signal flow graphs in a different way. So what we have is some universality result that says that if you are trying to do something like feedback and you admit a bunch of actions that look very reasonable, so you admit that feedback should not influence the inputs and output, that is not touching. But if we do multiple feedbacks, that's the same as doing one. And that somehow we should have some notion of sliding with the delay factor there. That could be the identity, but it's the delay factor. So if you just accept these actions, the structure you're accepting is the one of feedback monoidal categories, as studied by Cathy, Sabadini, and Walters. And the thing we can prove is that extensional streams are the morphisms of the free category with feedback over the delay factor on the objects of your monoidal category indexed by the natural numbers. So this is to say, if you have some theory of monoidal streams that do feedback like that, and they satisfy some reasonable actions, so you're already somehow implementing extensional streams inside of that thing. So let that be a different justification for co-ns. And the co-n, the naturality, appears here as this sliding action on the feedback. So I guess that's a different justification if you do like the co-n one. Right, and what are we doing when we write some morphism then with the syntax of monoidal of feedback categories, and then we interpret that as a monoidal stream? Well, the thing we do here is like unrolling this morphism, right? We're going to be reading it from top to bottom again and again, and that gives us a monoidal stream like this. So my point is that the translation between the two is actually intuitive. Okay, but we go back. And I was telling to you at the beginning that we do all of this because we want to interpret the Dataflow syntax, the Dataflow syntax for programming. And the claim is now that this Dataflow syntax, this wait that needs to delay a stream, this followed by, are going to be implemented from this syntax that we have from objects indexed by natural numbers and feedback. So if we want to do wait, we need to do a feedback. And because it's not trace, this thing is not going to be the identity. The types are even different. And what it does is to take some input, keep it from 1 unit of time, and give it to the output later. And the followed by operator, the only thing it's doing is just putting the first component of a stream with the rest of the stream, and it puts them together and just as the identity. So we have derived also the syntax that we use, that we normally use for Dataflow programming. But these are not primitives now. They are derived from the syntax that we have from feedback. Okay, so I have presented this second definition of monoidal streams. Where are these families of morphisms that are quotiented by the S equivalence relation? But there is something still that doesn't work quite well. And the problem is that we will have two monoidal streams that are not equal, not even equal after we quotient by this extensional equivalence, but they kind of do the same from the outside. So what's the idea here? The idea here is that imagine we have some two monoidal streams. One of them just discards the input, and one of them keeps the input to itself infinitely. So all the time, it's going to never output anything, but we will have something in memory that is just kept. So we see that observationally, these two streams are the same. We are not going to see anything different if we execute one or the other. But from the outside, we cannot equate them because we would need like to do infinite sliding or something with this wire. So we define a notion of observational equality. And we say that two streams are equal if every time we truncate them, they are equal up to some future. And what I mean by up to some future is imagine I truncate here. Well, I could still imagine that there is a future where I discard here that makes these two diagrams equal, right? So if I can truncate at every point in time and still equate them up to some future, then they are going to be observationally equal. Right. So why do we have, I'm calling this observational equality? Is because this is the equality that we get when we describe them as a final coalgebra. So the theorem and the main definition from the paper is that monoidal streams with this observational equivalence by truncation are going to be the final coalgebra of this formula here. So this formula here was the slogan that we talked at the beginning, was saying that a monoidal stream is going to be a function, a morphism that communicates from x0 to y0, and then along some memory channel with a monoidal stream that continues the computation. And at the beginning, we were putting here a coproduct, but now we can put here a coen. So the coen is saying that it doesn't matter if we affect the memory at the beginning or if we affect the memory later. And when we compute the final fixed point of this equation with Adam's theorem, it's not as easy as before. We really need some technical conditions, and it doesn't hold in every monoidal category. But we still get something like monoidal streams. So why it doesn't work in every monoidal category is because there will be some pathological categories where you have morphisms that can factor in infinite chains. Those are technical details I'm leaving for the paper. But suffice for you to know that this works in every Cartesian, in every semi-Cartesian. It will work in every freely generated monoidal category. It will work in every compact closed monoidal category. So for all the categories you usually care about, this is fine. But there are still some categories where you cannot show by Adam's theorem that this is the final coalgebra. Okay, but for the categories that it works, then the definition is the same as we do a co-inductive definition of monoidal streams. So until here, I tried to convince you that we can construct monoidal streams and that they are a reasonable construction. Now we can forget about all of that and we extract some co-inductive definition of monoidal stream. So we say now a monoidal stream is going to be some memory, some object of our category, and what it does on the first step, and then a monoidal stream. And then we need to quotient them by this equivalence relation that we were talking about before, that says that if we have some translation between memories, it should not matter if we apply at the beginning, before we give the memory, the output, or after we take the memory. But now this is a co-inductive definition that captures everything we were doing before. So why would we like to have a co-inductive definition? Is because it makes many reasonings with monoidal streams very elegant. So at least I found them very elegant. The idea is that instead of working with this complicated construction that I gave you with coends, you can work with that co-inductively. And how it works co-inductively, or at least intuitively, is that you are going to do some transformation of string diagrams when you reason with them, and then you're going to extend that transformation by co-induction to your whole diagram. So the idea is we're going to work with something like infinite string diagrams, but if we want to reason by co-induction, we only need to pick one piece and then extend the reasoning to the whole monoidal stream. So this is, for instance, the definition of sequential composition. We need to strengthen our co-induction hypothesis. We do something like this, and then we extend the composition to a whole monoidal stream. So all the proofs work by checking the first step and then applying co-induction. And we can do this because we have this co-inductive definition of monoidal stream. Right, so I have now argued that we can have a definition of monoidal streams, that it has a nice co-inductive characterization that you can reason about it using string diagrams and co-induction, but you may want to see examples. So all of this is very nice, but if you don't recover the examples we care about, then we will not be doing nothing, right? So the first example is Cartesian streams. So our motivation at the beginning was to generalize streams, right? So a good sanity check should be to check that we actually get back the usual definition of causal stream function. And how can we do this? Well, you can do this in two ways. You can reason about this in two ways. You may prefer one or the other. One is to use coends. And if you use coends, then by an application of the universal property of the product, and then generate a lemma here, you will get this fixed point equation when then it solves to give you causal stream functions. But perhaps a better way of seeing this is every time you have something like this, and you have a Cartesian category, so a common common in every object, sorry, and it's natural and uniform, then you can split every function into this copy and just put one side of the function to one side and then pass the rest as memory. So this is to say that if I'm writing a monoidal stream and I'm keeping something in the memory, I could keep just all the input in the memory all the time. And that's what gives us causal stream functions. So the theorem here is monoidal streams in a Cartesian monoidal category recover causal stream functions with the usual definition. Right, but this is just recovering the cases that we had before. Let's try to do something more, right? So let's try to do something that is not necessarily Cartesian. I was promising to you at the beginning that we can do something with stochastic functions. And what happens in Markov categories is that if you have a Markov category with conditionals, you cannot do the factoring that you would do in a Cartesian category where you put the two projections, but you can do something similar. And you can factor into the first part and then a conditional that recovers everything from the input and the output to that first part. So you can use that to show that monoidal streams in stochastic functions are the same as some existing notion of control stochastic process. So this proof is not totally trivial. I'm trying to draw the main idea here with string diagrams, showing that you can write every string diagram like this into something like this is easy. But the problem is to prove that this is actually faithful and full, right? So everyone can be written like this, and if you write something like this is the same as writing that in that form, and that is not trivial. That uses some properties that are not true in every Markov category with conditionals. Right, so I'm saying to you that if we take class of the finitary distribution monad, so stochastic functions, or some toy model of stochastic functions, what we get back is control stochastic processes. So there is this notion on the literature of control stochastic process that is given by a family of stochastic functions that need to satisfy some causality condition. So the idea here is that we have some stochastic channel that takes some variables and then produces some joint distribution on other variables. We say that this has a causality property if the first variables in the output do not depend on the last one. And this independence condition, we express it by saying that this diagram commutes. So if we forget about the last input and then compute, that should be the same as computing and then forgetting about the last output. So this is to say the future should not influence the past, right? If we have x n plus 1, that should not influence all the previous outputs. So we put this condition and we do this definition of control stochastic process. We get that monoidal streams over the category stochastic functions over class D coincide with control stochastic process. So the usual definition that you're going to find of a stochastic process will be without the x's, but this seems a reasonable generalization because then you can do a monoidal category where you have inputs and they control the stochastic process. Right. So we have now shown to you that we have a construction of monoidal streams, that this is coinductive and we can reason coinductively on it. And then that we can get two examples. First, the usual monoidal streams and then the stochastic monoidal streams. So I'm going to jump a bit. So the last part of the work, this was only if I had a bit of time. So the last part of the work is to try to implement all of this, right? There are reasonable type theories for symmetric monoidal categories, and there are reasonable type theories for symmetric monoidal categories with feedback. So we can try to use them to get back the syntax that we had for data flow programming. So if you do this, you will find that this syntax for symmetric monoidal categories is actually implemented in some programming languages, and you can bring back all your syntax from data flow programming and interpret it directly. Right, so this is what we do in the final part of the paper, which is to give a type theory, to give a way of translating between programs of data flow programming, even if it's in a category that is not Cartesian, programs that actually compute in a language like Haskell. Right, and for this, we are going to use something that is called pre-monoidal categories. So the idea here is that most of what I'm talking about works for monoidal categories, but you can also extend that to pre-monoidal categories where you don't have the interchange law. And I think we are going to hear much more about this during this session, so I'm not going to enter into the details. But the idea is that you can still have a model of this and the implementation works for that one. So the implementation kind of motivated us to generalize a bit from monoidal categories to pre-monoidal categories. So interchange law is actually not necessary on all this construction. Right, so what's further work? So there are many things that we could do here. I want to comment on one of them, or two of them, I think. One that is very obvious is that when we did this generalization from causal stream to monoidal streams, we were losing a bit of the structure. As you see, when Katsumata and Sprunger define these causal stream functions, they give them a differential, a Cartesian differential Cartesian differential structure, right? But if we are trying to do the monoidal version, we should still be able to preserve some differential forward structure on these monoidal streams. Another thing that we would like to have is a comparison with the delay trace calculus from Carette, Devins, and Pedry, where they do something that looks very similar to the trace that we have, and the semantics are very similar. And the only thing that we vary is having this thing of the followed by. So this gate at the beginning would be the followed by as a derived or as a primitive notion. And there are many other works that I think you'll see during this conference that we would compare with, but I'm not going to enter into the details of this. So I think I can stop here. That's fine. Thank you very much.
Hi, thanks for the nice talk.
Thank you.
Could you say something about productivity? For example, in your diagrammatic language, are all the streams, is it guaranteed that these streams are always productive, or could you make ill-formed streams?
So,
how do you handle that?
So somehow this is not, it's not clear to me that corresponds to the usual notion of productivity. But when I was telling you here that we cannot do this Aramex theorem on every category, we need some property. The condition that we put there on these monoidal categories that allow us to do this construction is something like is what we are calling productivity of that monoidal category. And that says to us that we cannot have an infinite change of descending factorizations of a morphism that could mean that the first part of the string is not defined until you define all the rest of the string. Somehow that would be like the equivalent of productivity, which is a bit more subtle because now the string can depend on the future, and that's fine. The only thing that you want is that it's still well defined somehow with respect to the future. So there is some notion of productivity, which is not clear to me that it's exactly the same one as usual. But then all monoidal strings are going to have this productivity condition because you are just saying that they are pieces. They are not partial. They should just end and give you the first output after they give you the rest of the input. Thank you. Thank you for that question.
Yeah, thanks, man.
Thank you.
I have a question about when you went to the stochastic version.
Yeah.
There's this theorem that says that monoidal streams in the classical category of the Markov stochastic processes. And since you mentioned that that's a Markov category, do you know if in the proof of the theory you're just using the Markov category accent, or is it specific to that category?
I would love that the only thing that we were using was Markov categories with conditionals. At least conditionals seem to be, so it seems to be necessary because you need to do this factorization. So if I have only a Markov category, it doesn't seem like it will be enough. But even with that, you still need to have some technical property of the category where you say that if you factor these two things in that way, they are like kind of unique. You cannot ask for uniqueness of conditionals, of course, in a Markov category, but you need to still ask for something like, so in the category of stochastic processes, that is to say that every function will have something like a range. So a function that is subjective enough so that you can pass it back and forth and check equalities here. So this is a technical condition that is not necessarily true in every Markov category. So we cannot prove that in every Markov with conditionals, but at least it's very clear that if you want to prove something like this, it should be a Markov with conditionals, and then perhaps some technical infrastructure that seems to be necessary. So thank you for the question. That's very important, actually.
Cheers. Thanks.
Thank you.
Okay, I was wondering if you could go, there was a slide where you mentioned something about causality and then this causality condition implying that your process decomposes a string.
Right.
I'm not sure if I can see it. Yeah. Okay. So I'm wondering that there's a theorem in quantum supermaps, which are like the sphere of like black box operations that aren't necessarily time-routine. And there's a theorem that says, in specifically the quantum case, that supermaps which behave well with causality conditions between the slots always decompose as clones. So I guess my question is, you know, if it has anything to do with that, it's sort of
right.
So is it quite a structural theorem?
Right. So I cannot give you the mathematical details of this because they are not super clear to me, but I agree with you that there is a relation. The relation seems to be, so this causality is useful because you need to have this kind of productivity condition in monoidal categories. So we were given this productivity condition that you need to have to define these streams. And this causality seems to give you exactly like this. So now I'm going to go to a different work where they do a graphical calculus for quantum supermaps, and they ask some property for them so that this coincides. So it seems like the two properties, we use them in the same way, essentially. We are using them to prove that we can construct these monoidal streams or something similar. So it really seems that should be the same thing. But when you try to go to the definitions, it's not clear how do you translate between one of the two. So let's say that we have a property in stochastic maps, we have a property for quantum supermaps, and they seem to have like the same technical use, right? We use them both to construct these monoidal streams, but it's not clear to me that you can write one that is abstracts both or something like that. But it should be something like factoring. So it is something like factoring comms. But the idea would be what's the minimal thing that you can ask so that you can factor a comm or something like that. Does that answer the question somehow?
Yeah. I suspect it's something like you have signaling, but probably signaling.
So I think that so we would like to have a condition that implies that and is as minimal as possible somehow, if that makes sense. But I think that's the idea. Thank you very much for the question.
Okay, maybe one more.
Yeah, hello.
Hello.
I have a kind of a technical question. So do you use the connection between coends and colimits in your work related to Atomics theorem? And if yes, so usually I think this holds when the category in question is small. So here do you assume that your category C on the slide there is small, or does those work for locally small ones as well?
Right. So there are two parts, I think, to this answer. One is that yes, you will need to assume some condition of smallness somewhere if you want these coends to exist. But that's fine. That doesn't cause us many problems. What seems to be a problem, though, is that you were saying coends are colimits, but they are not discrete colimits, so they don't usually commute with limits. And when you're applying a Damex theorem, that can be a problem. So to relate this to the previous questions, they were asking me if this is related to productivity. You somehow need to add some condition that looks like productivity in order for this limit to commute with the coend. So the fact that coends are colimits but are not discrete is very important when you try to generalize submonoidal streams, and causes a bit of technical problems that then you can solve asking for something like productivity. I don't know if this makes sense. It's very, I'm waving because I don't have the details here, but the idea is that these coends being colimit, not discrete, needs you to ask a bit of extra structure in your category. If not, a Damex would not work. And that's independent from the size issues that you would have. This you can solve as you ask that everything is small or something like that, and that's fine. Or you work under some universe. Thank you.
Okay, let's find the speaker again.
Does it work? Okay.
Okay, the next speaker we'll talk about central submonads and notions of computation.
Okay, thank you. Okay, so on Monday, someone told me that everyone here likes monads, so I'm going to talk about monads a lot. So I hope it's true. And I'm going to talk about central submonads. Does it? I don't know. Oh, okay, maybe I need to. Is it? Okay, I don't know how to check.
Problem is down here. Just sorry, don't do that.
Yeah, but this is falling down anyway.
Okay. Is it? I don't feel like it's working. It is? Okay. Anyway, also I should check the time. Okay. So the idea is to consider, well, okay, I'll just, okay. So monads are algebraic structures like a monoid or a group. And for all these kind of algebraic structures, you have a definition of commutativity and also a definition of center. So for example, for any monoid, its center, noted Zm, is a commutative submonoid of the monoid M. And it consists of all the elements that commute with all the others in the monoid. And this definition also exists for subring and for a group. And our question here is, what about monads? And now, a category theorist would tell you, well, a monad is just a monoid in the category of endofunctors, so it's just going to work like any monoid. But this is not the case. To define a commutative monoid, we need, we put ourselves in a symmetric monoidal category, and we consider a strong monad. I'll define what this is a bit later. And our question here is there a commutative submonad of this monad T, which is its center? and what are the conditions for it to exist. And I also try to give you well, a feeling of what the computational interpretation would be. Some background. Well, as I said, for any monoid M, its center is defined as the elements which commute with all the others. And here you can realize that this definition already has an implicit swap on the arguments. So this is why you cannot really define well, a commutative monad without the monoidal structure, because in any category of endofunctors you don't have natural braiding. Okay, so we need a strong monad to define this commutativity. So here the strength is a natural transformation from well, the tensor product of any object and a monadic object, and it moves the monads on top of the monoidal products. And we also have the co-strength, which does the same thing but with the monoidal object on the left. And this kind of shows that well, it also has coherence properties, and this ensures that the monads interact well with the monoidal structure. And the definition of a commutative monad is the following: if you have a monoidal product of two monadic objects, it does not matter if you apply the strength and then the co-strength, or the co-strength and then the strength. So it does not matter if you pull the monad starting from the left or the right. Okay. Well, you've heard about premonoidal categories a bit before, but well, if you have a strong monad T, its Gleissig category does not have a monoidal structure. The structure is premonoidal, and this has been studied by Power and Robertson. And the premonoidal structure is monoidal if and only if the monad is commutative. And this has a lot of consequences for the computational interpretation as well. Our first definition of central submonads is on the category of sets, which makes things a lot easier and a lot more understandable at first. A first simple example, the writer monad, which is generated by a monoid, and which is the Cartesian product, well, it is the Cartesian product of the monoids and any object of the category. Its unit is only mapping to the pair of the units of the monoids and the element x. The multiplier is using the multiplication of the monoids, and the strength is only moving well, this monoid element well, outside of the pair. And the question is, what should be its center? As I introduced you the center of a monoid, you should feel like the center should be the monad generated by the center of the monoid. And this monad is actually a commutative submonad of the previous one. Well, so now we'll try to define properly the center of a monad, and well, hopefully we'll get this kind of result. Okay, so remember that a commutative monad respects this diagram, so it does not matter if you apply the strength or the co-strength at first. And now, what is the definition of a central submonad Z of the monad T? Well, what we do is that we consider all the monadic elements, so elements T in Tx, such that the diagram, such that this equality, which is the commutativity of the tau and tau prime, well, commutes. And so we're basically using the subset structure of sets. Okay, and this construction is very nice because this Z is actually a functor. It is actually a monad, and the units, the multiplication and the strength of the base monad T restricts and co-restrict to units multiplication and strength for the submonad for yes this new monad Z. And this submonad Z is a commutative monad, so it is exactly what we wanted, and it is a submonad of T. And we have more than this. Its Kleisli category, well, written like this, is actually equivalent to the premonoidal center of the Kleisli category of T. I'll introduce you to premonoidal centers a bit later. Some other examples of monads on sets. The continuation monad is apparently useful in computation. This one, well, involves functions of functions, and you compose function, and as you can guess, composing function does not really commute. So the center of this monad is only the image of the unit. And here we can observe that the image of the unit is always in the center. And this center is isomorphic to the identity monad, so the monad 1. And we say that its center is trivial. Another example, if T is commutative, its center is itself. And as we wanted earlier, and this is true, the center of the monad generated by a monoid M is the monad generated by the center of the monoid. Okay, so now I'm going to talk about general symmetric monoidal categories, and we'll try to define the center in this setting. Well, we saw that every monad on set is centralizable thanks to the subsets. What about any strong monads in other categories where you don't necessarily have a notion of subsets? For this, I'll introduce you the notion of central cone. A central cone is something that we've well introduced for this result. Is a pair of an object and a morphism. The codomain of the morphism is Tx, so monadic objects, and if you map well, if you map this morphism into the premises of the commutative diagram, it verifies the conditions for the monad to be commutative. So you're kind of saying that if you start from Z and then you apply iota, you get an object which verifies the commutative diagram. You're kind of thinking, well, you could think as Z as your previous subset and iota some kind of subobject. This notion of central cone is pretty nice because you can have morphisms of central cone. So this is a category. And we can consider terminal central cones. Okay. Now we can define what is centralizable monads. A strong monad T is centralizable if for any object X there exists a terminal central cone of T at X. And if it exists for any object, we're going to write them Zx and the inclusion morphism iota X. So now you could guess where we are going. This Zx is actually, well, we've proven that it is a commutative submonad of T, and this iota is a submonad monomorphism. Okay, and it is interesting to note that well, if you have a submonad monomorphism, you also have a canonical embedding from the Kleisli category of the submonads to the Kleisli category of the base monads. Okay, so now I've introduced you a definition of a centralizable monad and how we kind of construct it, how we construct the center of monads. And we can also link this to results on classic categories and premonoidal categories. So as I said earlier, if T is a strong monad, its classic category does not necessarily have a monoidal structure. It is a premonoidal category, so, which means that there are two families of functors which do not commute in general. So you have the left tensor products and the right tensor product. But it does not commute, but you can still consider morphisms for which this commutes. So the Power and Robinson defined central morphisms. Those are morphisms F in the classic category of T. And they say they are central if for any other morphism that you're going to apply on the right, it does not matter if you apply F at first or F second. And it is important to notice that central cones, as we introduced earlier, and central morphism are actually equivalent notions. So I'm going to merge them somehow. You have to know that central cones, we've written them into the base category, and central morphisms are written in the classic category. So it's a bit dangerous to manipulate them those names in the same category. Okay. Now we can consider the premonoidal center, so Z of CT, the white subcategory. So you keep all the objects of CT, but now you consider only the central morphisms. And this category is symmetric monoidal because now you have all those morphisms that make the two tensor products commute. And we've proven that if a strong monad T is centralizable, as we've defined with central cones, then the canonical embedding from the classic category of Z to the classic category of T co-restricts to an isomorphism between the classic category of Z and the premonoidal center of the classic category of T. So there is literally a one-to-one correspondence between the premonoidal center of the classic category of T and the center of our classic category. This is why we were very confident in calling Z the central submonad of T. We also link this notion to adjunctions. Well, you know that okay, there is an adjunction between the base category and the classic category of T because it's a monad. And actually, the left adjoint J co-restricts to a functor with codomain the premonoidal center of the classic category of T. And we've proven that if T is centralizable, then this co-restriction is also a left adjoint, and it induces exactly our central submonad. Okay, so now we have this characterization. So three equivalent notions to define centralizability for a monad. So either you have terminal central cones at any object, either your canonical embedding is an isomorphism, or the restriction of the left adjoint is also a left adjoint. All those conditions ensure that your monad is centralizable. Okay, using this theorem, we can prove that any monads on any strong monad, on sets, DCPO, measurable spaces, topological spaces, Hilbert spaces, vector spaces, is centralizable. We've also proven that in a symmetric monoidal closed setting, and if the category is total, then every strong monad is centralizable. And of course, in any category, if a monad is commutative, then its center is itself. Now the question is, is every strong monad centralizable? Because it feels like it works well. Well, no, because you can build well, full subcategory of sets, but where you don't have all subsets. So you're basically building something where you don't have the subset that you want, and there you don't have a central submonad. Okay, some interesting monads. There's the evaluation monad, which is used a lot in probabilistic programming. Well, it is an open problem if the monad is commutative or not. So the trick is to use the central submonad, which is not trivial. So it's interesting. And also still probabilistic, the Geoff on measurable spaces is not commutative and does not have a trivial center. So it is interesting to use it. How much time do I have left? Okay. Yeah, okay, I'm going to finish. Okay, so I'm going through the computational interpretation very quickly. So strong monads are used to denotate, well, effects in programming languages. For example, non-determinism. And if you have one of those two operations, which is a central operation, so it is denoted by a central monad, then you can swap them. So this notion of central operation is useful in rewriting rewriting lines of your codes. Okay. Well, a few words to conclude. There is related work done by Rory on algebraic theories or commutants in algebraic theories, and this is something that we'd like to understand a bit better. Thank you.
Are there any questions?
Thank you. Very good talk. First of all, for the Geoff monad that's community, I guess you don't refer to the Cartesian product of measurable space, right? But has to be some other monadic product.
Okay, I must admit I don't know much about these things. This is the Geoff monad was an example introduced by my co-authors.
Oh, okay. And another thing, if our category is not monadic closed, just monoidal,
yeah,
can we still write the centralization as an equalizer, or is it more complicated?
What do you mean, the cone?
The terminal cone, yeah.
Well, sorry. I don't think you need to be close to have this. You can probably have terminal central cones without closure.
No, I know, but I guess in that case it's not just an equalizer, or can one still do that?
I don't know. It might be dangerous to see it as an equalizer. Okay.
Hi. Is there an analogous theory for all this with comonads?
I don't know. This is a good question. No, we might try actually. But is there also a definition for commutativity of a comonad?
I don't know.
Okay. Okay. So well, that's something to try. Yes.
Cool. Thanks.
Emo?
If I inform everything, you can also have a premonoidal category that is a classic category for monads, but the center is not the classic category.
The which classic category?
Like the counterexample that we gave before.
Ah.
Gives you a premonoidal category that is the class view of a strong monad, right?
Yeah.
But the center is not the class view.
Yeah, then the center is not well, yeah, it's not any classic category. Yeah. Okay.
Okay, let's thank the speaker again.
Thanks. Can you hear me like this? Thank you, Mateo.
Okay. Okay, so the final talk will be again Mario Román. We will now talk about diagrams for effectful clusters.
Thank you. Thank you very much. And thank you also to Luis for this talk, because it simplifies a lot many of the things that I wanted to talk to you about. So it's a luxury to have someone that explains this very clearly before you go. So as you're seeing, this session is trying to convince you that premonoidal categories are nice and useful. So I'm going to continue this trend by trying to introduce you to a notion of string diagrams for effectful and premonoidal categories. So the ideas that followed, you have already seen the definition of premonoidal category. And this is a definition that is usually done in 2 steps. And now we see why you need these 2 steps. First, you define something that's called a binoidal category, Power and Robinson. And they have a category that has something that is not a functor, not a tensor functor, but only a sesquic functor, meaning that it is independently functorial on each component. So you can compute F tensor with identity, the identity tensor with G, but you can never tensor F with G directly. And these 2 things are not generally equivalent. So F with identity G is not the same as identity G, F with identity. We say that a morphism is central when it satisfies that for any other G. So why do we need to do this definition in 2 steps? Is that we want to have centrality in any binoidal category, and then define a premonoidal category, which is the definition we were going after, as a binoidal category where you have natural and central isomorphisms that do the coherence isomorphism of a monoidal category, satisfy the same axioms, and then we say that it is strict if these are identities. So we repeat the same story that we do for monoidal categories, but we need to do this in 2 steps because we want the coherence morphisms to be central. Right, so that means that we have something like string diagrams of premonoidal categories, right? Because premonoidal categories, I was giving you this definition, but you can also see them as just monoidal categories without the interchange law. So everything is going to work the same, but you're not going to have the interchange law. So why would you like to not use the interchange law that we all love? The idea is that you may have some processes that are sharing some global state. So imagine that you have multiple processes writing to the same shared board or a server or something like that. Well, the order in which you write there matters. And if we don't want these 2 things to be the same, the one on the left and the right, then we need somehow to restrict the interchange law that is making them equal. This example is the free algebra of strong monad, precisely the monad over the monoid that takes the alphabet, for instance. And it's an example of why you may not always want the interchange law in monoidal categories. Right, but this is already giving you some notion of premonoidal string diagrams. Just draw your usual diagrams and keep track of where things interchange or not, and be really careful of not interchanging anything that you should not. However, it is not true that you cannot interchange anything or you cannot compose anything. There will be these morphisms that were central. So we were precisely seeing a talk about centrality of some morphisms, right? There will be some of them that are central, and then you can tensor them together. You can compose them with others. You can do most of what you usually do in a monoidal category. So for this, and for another technical consideration, which is that there is not a good notion of a premonoidal functor, we do premonoidal categories, but we usually choose a center. So we are going to pick not only a premonoidal category, but also a center of that premonoidal category. So some central morphism, some distinguished class of central morphisms forming a subcategory of this premonoidal category. So this is the motivation for phrase categories, which are usually Cartesian or Cartesian based. I'm going to work in a slightly more general context because I'm not going to assume that the base is Cartesian. So this will be non-Cartesian, not necessarily Cartesian phrase categories, which I shorten to effectful categories. And the idea is that we are going to have an identity in objects functor that goes from a symmetric monoidal category that represents the values or the pure computations, the things that are central and commute, and we have picked to be central, to a symmetric pre-monoidal category, which are the computations and that do not need to actually satisfy the interchange law. So this gives us an improvement over the previous diagrams here. We can choose some morphisms that I'm coloring here as red to be the non-central ones, and some of them to be central. The central one we can tensor together, we can interchange. The non-central ones we should not be able to interchange. Right, so this seems already a better notion of string diagrams, and we need these two colors here. But these diagrams have a problem. I think it's a subtle but important problem. That is that we don't have locality of transformation of string diagrams. And what I mean by that is that I expect that when you're manipulating string diagrams, if you zoom in into some section of your string diagram and apply some equalities, and then you zoom out, that should be a valid transformation, right? But here, because of these failures of interchange, we could have that you have two morphisms. One is like an inverse, one side inverse to the other. And then you are dealing with another string diagram where these two appear together. You are very tempted to simplify them, but you cannot because there is an edge in between these two. And so you could not only think about this part of this diagram when you simplify. You need to keep track of everything that happened around you. I think that's bad. And it seems that we almost never use pre-monoidal categories in string diagrams. So it seems at least that we are not very convinced that these diagrams are a good thing. At least you need to be keeping track of pre-monoidality all the time. But what if I tell you that there was a solution and it was there since the 90s? So actually it was 3 years old when this solution was proposed. So the idea is just add an extra wire. It looks very simple when you think of it because it solves all the problems that we were talking about. The idea, the conceptual idea, is that we were saying that these are morphisms that share some notion of global state or something like that. Well, if monoidal categories are like theories of resources and we put resources onto the wires and then processes take them, you would like to have a resource that is the central, that is the runtime, that is the ability of execute something, is this global state. We are just making it very explicit by adding an extra wire that is formal and represents this. This has two nice properties. The first one is that doesn't allow interchange anymore because these are morphisms that will share one wire, this runtime, so they cannot interchange. But also it solves the problem of locality. These two things were not really local because they depended on an edge that was in between them. And by writing a wire, we are writing explicitly that dependency. So this is a passing comment on a paper by Jeffrey on the 97. And even if it is a passing comment, it's very interesting because it seems to solve this problem of diagram. So what I'm doing today is trying to convince you that this can be promoted to a theorem that says what we reasonably expect that this should be. Right, so I do a recap of the situation now. We had an idea to do pre-monoidal and effectful string diagrams. So these are going to be effectful because I can have my blue thing. And this idea is very good because it not only works with pre-monoidals, but also with effectful categories. If I have some class of central morphisms, well, these are the morphisms that do not affect the global state. So I'm not going to put the runtime wire, the red wire, as an input and an output of those. So these can still interchange. The blue ones will interchange freely, and the red ones will have a wire that is preventing the interchange between them. So this solution is not only good for pre-monoidal categories, it also works if you want to pick a center and work with that center. And this notion going from pre-monoidal to effectful doesn't lose too much because actually if you take a pre-monoidal category, you could always pick the center of the pre-monoidal category as we were defined before, and that you pick that as your center. You could always pick all the center. The only thing this is giving you is the ability to choose a center for yourself. Right. So, okay, all of this is very nice. It gets some structure of programs, which was the motivation of Jeffrey. So I should say that the motivation in the paper by Jeffrey is to try to capture with string diagram the structure of imperative programs. So programs where computations are not necessarily pure. And this is something that they do there. But I still need to convince you that you may want to still use these diagrams with runtime. Because if you try to do diagrams, you could perhaps well, but I still want to use the pre-monoidal ones where I don't have I just keep track of the interchange by myself. So I'm going to argue that sometimes many structures become much more obvious when you have the runtime going around. So imagine I want to axiomatize something like the state monad, and I have some premonadal category where I have a series of rules with this get, put, and so on. Let's say that if I get something from the state and I get it again, well, the state hasn't changed, so I could have copied that one. If I put twice onto the state, every update erases the previous one, so it will be like discarding the previous one. And you have some like put get law that says if you are going to put something and then retrieve it, then you could keep it with you and just use that one. I'm going to argue that if you put the runtime though, it becomes obvious. This is you can say it in a sentence. So this is a semi-Frobenius action of a semi-monoid and a comonoid, the satisfying of Frobenius equation. So my point is some structures seem to become relevant also once you add the runtime, even if you're saying premonadal categories. So I take that as an argument of why would you care about the runtime when you're doing applied category theory. Right. But I'm basically selling you the paper by Lamjeffrey. What are the contributions that I'm doing here? The first one is to promote this into a theorem. And the theorem says something like the free effectful category in some generators is going to be the monoidal category over the same generators, but now with runtime. So this is a statement that says what I was intuitively saying to you as we just put this extra wire. And then the second theorem of the paper is to try to show why effectful categories you could consider them as fundamental structures somehow. Because in the same sense that you say that monoidal categories are pseudomonoids on a monoidal bicategory of categories, you can still say that effectful categories are pseudomonoids on a monoidal bicategory of something that are identity on objects arrows, identity on objects functors, which are sometimes called arrows in functional programming. So the idea is if this is something that if you give me a category, I can give you an identity on object functor that embeds it into a bigger category with effects. So this would be like the direction of adding effects, and this is the direction of taking pseudomonoids. So somehow monoidal categories are two categories, so the effectful categories are going to be to this identity on objects functors. Right, but I think I'm going to present basically the first result. I'll leave slides with the second one if you want to go further into that. Okay, so let's normalize this runtime on the paper by Jeffrey. So I recap. The idea was that we are going to avoid the interchange in premonoidal categories by adding an extra wire, which we conceptualize as the runtime or like the global state. And how are we going to do this is to show that the morphisms of the free effectful category or a signature, and I need to tell you what I mean by signature there, are going to be morphisms taking and giving this runtime extra object on a monoidal category with some generators. So this is the theorem that we are going to present in the paper. How do we do something like this? Because this seems like a technical theorem. The idea first is that we need to have some notion of what it means to have a signature for an effectful category. So you know how this works for monoidal categories. If I give you some signature for a monoidal category, I'm giving you a polygraph with some objects. And then I give you some edges that represent some generators for your monoidal category. And then you have an adjunction that is constructing the string diagrams over a polygraph into the strict monoidal category, the freely generated strict monoidal category on top of that signature. And then you can always forget a strict monoidal category into its underlying polygraph. And that gives you an adjunction. So let's do exactly the same thing, but now for effectful categories. And for this, I'm going to have two graphs that share the objects. So it's a pair of graphs, but they need to share the objects. And what I'm really saying is that I'm going to have my generators that I'm going to give them two colors. So that ones I know that are just commuting, the other ones are not. So this is the signature that we use now. And now we can still construct string diagrams with runtime. This is the construction we're going to present and recover an adjunction like that one. Where the forgetful functor would put, so if these are two categories, one with an identity on object functor into the other, each one of them generates one of the polygraphs. Right, so this was the adjunction for monoidal categories. We're going to do exactly the same for effectful categories. So how do we do that? We put exactly the string diagrams generated by the usual morphisms, but some of them taking runtime. And then we need to ask that the runtime can move freely around the monoidal category. Because you see, I was not asking that anything here needs to be symmetric in principle. So the runtime needs to still be able to swap, but the rest of the morphisms, like the rest of the wires, won't need to swap between them. So somehow we are asking the runtime to be on the differential center. We are asking it to be able to swap around all the wires. And then we have some equations that it should preserve. which say basically that this is really a swap of wires. Now we are going to prove that the diagrams with this shape are the ones giving you the free effectful category. And there is still a technical thing that we need to do. That is, well, the objects would not be the ones that we want if we just put a runtime and we'll let it live wherever we want. We need to be a bit more precise and take as objects the clicks with the runtime. And this is just a complicated way of saying, I don't care where the runtime is. It could be at the left, and you could just choose that, but I don't really care where you put it. So a similar technique is used when you try to prove monoidal coherence. So you put a clique of coherence isomorphisms, and then you take morphisms between them. So our category is going to be clicks of this runtime. So we don't care where the runtime is. And then a morphism of clicks is just a morphism from every component of the click to every other one, such that it commutes with isomorphism. And the interesting thing here is that you give me any of these arrows, all the rest of the arrows are just generated by isomorphisms on them. So I can pick whichever two things here, and there is a unique way of going from one to the other on the diagram, and they correspond to the different string diagrams that we could put changing the runtime. So all these diagrams should be really the same. It's just I'm moving the runtime. Right, that makes sense. So after you do this, you construct the category, and you show that the assignment is the only assignment that preserves all the structure and that doesn't do anything weird with the swaps, because they should be the identity, is that one. And that gives you the string diagrams that give you the free strict effectful category of a polygraph couple. So this is the adjunction that we are constructing. This is the construction that we are using, which seems reasonable. Right, so how much time do I have? Okay. Okay, so this was to justify string diagrams for monoidal categories, for effectful categories, sorry. So I still wanted to justify to you why effectful categories are interesting, and I'm not going to go into these details, so I'm going to go really fast, and I'm sorry if I leave many things. But the idea is that if you think that profunctors are interesting, and you treat them as bimodules, there is a notion that you should consider also important. And the notion is the following one. You take your double category of categories, functors, profunctors, that has the calculus of cells, or the dual one that Myers uses. They compose by coends, and the identity is the home profunctor. Now, in the same sense that you consider monads to be interesting because they are the monoids of the double category of the bicategory of categories and functors, then you could consider also promonads. So if ones are the monoids in one direction in the double category, ones are the promonoids going in the other direction. And if you have heard about monads, it's not always true that you have heard talking about promonads. And the problem here is that promonads are usually identity on objects functors. So I think because of that result, you can characterize them as identity on objects functors. We usually don't give them as much importance as monads. They seem not that interesting. They are just identity on objects functors. So they are just functors to another category. So an example of this, if you have your monad that induces a promonad, which is the Kleisli category, embedding the C, your category, into the Kleisli category. But now you have the double category structure. There are some notions that you want to study. One is the notion of nomomorphism of promonoids. And that is giving you, when you translate to promonad, a commuting square of functions. So that makes sense with that interpretation. And then there is the notion of a promonoid transformation, which you can write, at least feels very natural if you write it in a double category. And that gives you this cylinder transformation between two commutative squares. So there is a good correspondence on why promonads are interesting and the structure of identity and objects functors. So you can give, the claim here is, you can give a monoidal bicategory structure on these things such that the pseudomonoids for that monoidal bicategory structure are precisely the effectful categories. If I define this like with this, the thing I'm saying is that I will have some commutativity conditions between morphisms, but I think the way of presenting this, also after I introduce you to runtime, is to say that this tensor of promonads is doing something like this. I'm going to have one promonad on the left, one on the right. They are not monoidal, and then they are going to share some wire that prevents them from interchange. So if I put some effect on one of the promonads and one effect on the other promonad, these two should not interchange. But if we have some morphisms from the base categories, the pure ones, they do interchange. So the claim here is these commutativity restrictions to define this tensor are very well encoded by string diagrams with an extra wire, as we were doing before. And so the result is in the same way that you have pseudomonoids, and they are two-dimensional monoids, so monoidal categories are pseudomonoids, and monoidal category of categories. Then effectful categories are the same thing, just in the monoidal bicategory of promonads with this pure tensor that I was introducing here. So I think that's all. The idea here would be, so these results are small, but the idea would be like if people are already using premonoidal categories in programming languages, I think it would be nice to try to also bring them to applied category theory, because we have now, we had always good string diagrams for them. And we can translate between imperative programs and string diagrams in this way. The translation can be made formal. I'm not going to talk about that. Thank you. Thank you very much. This is the paper of the content.
Thanks. Good talk. Could you go back to that slide with the lens laws?
Yeah.
Yeah. So I just wanted to hear the statement again. So like, if you add these string diagrams with effects, then the lens laws become the special Frobenius structure or something.
Right. At least you can make it compact in this way, right? It would be like semi-Frobenius because I don't have a unit for the monoid, and I don't have the unit of the monoid for a very good reason, right? This is the monoid that you can define, the semi-monoid that you can define in a Cartesian by discarding one. So we really don't have a unit for that. But apart from that, you have still something like the Frobenius equation, right? Which this is, of course, this is arguably like you may prefer also that. But my point is sometimes having the runtime makes these things more obvious.
It's close at least.
Yeah.
Right.
Thank you.
I was just curious, is there any connection between this and the negative information categories that we talked about yesterday?
I do not know. I do not know yet. I guess there is some way of, so they were using enrichment and they were using something like dual to profunctors. And instead of having the and, you have an or, right? And that, if you have, so the thing is, instead of having a composition with profunctors, right, which is what a promonad gives you. So if you have A to B and B to C, then you have the A to C. They are doing something like the dual to this, right? So you do something like you don't have an A to C if you don't, so if you don't have an A to C, then you don't have either an A to B or a B to C, right?
Yeah, I think that was one.
So I think, I guess there could be a connection, perhaps if I enrich in the category that is proposed there. I don't know yet. I cannot have a look at that. But thank you for the question. That makes sense. I don't know what to say right now.
Okay,
thank you.
So there's this paper by Baez and some of his co-authors who are in the room probably, which I don't remember exactly which ones, where they talk about petrinets with catalysts.
Okay.
So as being just examples of premonoidal categories. But they also hint at if you have multiple catalysts. So in this sense, it would be like you have multiple different colors,
Sometimes.
red wires.
Yeah.
That are like, what is the semantics for this? Do you think that this kind of formalization of this result of Jeffrey could potentially be generalized to multiple wires that are currently
Right. Thank you for this, because I was thinking like, so let's take it very seriously now, and we put one runtime. Why cannot put like multiple runtimes and see what that means or what that does? And the problem that I had with this is that I was not finding. So I had some examples, but they feel a bit like forced, right? So if the petrinets with catalyst paper is doing something that we can use in this way, I would be really happy. I didn't know about this. Thank you, Cole. Thank you so much.
Hi, Mario. Thanks for your talk.
Thank you.
We were talking there at the end about monads or promonads rather being these identical objects after when you look at the morphisms and so on. I guess a suggestion I could offer you is that you could also look at the monad retromorphisms and get something like right.
Right, and I could do that in the promonoids of a double category, right?
Yeah.
And what is that? Do we get cofunctors there?
I think if you treat your identical objects functors as something
Yeah.
bundle, then you get something amorphous that's kind of like a polynomial.
like morphism.
Oh, that would be really cool.
Yeah, it's nice to look at that.
Thank you. So to add something to that, I was looking at the beginning to do this category in a different way so that we have like retro cells. Because I was expecting that if you want to have sesquifunctors, the thing you may want is to have cofunctors instead of functors there. But some things were not working as nicely. They working here, so I forgot about that. But now that you say it, perhaps I can study. Yeah, makes sense. I would like to talk a bit more about that later. Thank you, Vlad.
Any more? Okay, then let's thank the speaker again. It's lunchtime, I think.
Ah. Oh yeah. Well, someone knows what they're doing can come and do it. Right. Okay. Right. Hello. Okay. So today, yeah, we're going to be talking about fully abstract categorical semantics for digital circuits. This is joint work with David Springer, who, well, with much of this would not have happened, and my supervisor, Dan Geeker. So, well, what do I mean by fully abstract semantics for circuits? So what does that mean? Well, hopefully by the end of this, you'll know, and I'll explain it well enough. So why do we care? So digital circuits, they're everywhere. We're using them in all of our devices, our cars, computers, whatever. And obviously, if we're using circuits a lot, we want to be able to reason with them well. We want to be able to sort of verify they're correct. We want to see when the two circuits are the same and things like that. So we need good ways to reason with them. And normally this is done by simulation. You sort of make an automaton or something, and you just run it, simulate it, see what the outputs are. But in software, we do things a little bit differently. We have this more sort of reduction-based method of evaluation, like this, but the lambda calculus. You sort of do some reductions, you put a value into a function and see what happens. And we get eventually to our answer. And we want something like this for digital circuits as well. We want to have this way of finding these red X's in circuits that we can then reduce and get circuits to a value. So the first thing we want to do is obviously specify the syntax of our circuits. How do we build them up? So first of all, we want to have things like values. So obviously you would want something for a true and a false, and you might think, oh, that must be enough. But we're going to go a little bit further. We have these special values, this sort of black circles, like a disconnected wire, and then this sort of short circuit one at the end, which is sort of disconnected, is no information. The short circuit is sort of too much information. And if you're familiar with Belknap's four value logic, this is where that has come from. And what else might we need? We need some logic gates, and or and not gates. And then finally, to make our circuits a little bit more interesting than just sort of connecting things in a line, we want our classic sort of identity and symmetries, something for fork wires, something to join wires together, and something just to discard wires when we want. And for our sort of notation, we have stuff on these blue backgrounds. This is just, we have the gates in the structure. These are like just combinational circuits that act like functions. So this is fine. We can build lots of nice things to this. You can build all the full adders and half adders you want. But to make circuits actually useful, you need to add something a bit more to them. You need to add a notion of delay. So you have sort of, the stuff doesn't happen straight away. You want to delay circuits inputs to the next tick or something. And also we need to have feedback. And crucially, this isn't the kind of delayed feedback that we had in Mario's talk. This is just feedback that happens straight away, in the instant, as it were. I mean, then you could combine it with the delay to make a delayed feedback. And then this green color is basically all these complicated circuits, these sequential circuits where have delay or feedback in them. And then we can build circuits just as morphisms in a freely generated symmetric trace monoidal category, like something like this, so where the trace is just this feedback. So that's fine. We have nice circuits we've built up and they look really pretty in all the colors, but currently they don't do anything. They're just syntactic. So we need to first of all say, what are the semantics of our circuits? So we interpret the values in this lattice. So we start with this undefined value at the bottom. We have in the middle just our sort of true and false values of 0 and 1. And then the short circuit is at the top of this lattice. It's all the information at once. It's over-specified. And then with this, we can then also define things for like the gates are just monotone functions where they preserve the ordering, the lattice, the copies. The join is then the join in the lattice. So if you think of try and join a true and a false together into one wire, that's going to cause this short circuit at the top. And the discard is obviously just discarding the input. So this is sort of the semantics of these combinational components, these sort of things that happen every time you give some inputs, they'll give the same thing. But to give semantics for things with delay, we need to go one level sort of deeper. We need to use stream functions, which again have helpfully already been implemented, introduced for me. So we have a stream, it's just an infinite sequence of values over time. And a stream function just takes a stream as an input and then outputs a stream as an input, which again makes sense because you give a load of stuff into a circuit and it produces some values over time. And so stream functions are the semantics of digital circuits, but not all stream functions. So first of all, we have to, only use causal stream functions because a circuit can't depend on inputs it hasn't received yet. We can only look in the past. They also have to be monotone because all of the components in our circuits are these monotone gates. So the stream function in question has to also be monotone and respect this order of the lattice. And finally, which is maybe something a little bit more subtle, is that these stream functions, although they are sort of infinite, they are streams, there's only a sort of a finite amount of behavior they can sort of specify. Eventually, you're going to get back to some state you've reached before. And this is because circuits are constructed from finite components, so you can't define infinite kind of behaviors. And then we have this theorem that, every one of these stream functions with these properties, this corresponds to like some amount of circuits. Obviously, you can have multiple circuits that all do the same behavior, but you can't make a stream function like this that does not correspond to a circuit. That's quite nice. And we can just use the streams as semantics for circuits. But that's all right. We're fine. We could try and find out if two circuits are equal by sort of comparing their streams. So something like this for these two, so a classic sort of De Morgan type thing. We could negate the outputs of an AND, or we could negate the input to an OR. And these are the same. And we could test this by just looking at their stream functions and seeing are they the same stream function. And this, it would be very easy because there's no delay or anything. We just sort of have to do it. But in general, this is a pain because if you have lots of delays, you have to sort of test inputs of very long lengths, and it's very hard. It's basically exponential at the end. And yeah, it's just not cool, not fun. So alternatively, we would like to reason equationally. If we have these diagrams, why don't we sort of rewrite them into things that also do the same thing, but are simpler? So the first goal we have here is that we want to say, if we have a circuit, say a circuit like this F here, it's a closed circuit, we've sort of capped it all its inputs with some values. We want to be able to get sort of one value that is what's happening now, and then behind a delay, another circuit, which is everything that happens later. And this is basically corresponding to running the circuit for one tick and finding what its output is. So this is sort of a goal for all the equations we want. So, well, what are these equations? I'm going to show you. So first thing, well, if you have a gate and you want to apply it to some values, then, well, you just sort of apply that function. Very simple. The join, again, you'd have two things joined together. We can just replace this with the join of the lattice. Then we have this, which may be very familiar to people. So we're in a Cartesian setting because we can just copy and delete at will. So if we have a copy, we can just push something over it. It's natural. And the same with a discard. We just sort of push it back in. I mean, just discard big circuits. And finally, we have to sort of take into account that the join and the fork are sort of the monoids and comonoids. So we can just apply the unit whenever we want and make sort of new bits. So these equations, all these here, if we have a combinational circuit, so remember this is just gates and structures, we can reduce it down to some value with just these equations. And in fact, we probably don't even need the bottom ones, but they're on this slide because they're used later. So that's good. So we have combinational circuits, they can become values. Fantastic. But what about if we have delays and stuff? But first of all, we have this sort of delay generator. Well, if it's disconnected and then delayed, then that doesn't really mean anything, right? We can just say it's always been disconnected. We can just sort of push it across. And then finally, this one's maybe a little bit less obvious. So what's going on here? So what's happening is we have just the gates, and we have its inputs have an instantaneous component, this value, over there, and they also have a delayed component, this delay here. And we want to sort of process this. We want to say that the gates, we test it with the V, and we also have one for what's coming later. So we can copy the gate, and we have one copy for the now, which the V is applied to, and we have one copy for the later. This is sort of cool. We call this streaming. You sort of stream the waveform over the gate. So we've nearly got everything to deal with circuit so far, but there's one last thing we've got to think about. So remember how I said that this feedback is this like instant feedback. This isn't delayed feedback. So how would we deal with something like this? What does this even reduce to? Yeah, at the moment we can't do anything. We never find out what the first input to this AND gate is. So we need to somehow get rid of this and replace it with something nicer, something maybe with no feedback loop at all. So how are we going to do this? What are we going to do? So our gates are all monotonic. We specified that they're monotonic. So they have a least fixed point. We can keep applying stuff, and eventually we'll find this fixed point. And because our value set is finite, we can always find this fixed point by doing some iterations, some finite number of iterations. So in our example, we have this 4-element lattice, and we've got length of chain is 2. So all we need to do is just sort of copy the circuit, 3 times we want to get just to the end. And this is the same as this. We have a circuit which has this instant feedback loop. We can actually just replace it with 3 copies. If we sort of start the feedback with this disconnected wire, you're saying copy the circuit, 3 times, I guess. And then this is the same. This is finding this fixed point. And this is good because it means that anything with this instant feedback, we can just replace it with a sequence of combinational circuits, which, as we know, are really easy to deal with. So have we got enough? Well, let's find out. So what did we want? We wanted to say if we had closed circuits, we could reduce it to this form here, where we have this instant value and some delayed bit afterwards. So let's try and work it out. So what do we do first? Well, first of all, we can, using the axioms of trace categories, just pull out all the feedback and the delays to sort of a big global loop. This is just pulling stuff out, moving around wires and boxes. And then, well, first of all, we want to get rid of this instant feedback. This is what was causing us a big problem. And we know that we can just replace it with some other combinational circuit, and sort of F tilde here. And now we have a circuit which all the feedback is just delay guarded, which is much nicer, much more friendly to work with. And then now this is just me making it a bit bigger because things are going to get crazy. And then, well, what are we going to do next? We have to be a little bit clever here. And using these unitality equations we said earlier, we want to make something that has these sort of forks. And why are we doing this? Well, because we want to be able to push these circuits around. We want to get one which isn't even guarded by this delay feedback loop, because that's also a little bit annoying to work with. And then we can also push the delays across as well, because they're just another circuit. Okay, so now what? So drag this one over here, and now we're going to think about this one in particular. And then finally, we have a fork here for these values. So, we're going to tidy up more, and then we're going to copy these values. Okay, so we're getting to a sort of state here where it looks a little bit like this axiom I showed before, this streaming one. We have stuff coming in with instant components and stuff coming in with delayed components. But we're not quite there yet, because on the bottom input, we have everything coming in straight away. And on the top one, this is all delayed. But that's fine, because we can just use this sort of unitality axiom to add in these bits, and then use the one to get the delay in. So now we have each input has an instant bit, this one, and a delayed bit. And there. So now we can just do the streaming one. Whoop. We have 2 copies. And if you remember rightly, if we have this combinational thing, we can always reduce this to a value just by propagating the values across all the gates. So it goes down to W. And then, well, we are done now, right? We have this instant bit, and then everything here is all guarded by a delay. So we just sort of tidy this up into one more box, and we've got what we wanted. We've got to this productive state where we have this instant W and another circuit G. And then we can just sort of keep applying this and get the elements of the output stream. Yeah, that's what I just said. The end of the stream. Okay, so that's already pretty cool. So if we have a closed circuit, we can always get the value. And that's quite a common sort of application, because you want to see what a circuit does, give it some inputs. But for seeing we have every equation we need to sort of characterize circuits, we're not quite there, because we have to consider open circuits as well. So we have something like this, where, well, this is just sort of, again, we've used this sort of De Morgan kind of equivalence here. These are the same, but we can't do anything about them because we have these sort of dangling inputs, and we can't use, okay, and we can't reduce them quite yet. So when do they have the same stream? Well, we can think of circuits as sort of state machines. Again, we go back to this idea that we can get them to a state with only the delay guided feedback. And we can think of sort of, this is sort of the logic of the circuit, and they have a state here, which is sort of defined by this value, which is the initial state, and this sort of delay, which will hold all the next states as they come around. Yeah, this sort of circuit here sort of produces the next state and the output. So all the idea is that if we could find all the possible states that this circuit has, remember, there can only be a finite number of states because there are a finite number of components in the circuit. All we need to do is just sort of check for each possible set of states, do we make the same next state? Do we make the same output? And yes, this is a bit like a Mealy machine by simulation, if you're aware of that. So then we get to our final thing, and I can finally say what full abstraction actually means, is that basically, yeah, we have two circuits which are equal syntactically in the equational theory. And this happens if and only if their streams are equal. There's a correspondence between the denotational side of the stream functions and the sort of more operational side of the equations. And the proof of this is, well, pretty simple now, because we just say we have two circuits, we can get them into this sort of global delay form, and then using this new sort of idea, we're just testing the bisimilar states. Then we just say, oh, this is equal. So there we go. So we presented a categorical, it's all gone, it's gone fast. We presented a categorical framework for sequential circuits. And so these have semantics as stream functions, but actually it's much more easy to reason equationally, and it looks much prettier on the page. And we've actually now got enough equations to guarantee this full abstraction result. We have syntactic domain where we can do our rewrites, or we have the semantic realm where we sort of test the equality of streams. Yeah, so I guess the next step is just to refine sort of rewriting systems. So everything has been presented so far as equations. They're not really directed. There's no strategy. And what Dan has done before is that he did define the sort of operational semantics, these graphs and stuff. And we just need to refine that with these new equations and make sure it all still works, which hopefully it should. And yeah, that is it. Thank you.
Do we have any questions?
Thank you. Very nice talk. I just wanted to double check something. So for the equational reasoning, like, okay, so you've got this trace operator. You don't need to assume uniqueness of fixed points anyway. You just need to assume that you have a trace, right?
Yeah. Just...
And you can get complete as well. Okay, super.
Yeah.
I have a question. Is there an extension of this to values that are maybe continuous or other sort of things you can set as V? Maybe it could represent current instead of just logic or something.
Well, I think because what's important here is that it's a finite amount of values. That's very important for this calculating this fixed point sort of thing.
Feedback loops get out of control.
Yeah. Yes, I think for this we need to be finite for this instant feedback thing.
Is there any reason why you couldn't model circuits as being compact closed, or is there some sort of physical reason why you can only trace things? And if not, do you extend this to having duals?
Well, one thing is the idea is that with digital circuits, everything is always going from left to right. You can't pipe an output back into an output because that just wouldn't do anything. So this trace gives us this sort of left-rightness of it. I think also because we have products, things go wrong, I think, with the compact closed, maybe, I think. So that's probably a more mathematical reason as well. Yeah.
Thanks.
Do we have any questions?
Hi, can you all hear me?
You can use those. So we can see your slides on YouTube, please. So
can you hear me?
yeah, we can hear you. Okay, perfect.
Great. So thanks for having me. I'll just get started. There's the famous DARPA disclaimer. And I'll start by talking about flow graphs. So a flow graph is a digraph, basically that if, so directed graph, and it's got two sort of special places in it. It's got a beginning and an end, or an entry and an exit. So the entry is an edge with a vertex of in degree 0 at degree 1, and similarly for the exit. And the idea is if you connect those two, if you just glue the source and the target, you'll get a strongly connected digraph. And what that means is that there's a path from any vertex to any other vertex. And so let's see. And so I'm highlighting here some sort of special parts of this flow graph. So in the solid rectangles, I'm highlighting sort of minimal subflow graphs that are indicated by the places where the boxes cross, and the dashed ones indicate flow graphs, subflow graphs that are not minimal. And we'll see that sort of the reason to make that distinction later. But one thing I want you to notice is that the non-minimal ones are all basically compositions of minimal ones that are taken in series. So that'll rear its head later. So a subflow graph is really just defined in terms of having a region that has one entry and one exit. So in some sense, this sort of sounds trivial. If you go through all the math, you can come up with a relation called the dominance relation that just talks about how paths have to go from one place to another. That's this DOM thing. And then there's a dual relation. You just reverse the arrows or the edges, I'd say, and you get a dual relation. And so the single entry, single exit region is just something so that the first edge dominates the second. So every path through the second edge has to go through the first. And similarly with the dual relation, and there's a sort of technical restriction on cycles. So there's a degenerate flow, single entry, single exit region, just a single edge. And if it's non-degenerate, you can just determine it by the vertices that are sort of anchoring the entry and exit edges. So algorithmically, it's very easy to find these in directed acyclic graphs, literally like 2 lines of MATLAB. It's not quite so easy in general, but there's an algorithmic framework called the program structure tree that does it in pretty easily in quadratic time, and if you're really careful, in linear time. So there's an analogy with these flow graphs and tangles. I'm taking some pictures from an old paper from Baez and Stay showing some tangles, and you can compose these, of course, in series like here and in parallel like here. It turns out we'll be able to do both of those. So that said, there's a little bit of some subtlety involved in this. So you would want to be able to compose these flow graphs in those ways, just like tangles or incobordisms. But digraph categories are a little bit tricky, and the trickiness is how do you deal with loops? And you essentially have to make sort of a judgment call about what that is. There's different ways you can do it. And the way that we do it is basically geared towards applications in program analysis. And we treat loops and non-loop edges differently. And so in practice, we really just restrict attention to a lot of loopless digraphs at the beginning. And that's what you would see in a typical control flow graph in a computer program. You can have a loop, but it's possible to do some compiler tricks so that you can make that not the case. And so it's really just a technical restriction. So you can get a category from this. It's a little bit awkward to define, but I think the rule of thumb is you'd rather have a nice category with an ugly definition than an ugly category with a nice definition. So this obeys that. And if you take the full category with the objects being flow graphs, you get a nice operad thing. So you can substitute a flow graph into an edge pretty obviously. You can compose in parallel, but it's a little bit tricky because if the entry and exit inches are the same or adjacent, things get slightly technical. But the series tensor is trivial. Right? You just glue one to the other in series, but it's still interesting. And the details of this series thing are just here. You glue everything just the way you would expect to. And if you just do some definition checking, you'll see that you get an enriched category overflow. And so the objects are the edges and the HOM objects are just these subflow graphs. And everything's induced by the series tensor. And it's easy to build using this program structure tree. So with that background, we'll go into the theory of magnitude. So you start with a monoidal category and a category enriched over it. So you've got a set, some HOM objects, all the morphisms and horns and whistles, and they've got to satisfy whatever. Once you have that, pardon me, enriched category, the sort of sine qua non for having a notion of magnitude is a size map that goes from the objects of the monoidal category into a semi-ring that behaves nicely under tensor and with respect to the unit. So we've got these very sort of simple equations here. And once you've got that set up, you can build something called the similarity matrix for a finite enriched category. You just say, I'm going to take my HOM object and say how big it is, and take that as entries in a matrix, and that's what we'd call a similarity matrix. And then if you do some linear algebra where you say, I'm going to find this vector so that this equation is satisfied, and I'll call that a weighting. You can do a co-weighting also. And the magnitude is just the sum of the entries of those. And now it turns out in the setting of, Euclidean space as a Lavore, metric space, that this does all sorts of nice things. It has like a notion of an effective size that really amounts to an effective number of points at a scale dictated by by basically a knob you can turn. And it's got nice connections with Euler characteristic, very rich geometric interpretation. And it's been looked at a lot in the setting of Lavore metric spaces, not so much elsewhere. The only example I'm aware of is a vect category, and there's some representation theoretic stuff that has been done there. Now, the Lavore setting just emerges from the normal setup. You've got, the extended the extended non-negative reals. Here's your order structure, and your monoidal stuff is just addition. And that requires this sort of choice of the size function. It's not hard to prove that. And when you run through that, you do get these Lavore metric spaces. So that's basically a metric space that lets distances be infinite. They don't have to be symmetric, and they can be zero. But it does satisfy the triangle inequality, which is important. Now, if you would like to do something that's close by, it turns out that's not possible. There's a lot of rigidity in this setting, and the details are in the paper. They're pretty straightforward. So this is really just to say, if you want something that isn't a Lavore metric space and that isn't this vect category example, you've got to do something pretty different than the ordinary setting. So here's the different thing. So consider a digraph. What it does is there's this notion from symbolic dynamics or ergodic theory, or name your favorite sort of instantiation of these ideas. It could be dynamical systems. You've got a notion of a dynamical system induced by this digraph, which is just if you have a path through the digraph, you can just shift indices, and it amounts to shifting the trajectory through the digraph by one. And so the notion of complexity of a digraph or of the corresponding dynamical system that squares with this is called topological entropy. And here's the formula. But what it really is doing is measuring how fast the number of paths of length n through the digraph grows as a function of n. And so for instance, if the digraph isn't strong, say if it's a directed acyclic graph, well, sooner or later, all the paths end and the topological entropy will be 0. Or if it's a cycle, there's only one path of length n. So again, the topological entropy will degenerate. But if there's lots of paths, then this will be a positive number, and you can compute it just doing some linear algebra like so. And it's not hard to show that the topological entropy has this very sort of nice property with respect to the series tensor for flow graphs. And the reason is that you can just consider a path that's confined to whichever one of these components has the highest topological entropy. So, in fact, you get more than this result. You get some sort of results on the spectrum of the adjacency matrix of this composition, or even on the zeta functions that result that, again, sort of measure the rate of growth. So you can think of special sort of closed cycles in the digraph as sort of analogs of primes. So here's all that in action. So on the left, I'm showing a couple of flow graphs that have been composed in series. And on the upper right, I'm showing their spectra of the original ones and their composition. You'll notice that 0 is showing up in the composition. And then the zeta functions down here. And I don't know if you can see the dots and the lines, but they line up perfectly. So this really is true. And with that in hand, we can define a notion of magnitude for flow graphs. So that Max defines a monoidal structure on this post set of extended non-negative reals. And so this works for Lavore ultrametric spaces. And we can also get this other sort of monoidal structure. And with that in hand, we say we've got this enriched category subflow D. And over the max plus or tropical semi-ring, we just say, okay, the similarity matrix entry is just the topological entropy of the subflow graph or of the Hom object. And there's some sort of, in order to have a well-defined magnitude, we've got to have solutions to these sort of linear equations over the max plus semi-ring. And it turns out that they always admit something called principal solutions that may not actually be real solutions, and you can write them down. Here they are. It's just you take the maxima. And so if you take repeated maxima with that minus sign included, and they equal, then you do have well-defined magnitude. And it's not clear that that's always something that you can do. But it turns out, as I mentioned before, that the non-trivial subflow graphs have to be of the form a series composition of subflow graphs that are minimal. And that turns out to be the linchpin that lets you say that, in fact, this notion of magnitude is well defined. And when you actually go through examples, what you find is that the co-weighting identifies regions of high topological entropy. So it picks out features. And in practice, in something like Euclidean space, the co-weighting identifies sort of regions that are boundaries or peripheral. So there's still some sort of implicit geometrical content, even in this setting of a digraph. So it's pretty interesting to me for that reason. So I'll shift gears a little bit for the last part of the talk and just talk about universal covers of digraphs, where there's a sort of separate connection with magnitude. So if we've got a weak digraph, so not strong, then the universal cover is just defined so that we take all the paths through the digraph. Now you can walk through this sort of definition, or we can just look at an example down here. So on the left, I'm showing a digraph, and it turns out to be strong, but hence also weak. And if we just look at the paths through there, I'm identifying this base point as 1 and labeling it as 0 here. And I just take all the paths that I can through here of length 3. And remembering that the 0 is really a special 1, we just start listing the paths and how they branch out. and we go out to, in and out to some radius, in this case 3, and that's the local part of the universal cover. So here I'll show another sort of picture of the same thing. Again, our original digraph. There's the covering map. This is just the right-hand panel from the previous page. And here's when we take it out to a larger radius going in and out, say distance 10 with respect to the graph, the hop distance. So it turns out that there's a lot of sort of one-line sort of definitions and propositions that fall out of this. So there's a unique path from anything in the universal cover to anything else, or vice versa. And as long as you remember that these loops are cycles of length 1, remember we treat them sort of specially in the category that we are concerned with, then the paths in the universal cover correspond to loopless paths in the original digraph. And so you can consider the ball in the universal cover. And again, we've seen a couple of those at radius 3 and 10, just the right-hand sides of those. And so you can say, how big are those? You can do some linear algebra and just say that the number of vertices in that ball is just, well, I take different powers of the adjacency matrix and sum over the destination vertices of the paths, where I start with the index of the given base point. And so this sort of way of gauging the number of vertices in the universal cover is very closely related to something called the Katz centrality that dates from the 50s and is used a lot in network science. And so again, this is basically the same, except for no discount factor and you don't have an infinite sum. So there's a simple lemma that talks about what the magnitude of a DAG that has a sort of forest structure on it. So a bunch of trees that are not connected. If it's and the magnitude function of this, which is just the magnitude of this matrix, turns out to equal that. The proof is pretty straightforward. And because this number of vertices is the number of edges plus 1, that sort of lemma gives you a sort of very effective way of computing the magnitude of these balls. And there it is. And we've already seen the algorithm for computing the number of these vertices. And so it follows immediately that if this digraph is loopless and strong, that the topological entropy of it is given by this expression. And so from there, it's really just replacing definitions to say that you get this result on the topological entropy for a bound on the log magnitudes of balls in the graph. And this is very closely related to a sort of classical result in dynamical systems due to Manning in, I think, the late 70s for the topological entropy of geodesic flows on hyperbolic manifolds, where you have a result that looks formally quite similar to this, only there's some other notion of size besides magnitude that's available in that setting. But if you take this and just plot it up for an example, the same example that I was showing before, you can see how these numbers vary with the sort of length, the radius of these balls. And you'll notice that the convergence is quite slow, but it definitely happens. So that's kind of interesting. And what's particularly interesting is that these numbers are different enough for small radii that we might think of using them as sort of features for doing various sort of graph analytics tasks. So I'll talk about that briefly before I wrap up. So what I'm showing on the left is the so-called import graph, or you might think of it as a call graph or something like that for a software hierarchy of a package called Flare. It's pretty big, pretty complicated. And these are just the sort of the parts of the program that invoke other parts of the program to get the job done. So I took this digraph and did 100 realizations of the following process. So I take edges out of there uniformly at random, with probability 3/4, and then take the biggest weak component So every edge has an undirected connection, or sorry, every vertex has an undirected connection to every other vertex. And then compute the co-weightings, log magnitudes of balls, and sort of different centralities like page rank, or the very simple ones like in degree. And just look at the correlation coefficients of these to see if they give you sort of useful features for things like graph matching or other machine learning tasks. And it turns out that the co-weighting and log magnitudes of balls are pretty strongly correlated, and that's pretty interesting. So wanted to see if that holds up more generally, and did essentially the same sort of thing with some Erdős-Rényi digraphs of comparable size. And so I'll wrap up by showing sort of results of these correlation coefficients.
Time for questions.
Yep.
Okay, please.
Great, thanks.
Okay, so are there any questions? Right. What was the conclusion slide? Sorry, I interrupted. So can you hear me?
Not very well.
Oh, okay. So can you hear me now?
Yes.
Oh, perfect. So I think the first question was what was on the conclusion slide.
Sure. The conclusion slide just shows that these things are pretty well correlated, and in particular that that the log magnitudes of small balls in particular are pretty close to being something like an in degree or out degree. So they're not very sophisticated, but they tend to outperform most measures, like something like page rank, which is pretty surprising in terms of being correlated between these different realizations. So there's a utility for using these for things like graph matching or machine learning.
Thank you. So are there any other questions here from the online audience? So meanwhile, I wanted to ask, so at some point you related the magnitude of the directed acyclic graph to the magnitude of a matrix, which was depending on some Lavore distance. Is this thing something that depends on the graph, or how would that work exactly?
I'm sorry, it's hard. It's pretty hard.
There was a slide where you were relating the magnitude of the graph to the magnitude of some matrix that has some exponential and Lavore distance to me. Is this matrix related to the graph in some standard way? Or?
The adjacency matrix? Sure. So the adjacency matrix.
Okay. Yeah, so it's the adjacency matrix then, right?
I'm sorry, it's really hard for me to hear.
Sorry. So I was asking if that matrix or the adjacency matrix.
I'm sorry, I think we can do it in chat maybe.
Sorry.
Yeah, thank you. Okay, so meanwhile, perhaps someone can start preparing. So can you hear me now?
Yes.
I was asking if the matrix that is related to this magnitude of the graph, is that the adjacency matrix of the graph?
Well, you use the adjacency matrix to get it. So if I bring my slides back up, I'd show you the formula. But basically, what you're doing is you're taking powers of the adjacency matrix and summing them, and you're doing that either in the Katz centrality or in the setup for these magnitudes of balls in the universal cover. It's almost the same thing. So
right, I see. Thank you. So for the next talk, we are going to have, so let's thank first Steve. For the next talk, we are going to have Lynch talking about compositional thermostatics. So I'm going to give them.
Okay, can everyone hear me? Okay, can people online hear me? I don't know. I won't be able to get nods from those people. But if people online can't hear me, then yeah, interrupt me. Okay, hello. I am going to give a talk on compositional thermostatics. This is based on a paper by John Baez, me, and Joe Moeller. And this work was funded in part, thanks to viewers like you know, it was funded in part thanks to the Topos Institute, Algebraic Julia, and University of Florida. Oh, this works. Okay, wow. So compositional thermostatics is the beginning of an attempt to integrate applied category theory and thermodynamics. There's a long story why I'm interested in that, but I'm not going to go into that now. But like really, mostly this just comes from me trying to learn thermodynamics, and because I like category theory, trying to turn thermodynamics into category theory. So in this talk, I'm going to tell you what a thermostatic system is, which is pretty simple actually. And then I'm going to tell you how to compose thermostatic systems. I'm going to give some examples of the composition, and then I'm going to conclude. So what is a thermostatic system? Well, the basic idea is that thermostatics is the study of equilibria of thermodynamic systems. And the kind of question that one might ask in this framework is, okay, we have two chambers of ideal gas, and we can sort of tweak the parameters. Like you have an experimental setup, you can tweak the parameters of each of the chambers. So we can tweak the overall volume available to both of the chambers. So the divider can move between, but the overall volume stays constant once we tweak the volume. We can sort of add heat to the overall system. And then we can change the amount of gas molecules in each thing. And the question is, well, okay, once we do this, what temperature is this going to be at, and where's the divider? And the answer is that you can find the answer to this question using constrained maximization of entropy. So that basically this whole talk is a categorical formulation of constrained maximization of entropy. So I'm going to get into that. Okay, so a thermostatic system, just one thermostatic system on its own, just consists of a convex space called the state space and a concave function called the entropy function. And so we use a slightly more general definition of convex space than you might be used to. So a convex space is a set X along with an operation C lambda from X times X to X, which we call the mixing operation. It sort of mixes two elements of X with a bias by lambda. And so for every lambda, there's an operation for every lambda. And when you mix X and X for any lambda parameter, you just get X. If you bias all the way towards X, whatever Y is, you just get X. Mixing is symmetric. So if you bias by lambda towards X, that's the same as biasing by 1 minus lambda towards Y. And finally, we have sort of an associativity condition, which doesn't have a neat explanation, but makes sense in examples. So one example of a convex space, this is sort of the traditional example of convex spaces, is subsets of a vector space such that the line segment between any 2 points is contained in the subset. And so does this have a laser pointer? No, that would be too, oh, it does, awesome. So this is sort of this is a formula for parametrizing all of the points on this line segment. So this being in X for all lambda says that the points on this line segment are in X. But there are also sort of more exotic convex spaces, which are not subsets of vector spaces. So the extended reals, which are the reals along with negative infinity and positive infinity, we can put a convex space structure on it where, so notice that for lambda if lambda is 0 or 1, we always know what the mixing is because it's just biased towards one of the parameters. So the thing that we have to define is for lambda between 0 and 1. And for just normal finite real numbers, we just use the standard mixture. But when we mix anything finite with infinity, we get infinity because it's really big. But then we make a decision, which we say that if you mix infinity and negative infinity, well, it's kind of a toss-up. It could go either way. But we make the decision that there's a convention that we choose it to be negative infinity. So you could do it the other way. It turns out that this convention is what we wanted for our paper. A concave function is a function from a convex space to the extended reals such that S of the mixture is greater than or equal to the mixture of the S's. So this B, this is S of the mixture. A is the mixture of the S's. And you can see the intuitive definition of a convex, the sort of definition that you might have learned in high school or middle school of a concave function, where it's like a function that slopes down. Well, these two definitions agree. Okay, so now we're going to get some examples of thermostatic systems. So the simplest thermostatic system is a thermostatic system that has a constant heat capacity. And this has a state space X where we think of the states here as just the energy of the system. We've forgotten everything about the system except for its energy, and the energy is positive. And then the entropy function is S of U equals C log U. And the reason for this is that in thermodynamics, in classical thermodynamics, you identify 1 over the temperature with the partial derivative of entropy with respect to U. And so if we plug this definition of temperature into here, we get CT equals U. And so this gives the interpretation of heat capacity. This C is the heat capacity. When we raise in order to raise the temperature of the system by 1 degree, we have to put energy C into the system. Now, if we take something something with a system with a heat capacity, but the heat capacity is like really, really, really big, then putting small amounts of energy in or out doesn't change the temperature of the system too much. So like the atmosphere of the Earth. And we model this in sort of the limit case by a heat bath. And in a heat bath, the parameter delta U is not the total energy because the total energy is infinite. It's just sort of the energy that you've put in over a certain period of time, where the actual extent of the period of time doesn't matter, which is kind of weird, but it doesn't. And you notice that in this expression, the partial derivative with respect to delta U is always 1 over T. So the temperature is constant. And now I've sort of lied to you. I've said that we're talking about thermodynamic systems, but then that's what I wanted to do originally. But sort of once I like boiled it down, I boiled this down to, okay, convex space, concave function. And then I thought to myself, oh, hey, there's actually a bunch of other systems that have this, that follow this. So for instance, a probabilistic system you can model where it has a state space X, which is the set of probability distributions for some finite set. This is a convex space. And then Shannon entropy is a concave function on this convex space. Fun fact. You can also do this quantum. I'm not going to get into that. And there are also generalizations of probability theory, which are called generalized probability theories, I think. I think that's their official name. I could be wrong. But they're using quantum foundations that also fit into this framework: convex space, concave entropy functions. Okay, now we're going to give, before I give the definition of composition, I'm going to give an example. So suppose you have a hot pie and cold ice cream, and you put it in a cooler. You can do this at home. This is like an experiment that I encourage you to do at home because it's not dangerous. Though you might get melted ice cream, which I don't know, you might not like. And a cold pie. Yeah, so it's really, thermodynamics is a bit depressing. Everything sort of becomes a little bit less exciting. Well, anyways, so yeah, so we put these two together. What do we think happens? Well, we're gonna sort of work this from first principles and show that constrained maximization of entropy, what I said that I was going to do at the first place, agrees with your intuition of what's going to happen, which is disappointing pie and disappointing ice cream. Oh, and ice is Dutch for, this is from my master's thesis, which is in the Netherlands, so ice cream. Okay, so the first system is just like in my example, we're going to model it just by its energy, and it has a constant heat capacity, C1. Second system, same thing, but with a different heat capacity, potentially. The constraint is that, well, this is in a cooler, and it's in like a really powerful picnic cooler where no energy can come in and out. So we're going to say that the total energy is conserved. And then the equilibrium is going to be found by maximizing the two entropies of each of the systems, subject to the constraint on total energy. And now, so let's look at what this means. So at this equilibrium, we can, in high school calculus, you learn to find the maximum of a function. Well, you set the derivative equal to 0. When you set this derivative of this equal to 0, subject to this constraint, because with this constraint, you can parameterize this with one variable. So you just take the derivative with respect to that variable. And you get that the partial derivatives are equal. So that means the temperatures are equal. Boring pie, boring ice cream. And now if we take this supremum of, this is sort of the, maybe you haven't thought of this, but if we take this supremum and look at it as a function of total energy, then you can calculate this out. And what you get is that it's C1 plus C2 times log U, which is actually quite intuitive, because what's the heat capacity of the pie and ice cream together? Well, it's the heat capacity of the pie plus the heat capacity of the ice cream once they're at equilibrium. So this was sort of where compositionality came in. We can now think about composing systems and viewing them as a single system where the parameters of that single system are sort of the conserved quantities in the interactions between the subsystems. Okay. I've always wanted to call something the central dogma. So this is the central dogma of thermostatic composition. So central dogma has two parts. The first part is independent composition. So this is sort of before we've allowed the pie and ice cream to interact, we're just going to make a state space for all of the possible values of the states of the pie and ice cream. And that's just the Cartesian product. And then the entropy of this whole system, but it's not allowed to interact yet. So we're not doing any supremums, anything. We just add them. And so, yeah. So anyway, so this is just, we take a bunch of thermostatic systems, put them together into a single thermostatic system in kind of a pretty simple way. And then we coarse grain it. So this coarse graining is sort of, we take the conserved quantities and then we describe the system in terms of the conserved quantities, and the entropy function on the values of the conserved quantities. So Y could be like the space of total energies, is just the supremum over the states of the sort of underlying system that's compatible with the conserved quantities. And so this allows us to push forwards a entropy function on X along a relation between X and Y to get an entropy function on S. And so the central dogma is that composition of thermostatic systems is independent composition followed by coarse graining. We're going to turn this into category theory. Okay, formalization of the central dogma. So convex relation, I sort of mentioned this before, but now this is a formal definition. It's a convex subspace of X cross Y, and we write it in this way. We can compose these convex relations with the standard definition of composition. It turns out this preserves the property of being convex. And there's a category. Objects are convex spaces, morphisms, convex relations. Great. And for those of you that like wiring diagrams, I know there are a couple of you out there, we can think of this as like a wiring diagram where we're wiring together this system and this system to get an overall system. And for some of you, you're gonna be thinking operads. We'll get there. And okay, now from this category, we're now going to model. So we've modeled the convex spaces. Now we're going to model the entropy functions. And the way we do that is we make a functor from convrel to set, which sends a convex space to the set of entropy functions, possible entropy functions on that space. And then the action of this functor on the entropy functions is exactly the coarse graining. So this is sort of backwards. This is part 2 of the central dogma, which it turns out in the math, this logically precedes part 1. And now part 1 of the central dogma, the independent composition, is that there's a natural transformation from ent to ent to ent of the product, which basically takes a bunch of entropy functions and sends them to their sum. So this is part 1 of the central dogma. So now, putting it all together, ent along with mu forms a lax-symmetric monoidal functor. And because I'm hoping because this is ACT, I can get away with this. I don't have time to define what this is, but maybe you'll get excited, maybe you won't. But anyway, with this lax-symmetric monoidal functor, the central dogma builds a thermostatic system on Y via first you do independent composition with mu, and then you do the action of the functor. And sort of this 2-step process is formalized or is sort of, yeah, this 2-step process turns into 1 step when we move to the operatic framework. So in operad, I consider multi-operads. I consider operads with multiple types. So some people only think that there is 1 type in an operad, which is fine, but I don't. I think that there are multiple types in an operad. And an operad consists of a collection of types, and for all types, a collection of operations. So it's sort of like a category. You can also call this a multi-category. It's like a category where a morphism can have multiple domains. So it's like an n-area morphism. And there's an operad where the types are convex spaces and where operations are convex relations between the Cartesian product of all of the inputs and then y, and then y is the output. So we can think of this as this describes a way of composing a bunch of systems with state space x1 to xn, and then getting a system description in terms of the conserved quantities in y. And so an operation is exactly the information you need to compose thermostatic systems. And now in operad algebra, well, we associate a set of things to each type and a function to each operation in a way that's compatible with composition in the operad. And we can turn the central dogma into an operad algebra. So we start with a bunch of entropy functions so that we have like n thermostatic systems, X1, S1 to X1, Xn, Sn. And then we end up with a thermostatic system with state space Y from central dogma, independent coarse graining. Okay, back to pie and ice cream. So now that we've sort of done the framework formally, I'm now going to show you how it works in the case of pie and ice cream. So we start with the spaces X1, X2, and Y they're all positive reals, missing a 0 there. And then we have a relation between the product here and Y given by, it's a set of triples such that U1 plus U2 equals Y. So this is sort of a specification of the conservation law. Then we take the entropy functions. So these are elements of ent of X1 and ent of X2 given by the entropy functions describing a constant heat capacity system. We use the operad to apply this R to these two things, and then we end up with an entropy function on Y, which is this entropy function on Y corresponds to a heat capacity of C1 plus C2. It's just, so I said I would take the central dogma and make it into category theory, and I did it. So now I'm going to give a brief example. I'm almost out of time, I'm assuming. No, okay. What have I got? I am almost out of time. So what happens when we attach a probabilistic system to a heat bath? Well, what does that mean? Well, okay, so let's start with a probabilistic system. We gave this as an example before. Heat bath, we also gave this as an example before. What does it mean to connect them? Well, we're going to give a relation between them and sort of the empty interface. So it's just a relation between them. And that relation is that the expected value of the energy observable is equal to the energy taken out of the heat bath. And when we maximize entropy now here, what we get is the canonical distribution, which is sort of the start of statistical mechanics. So I don't know if this example says so much, but it was kind of exciting to me when I made this formalism for thermodynamics. And then it also, it told me something about, or it somehow had some connection to statistical mechanics. Yeah, and that's pretty much the end. So what have I learned from all of this? Well, I've learned a bit of thermodynamics. I've learned that operads and operad algebras are a toolbox for complex open systems, which, yeah, algebraic Julia has taught me that, but now I learned it in my own way too. I also learned that a lot of thermodynamics and statistical mechanics just sort of boils down to constrained entropy maximization, which I think is sort of a neat little kernel in the center of it, because sometimes thermodynamics can be very confusing. And then finally, I learned to love lax symmetric monoidal functors. They're kind of weird, but they're useful. Okay, thank you.
I have a question.
Is that on Zoom?
I don't know.
Yeah, go ahead.
My question is, sir, do you have formulations of the first and second laws of thermodynamics in this formalism?
No. So, but they are connected to this formalism. So the first law is a statement about conserved quantities. So you have to, like, nothing about the system tells you what relations to pick, but you can pick relations that are inspired by the first law. So my relation to the pie and ice cream, the first law there was that the total energy of the pie and ice cream was conserved. And the second law sort of comes in that, like, entropy. Well, why do we care about constrained entropy maximization? Well, it's because, you know, if you imagine you have some dynamical system which obeys the second law, so that entropy is always sort of increasing or at least non-decreasing, then an equilibrium point of that system is going to be somewhere where the entropy can't increase anymore. And if entropy is concave, then there are only global maxima. So you're not going to get stuck in a local maxima. So that's one of the reasons why we consider concave functions. So the second law is sort of a justification for why equilibrium is found by constrained entropy maximization.
Hi, so this is sort of way at the beginning. I'm curious
where
this sort of abstract definition of convex spaces came from. Because to me, that just looking at that, it looks very bright for like it feels like the points ought to be like objects, these sort of hats can be some sort of like morphism. It feels like some sort of factorization condition of the morphisms, and there's some associativity thing going on. I don't know if that is anything.
So this goes back to, I believe, Stone in the 40s, and he called them barycentric algebras. And I am excited about categorifying these things too. Yes.
Thank you very much. I think the next speaker is Christopher Brown, so if you can start with that.
Okay.
I was curious whether you're familiar with the work of Lieb and Younesse. I can never pronounce the guy's last name. Navson?
I can already answer no, but go on.
So the work that they did there is similar to what you've done in that it was close enough that I was actually curious whether you started from that paper.
No, yeah.
So I can speak to you more about it afterwards.
You on category? Oh, yeah, afterwards. But also category theory Zulip.
Yeah, they definitely didn't use category theory. So
no, but I'm saying like you can message me on category theory Zulip.
Okay.
Yeah. Okay.
Thank you. So I think we will have much more conversation.
Okay.
So now.
Yeah, take the second one. Yeah. I guess I can look at this. What's wrong? No, this is what I want. I want. Okay. I want that. Oh, we don't want that. Oh, sorry. I want to see that. I don't want them to see that. If you like change the window that you're looking at, there should be a.
How do we do that with PowerPoint?
Oh, I thought it was like a Zoom thing that you.
No, that was just the PowerPoint.
I was like, Zoom looks at different windows. But okay, why don't we just do the normal view? And I guess I won't have notes.
I don't know which one is.
Okay. Brilliant. Yeah. Yeah, so then you just point them at, yeah.
So now we can do exploration.
Thank you, everyone. So I'm going to discuss some work that we did at University of Florida. It's clipped. Now we're good. Okay. So I'm going to discuss some work we did this past year. And I think we're very used to exploring model spaces where it's a parameterized model and our parameters are real values and you do some sort of gradient descent. But in contrast, we're going to try to explore spaces of models that, oh, is this connection? Yeah. I can just stay within this radius. I can't imagine moving further. Yeah, cool. No, I'm fine. So we're going to explore spaces, model spaces where not only do we not have continuous parameters, but we might not even have parameters at all. And the models we're exploring are actually structurally different. So we're not going to make that kind of process fully automatic, but we're going to give a language for domain experts that can allow them to combine their smaller models into larger models. So I'll start by motivating this idea of representing scientific models combinatorially at all, and then I'll go into some category theory and how we apply it. So in the real world, a lot of scientific and engineering knowledge are represented in very opaque formats, such as random one-off scripts that someone writes to simulate a chemical reaction like this. And it doesn't even help if the scientist represents it with general math expressions or logic, because those are all formal and very powerful languages, which makes them actually very hard to reason about. And so actually we want to work in more restricted syntaxes that we can actually perform automatic reasoning about. And when we do that, there's all sorts of really cool and useful things that we can do with that knowledge that has been formalized. So I'll try to briefly walk through the first four of these, but then the talk is really going to focus on this fifth one of exploring alternate, let's say, chemical reaction networks to fit some data that you might have. So one potential thing that you can do with a scientific model that's been represented combinatorially is generate the code itself that you would have written. So this is a working example that we'll use throughout the talk of an SIR model, where we're actually going to represent that data, which is the data of a Petri net, as a particular functor from this category to set. So this co-presheaf has the shape of that has 4 objects and 4 generating morphisms, and that captures the data in order to create this Petri net. And then we can do some functorial semantics and actually give it this ODE semantics that allows us to then compute the differential equations and do simulations. But something that we can also do is easily change the semantics now that we've separated our syntax and our semantics. And now we can give these transitions rewrite rule semantics and then apply those rewrite rules stochastically, and then we get a discrete time simulation. We can also view Petri nets, give them yet another syntax of a query. So think of the Petri net as a query in some database of chemical reactions where homomorphisms from this Petri net are picking out matches of a particular shape. And now we can actually use this operad of undirected wiring diagrams and actually nest Petri nets inside of each other and build them hierarchically. And if you were to try to do that with SQL, the sort of natural way that you would write out a query like this, suddenly you don't have that kind of hierarchical composition. You can't just substitute SQL into SQL. Another way that you can build models compositionally with this kind of Petri net representation, this combinatorial syntax, is to essentially take limits or co-limits in this category of co-presheaves or C-sets. So this is an example that Sophie went into great detail in her talk yesterday, which was essentially this idea of model stratification as a product in some category. So if we have, I mean, intuitively, we have some disease model, and we have some transportation model of people going between two cities, there's a natural thing to do to combine these two models, and it happens to correspond to a categorical product. And you end up with two susceptible populations, two infected, two recovered, and the right transitions of people going between the cities. So now what I'm going to talk about is, I'm going to work towards this as like a final slide, is I'm going to talk about this process of building entire spaces of models via limits and co-limits, not individual models. And so we might have some real data that we're trying to fit. We don't know what is the right Petri net that does describe it, and nor its parameters. So we need to build entire space of Petri nets in order to explore, to compare to the data, and eventually evaluate which one of them is the best fit. So we want to essentially build up to this. So now I'm going to talk about some category theory, the category of diagrams. So to make things more concrete, these really could be diagrams in your category of models. Because our working example is these Petri nets, which represent chemical reaction networks, I'm going to talk about diagrams in Petri. So our diagrams are going to have a shape category, which is a small category. Because we're actually implementing this on the computer, we can't, it's really convenient to be able to represent small categories as presented by graphs. And we just take the free category that's presented by a graph like this. And so for each object in this category, we're going to assign a Petri net. And for each edge or each generating morphism, we're going to assign a Petri net morphism. And so what's the interesting thing about the category diagrams is what you want to pick to be the morphisms of this category. So you actually have quite a few choices. One choice might be to take actually something that's like a slice category where I demand some equality here, where I have a functor of the shapes, but I demand equality. But that actually wouldn't serve our purpose, because what we want is pushouts and pullbacks to build things compositionally. So in order to get that by completeness, we actually want to work with a lax slice category. And so in addition to having a shape map, we also need the data of a diagram map whenever we have a morphism. And that's what's going to allow us to do our constructions. So I'll motivate why we want to do pushouts and pullbacks by showing some examples. So we already saw building an individual model compositionally with limits. But now consider it's a very natural thing actually to have multiple entire dimensions of parameters that you want to explore. So you might have a whole sequence of diseases that we could linearly arrange as a disease dimension. And we might have a whole sequence of transportation models, maybe a 1-city model, a 2-city model, a 3-city model. And what we want is to have one thing from each of those. So this actually corresponds to just literally the product in the category of diagrams of this linear shaped diagram and this linear shaped diagram. So you get essentially a shape that looks like this grid. And if you look at any individual model in that, and you actually look what Petri net lies underneath it, you're going to get the actual product that I had shown earlier. So this is kind of model stratification, one more level meta. Model space pushouts essentially are encapsulating this fact that we don't always want grid-shaped parameter, grid-shaped search spaces. Sometimes we have either or decisions to make. And this is really captured with co-limits. So here we're taking a push out where actually the first model happens to be the exact same Petri net. And when we do that, there's nothing interesting going on at the Petri net level of the diagram, and we just really create a branching shape. And we could also take a co-product, and it just sort of, just has the two diagrams living side by side. But then you might ask, what happens when these don't actually share? Let's say we're gluing together the very first model in these two sequences. What happens when they aren't the exact same thing? And it turns out that actually corresponds to something interesting and practical. So this operation, which I'll call the gluing operation, is going to, let's look at this example. So I have a disease dimension. This is an SIR model. This might be an SIR model where people can get reinfected. And then we say, and so on. What I want to do is consider, well, none of these models are considering the possibility that someone might actually die. And so I have this notion of a death transition that's living in this other diagram. And I want to actually glue this to my SIR model. So if I construct this push out of diagrams, I'm going to glue together this death transition to the SIR model. But then there's this morphism here, which is going to send it's a PetriNet morphism. And it's going to send the data from A1 to B1. The only data I have to start out with is this SIR model to the SIRS model. It doesn't know anything about the death transition. So it turns out actually that the only kind of universal thing you can do is actually freely add another death transition to the next thing in the sequence, and it actually adds it in the right place. So you end up actually gluing together this death transition to everything in this entire model space. So that's like at a high level, this push out corresponds to something that's very semantically intuitive that you might want to do. And we can string together these different operations that I've just shown you and organize them in, as a process that is through a string diagram. And this is nice because it separates the sort of workflow that you want to do from the particular inputs that you're going to try to test that on. So I want to stress now that this is all stuff that's actually been implemented in this package model exploration.jl, which depends on CatLab.jl. So if you really construct these diagrams and you provide the data as a user, you can feed them into a diagram like that, or just call coproduct and call product on your actual diagrams, and you'll actually compute the result. So what happens if we glue together the death transition to our disease dimension, but then we also coproduct that with the disease dimension, and then take this product with our 1 city, 2 city, 3 city model? So when we do that, we get this result. So I'll try to walk through some of it. So the result of gluing, as we saw, was this SIRD model, SIRSD model, and so on. Our disease dimension looks like this model, SIR, SIRS. And if we coproduct them, we get the sort of front face of the triangle. And then when we take the product, it's sort of the dimension into the page. And you can start having that shape at every single 1, 2, 3, 4. So by just, our starting ingredients were very simple, just these 3 things. And now we've generated this somewhat complex topology of a model space. So let me talk a little bit more about the implementation, because a lot of this is interesting of how you actually implement this on a computer. So I want to just briefly show some intuition for what the limits are, because we need to actually, need to compute for a product between, let's say, a diagram A and a diagram B, what for each object in the product diagram, what PetriNet does that correspond to? And for each morphism in the product space, what PetriNet morphism does that correspond to? So I'm showing an example morphism in this product diagram. And it turns out that the product diagram is just, the shape of it is just the product of the 2 shape categories. And so we're going to have for every pair of objects, an object in the product category, and for every pair of morphisms, a product morphism. And it turns out that it's really natural how you compute this, because for every pair of objects, you simply just take the product in the underlying category, which here would be a product of PetriNets. And it's also worth mentioning now that because PetriNets are co-presheaves, that our notion of a morphism of PetriNets is just a natural transformation. So we know that we can just take products in the shape category to get the shape. And underneath, we simply just take products of the corresponding objects. And then by the universal property of products, we can induce what the morphism should be. Equalizers are essentially the same way. We take an equalizer of the shape categories, and underneath, we're going to have these diagram map data is going to allow us to equalize those morphisms underneath and essentially generate the object data and the morphism data underneath. And so we can completely determine what the equalizer is by just taking equalizers of the finite, the small categories up top, and of equalizers of PetriNet morphisms underneath. Coproducts are also very simple and straightforward to implement, because you simply take coproducts of your shape categories again, and underneath you're also taking coproducts in the underlying space, such as PetriNets. Co-equalizers are quite a bit more challenging, because it turns out that what you would love to do is take a co-equalizer of the shape functors, and then take co-equalizers somehow underneath of PetriNet morphisms. It turns out there are no parallel morphisms to co-equalize that give you what you need. So there's a somewhat complicated construction. This is given by Peshke and Tholen. And it turns out that this is essentially taking left-con extensions in order to give you morphisms to co-equalize. But I can go into this in more detail if there are questions about that. But essentially, we have a means of actually computing all of these limits and co-limits in terms of limits and co-limits of the underlying category. And so that means we can really implement this. So now I want to use this model space that we just constructed here, and I want to actually apply that to a practical problem, which the sort of example problem we've been working with is one of you have real world data, you don't know which Petri net is actually corresponding to that best. So we're going to actually just truncate this infinite model space to the 8 models you see here. We'll actually pick one of those models and add some noise to it and use that as our sort of ground truth model. And then what we need to do is evaluate all the other models with respect to this data. And one way to do that is to do a sort of nonlinear optimization of the parameters. So we essentially find best fit parameters. And our notion of best fit is minimizing the distance of the trajectory data to the SIR trajectory data that we have here. Now, I did a little sleight of hand actually here because this is, I'm comparing the trajectories of SI and R, but there is no object, there's no state in this model S, and there's no state I. And some of the models have D states. So it's like, how do you compare the trajectories of these different Petri nets that are sort of living in different state spaces? So this is where it actually is really helpful that we constructed these model spaces in virtue of limits and co-limits, because the projection map data is what allows us to put all these different models on a par with each other. So if I have observations of, let's say, SX data and SY data, I can still view that as susceptible data because I can essentially integrate out the other information. So I can use the projection maps to essentially sum up all the components in the different cities. Likewise, for parameterizations, we can move information the other way as well. So an example of this is the initial conditions. Let's say we know that initially, our real data is that initially 90% of people are susceptible and 33% of people live in city X. So I have those, I have a parameter for, let's say, one side of our model and a parameter for the other side of our model. It turns out that given some commutative monoid that we pick, but in this case, there's a very natural choice to pick, which is multiplication, we have a very intuitive notion of what is a good guess for the initial population of susceptible people in city X, which would be 30%. So essentially, the projection map data for both the limits and the co-limits allows us to move information both from the composite model to the sort of primitive models that you might have concrete data for, and vice versa. So yeah, we can generate essentially these trajectories for all 8 of our models and look at our loss function. And I've color-coded it and also written the number of the loss. So low is good. And we see that the true model actually does have the lowest score. So this whole pipeline has been automated just from constructing the model space. And so how would you interpret this data? Well, it turns out if we restrict our morphisms to monic morphisms, it turns out that that means that there being an arrow from one to another is sort of a proxy for complexity. And that means that we can actually take the least element of all the elements that score very well. And that will be our simplest model that explains the data. So to conclude, we want to have not just manually constructing the sort of inputs to your system, but some sort of automatic thing, such as generating an entire dimension via a sequence of rewrite rules that get applied randomly. Actually implementing that wiring diagram GUI will be really essential for scientists to actually use this as a tool that they would use. Working with infinite state spaces would be only possible if we implement some sort of lazy exploration. And yeah, working with other applications and other interesting ways of using loss functions. All right, so thank you.
Are there any questions? Yeah, so I want to ask about the optimization procedure. So are you picking each of those models in the model space like individually? And if so, is there maybe a way to use the maps you have between the models to somehow not compute, like recompute the loss bit?
Yes. So each of these morphisms has, Petri-net morphisms have a really useful property, which is that if I have a parameterization, let's say, of this model, SIRD, I can essentially push forward those. Let's say I fit the parameters for that. I can push those parameters forward along that morphism and get a parameterization of another model that performs at least as well. So yes, we can use that to reduce work. It sometimes is not the right decision, such as the 1 city to 2 city model. Where is one? Like this morphism is going to pick city X, which means that you're going to initialize this with everyone in city X and city Y is 0. And maybe that's like not the best initial guess. So use that technique with caution.
Any other quick question? We can find.
I essentially the same question. So
we can find Chris.
Okay. Thanks.
I used to have something like a 20 minutes break, and then there will be the during school session of posters. I also think we don't have an announcement.
Oh yes, for people who want a receipt of payment for the dinner and conference, you can talk to me here. I have a bunch of them, so you can spread them out. And also, if you need receipts of attendance of any kind in general, but however it is, you can email or talk to Fred.
Yeah, we can go. Oh, okay. No way. Oh, I see.
category theory, which began as adjoint, and this is a pun, to, thank you, to the Applied Category Theory Conference a number of years ago. And what it is a combination of a learning seminar and a research workshop. So we have a number of students, usually it's about 16, who come together and work with 4 mentors on projects in applied category theory, novel research. And for the 6 months leading up to the period of this workshop, they read papers in applied category theory, and they discuss it with each other. They write presentations on it, and eventually they also write blog posts, which will be going up on then everyone gets together here. We got together last week in this very building to work on doing this research. They work all week, all the time, do math, tons of math. And here, what you'll see is a result of this, which is a preliminary results. Over that time, they've done a lot of research, not necessarily finished any projects. It is a week-long school, but they're here to show you what they did. They did a lot of really good work. So I'm pretty excited to see what they got. Is there anything I'm forgetting? Great, so let's begin. I think we'll start with our first group here, which was compositional thermodynamics, and it's an example of Lavere's entropy framework by Román and Lemonnier. So
just me for the presentation, but yeah. Hi everyone, I'm Mano. I don't know if this mic setup is working okay. Yeah, okay, perfect. So yes, I was in the compositional thermodynamics group with Spencer Brenner, Joe Muller, and Owen Lynch. And over the course of the adjoint school, we read a 1984 paper by Lavore that proposes a categorical framework for working with thermodynamic entropy. And last week, we were working on coming up with a concrete example for this framework. So I'll tell you a little bit about that. So we'll start off with the framework itself. So Lavore starts off with a category P that represents a thermodynamic system. The objects of the category are the collection of states in the thermodynamic system, and then the morphisms are the processes that allow you to get from state to state. And Lavore also starts off by assuming that there's a functor from this category representing a thermodynamic system to the additive monoid of extended reals. And that's just a single object category where the morphisms are extended reals and the composition is addition. And we'll call that functor the entropy supply. And entropy in physics, it's in general about the amount of disorder that you have in a system and the amount of disorder that you introduce by doing stuff to a system. And yeah, so processes either consume entropy, which means that they cause a system to become more ordered, in which case they'll have a positive entropy supply value, or they generate entropy and make the system more disordered with a negative entropy supply. So Lavore doesn't provide an example of this thermodynamic system category or the entropy supply functor. So we started off by just thinking of a simple one that we could do, just like a network-based model where we can look at heat flows from subsystems to subsystems and interactions with the environment. So these hollow vertices are like interfaces. And then the inner graph, you can think of each point as maybe a tank of idealized gas. And they're connected by maybe like metal plates that allow heat flow from one to the other. And yeah, entropy supply is all about the flows through the interfaces of such a network, the interactions between a system and its surroundings. So formally, we think of heat networks as open graphs. So this diagram up here formalizes the structure of that. So X is our set of interface vertices with this iota map telling what subsystems in our system of interest the interfaces are connected to. And then the vertices and edges within the actual system, it works like a normal graph with source and target maps for the edges. Yeah. So when we start off with one of these heat networks, we assign a heat capacity to each vertex. And physically, a heat capacity is just the amount of energy that you add to a material in order to increase its temperature by 1 unit. It's a property of the system and not something that'll change over time. And we define the states of the heat network to be specified by a function u that assigns an energy to each vertex. So we have this concept called a phase space where all of the states of the system live. And a point in phase space is a state, and it's just going to be a V-length tuple of non-negative reals. And then we have a temperature of the vertices at a certain state. And again, we see the heat capacity here because the temperature of a vertex is just its energy divided by its heat capacity. So that was sort of setting up the machinery for our states in our phase space category. I'll change my terminology there slightly. I was calling it the category representing a thermodynamic system, but it really is a phase space because the objects are states, and then the morphisms are paths between states in the phase space. So a process consists of a time interval over which it happens, a piecewise differentiable function that assigns an internal energy or points out one particular state of the system that a process takes the heat network to, and then two integrable functions, f and g, where f is all about the heat fluxes that are within the graph, and then g assigns heat fluxes to the interfaces. That's the interaction between the system and the environment. And these processes have certain constraints. So the first one, so for all vertices and almost all t in this duration, because this is piecewise differentiable, we have energy conservation, which basically says that the change in energy at a particular vertex is the sum of the flows into that vertex, the sum of the flows out of that vertex, and then any interfacing that that vertex might do with the environment. And then that's the first law of thermodynamics. There's a lot of physical meaning behind it. And yeah, this second one is essentially a condition that heat only flows from hot to cold. So if a vertex has, if a source vertex has a higher temperature than the target vertex, then the value that's assigned to the flow will be positive. Otherwise, it'll be negative, which is pretty much equivalent to switching the direction of the process arrow. And the fact that heat only flows from hot to cold, it's a consequence of the second law of thermodynamics. Systems have a tendency to equilibrate, and basically, if you have a hot thing and a cold thing, that's more ordered than having things that are of the same temperature. So it's about the fact that entropy increases over time. So now we can set up this category of heat network processes. The objects are the collection of states within the phase space. The morphisms are the collection of processes where the domain is the initial state and the codomain is the final state. We can call our identity morphisms freeze processes that have 0 duration and 0 heat flow. Basically, nothing's happening in the system and it remains at the same state. And we think of composition of processes as concatenation. It's just if you have one process, if the domain of the second process is the codomain of the first process, then you can do one after the other. That's the idea. And yes, now we can define our entropy supply functor. So again, we have this functor S from our phase space category to the additive monoid of extended reals. And in order to define S for our phase space category that we've put together, we took some intuition from thermodynamics. It's that the change in entropy is equal to the integral of the heat flowing into the system and the temperature of the surroundings over the temperature of the surroundings. And you can sort of identify parts of this functor definition to parts of this. So again, G sub X is about flows that come from the interfaces into the system. So that's your DQ. And then T sub iota, that's the temperature of your interface points. And this is functorial. We have preservation of identity morphisms because the entropy supply of a freeze process in which there's no heat transfer and no duration is going to be 0. And S also preserves composition because if you look at a composed process, this integral is going to be the same as if you look at the sum of the integrals for the first process and the second process. And Lavore is particularly interested in something called the naive Clausius property. It's something that captures the essence of the second law of thermodynamics. So it's that the change in entropy over a closed loop is always less than or equal to 0. So thermodynamic cycles can't decrease entropy. And the idea is that you can't have something like a perpetual motion machine that basically can perform endless amounts of work without dissipating any of the energy used to perform that work. And categorically, Lavore sort of adapts this property and says that the entropy supply of an endomorphism is going to be less than or equal to 0. We have a short proof of that. So the theorem is that our entropy supply functor satisfies the naive Clausius property. And we start off with the definition that we gave. And using a little bit of algebra and applying conservation of energy, we can get it to this form on the second line, where the first term reduces to 0 for cyclic processes. And then the second term, because of this heat flow condition, both of the factors are going to have the same sign always. And the second term will always be less than or equal to 0. So we didn't assume it to begin with, but our functor does end up satisfying this Clausius theorem that is an important consequence of the second law. So that is a nice physical connection. And some future directions that we'd like to explore are adapting the network model to other thermodynamic fluxes like work or particle exchange, and also investigating the functoriality, the construction of heat proc from open graphs. Thank you.
Thank you, Are there any questions?
Might I ask a question?
Yep, of course.
Is there any suggestion that there's a connection to statistical thermodynamics with this functorial framework?
It's a little bit hard to switch between like statistical, mechanical, and thermodynamic perspectives of entropy, I think. And yeah, it's something that I don't think we really approached during the research week. Do you?
No, we didn't cover that question. I would say that like this integral that we're doing, like as the integral of S, it's integrating over ds to get S, I think. Like if you had just the equal equation in terms of this infinitesimal differences, then in the heat network case, you would get S as logarithmic, multiple logarithmic of the energy.
I mean, the perspectives of entropy and thermodynamics versus statistical mechanics, it's like thermodynamics, it makes sense to talk about entropy of processes, but I feel like statistical mechanics is more about the entropy of states and you know, the relationship between microstates and macrostates. We're really considering doing things to systems and not seeing what they're like at you know, equilibrium.
So my question is about the extending to other thermodynamic fluxes.
Mm-hmm.
How
Yeah, how would you build it? Would you do like a multi-layer network, or what are your thoughts on that?
Let's see.
So although we haven't concretely worked out what happens in other cases, so we did consider and start thinking about, we haven't written it down yet or worked it out, is, so here we talked about heat networks. If we have something else, I'm going to call it a work network, where instead of heat energy being exchanged between subsystems, you have work, like pressure volume work. And so you can have adiabatic transitions of every subsystem state to the next, and you have adiabatic partitions. So think of like thermally isolated systems, and then you push around. You allow the partitions to move, to do pressure volume work. So in that case, we do expect that the flow conditions would instead be dependent on pressure. So pressure differentials rather than temperature differentials. So we were hoping that if we were to look into this next, they would inform how to do the more general case where you can have both heat and work involved in these systems.
Are there any other questions?
Hi, so this may be way off the mark, but the stuff with like the graphs and assigning sort of like results to the graphs kind of remind me of like discrete Morse theory. And so I was wondering if there's like any kind of like way you could go backwards and like based on the behavior of like the flow, this thermodynamic flow of a system, and to tell you something about like the shape or the topology of the graph, whatever. Do anything like that. I don't know.
That's an interesting thought. We haven't thought about that because we're approaching it from the perspective of every subsystem having states, and then the flows between the states what properties those have. So if you just had the flows, then try to get the subsystem states, I don't quite know how that would. I don't know how to go about that, if that's something.
Yeah. So as you may know, at UF, we have the Dataflow project, which is PDE's meshes, and that the sums of over the target for the conservation of energy there, that can be thought of in terms of the differential of the chain complex. So I'm not sure you can infer. I'm not sure if you can infer the topology of the graph of the processes, but then you can talk about this in a cohomological way.
Okay, thank you. Are there any other questions? Okay, so I think we can move on to the second group. So the second group is going to, Sean is going to present, and they're going to talk about fuzzy type theory for opinion dynamics. So yes, you should. Graded non-symmetric.
Should I try to get it facing up? Hello, is this on or?
Yeah. Yeah.
Ooh, fantastic. Where's the laser pointer? This.
It's upside down. It's this.
Yes, fantastic.
Yeah, and I issue.
Okay. Yes. All right. Can everyone hear me? Nice. All right. Hello. My name is Sean O'Connor, and I'll be giving the fuzzy type theory for opinion dynamics talk. First, though, yes, the Alt tab. Fantastic. First, though, I just wanted to give a brief moment to thank the rest of my members of my group who unfortunately couldn't be here today. I know how easy it is to see one person giving a talk and not really internalize all the other people that worked on it. So I just wanted to put some faces to the names and thank them. And unfortunately, Hans couldn't be here the previous week either. So I have his photo from his website. All right, so here's the idea. We want to model opinions in a way that sort of keeps track of how those opinions were formed. So the idea Paige had was to kind of almost do like a proof relevant opinion modeling, where we can represent opinions as terms of some type. And so we can evaluate how a specific term was constructed, perhaps looking at specific constructors, and hopefully get a way to infer how exactly someone came to have an opinion just from the opinion they currently have. And to do this, we're going to model types as opinions, and then terms as proofs of or reasons for opinions. And so the reason we're using terms here is because you could have someone have one opinion and have another person have the same opinion, but they could have arrived to that opinion in two completely different ways. And so we want to be able to distinguish between those cases. And then finally, we want fuzzy logic as a way of sort of talking about the degree that someone holds an opinion. Because you could have someone hold the same opinion, but like to different degrees, depending on the amount of evidence they have, or maybe the situation they attain that opinion. And so we have this nice diagram here, sort of talking about the differences between binary and fuzzy logic, and then propositional and type theoretic systems. So we can think of this as, so type theories have categorical semantics, which is sort of this category that can be used to reason about the semantics of the type theory. In the case when the category is enriched over the Booleans, or in the case of posets, we actually get that this corresponds to natural deduction. So natural deduction is almost like type theory, except you don't actually worry about the terms of an individual type. In the case when it's enriched over set, we get that this is just simply type lambda calculus. And that's a pretty standard construction if quite involved. We haven't fully worked this out, but we think that in the case when we enrich the category over the interval, so from 0 to 1, this corresponds to fuzzy logic, except it would be like a natural deduction form of fuzzy logic. We actually chose not to go into that too much because we wanted to focus on the next one, which is when we enrich the category over fuzzy sets. So in this case, each Hom set will be a set paired with an assignment of fuzzy values to each element in the set. So this right here is what we're focusing on. So to sort of get to sort of figure out what a fuzzy type theory is, we're going to use this back and forth between type theories and categories. Because we can take the syntax of a type theory with all its structural rules, and we can look at the categorical semantics of it, but we can also do the reverse. If we have a category that sort of satisfies the semantical properties that we want, we can try to derive what the structural rules should be. So in some sense, what we're doing is we're going to take the standard category of semantics for a simply type lambda calculus, or hopefully later on dependent type theory, and then we're going to enrich that category over fuzzy sets, and then try to work backwards to get a fuzzy type theory from there. And the whole reason of doing this is to try to make as few choices as possible in some sense, so that we have less of an issue of making a bad choice and then having consequences down the line. So we can obtain a category from a type theory where the objects are context, and then the context morphisms are a list of terms. So specifically, if you have some context gamma and a morphism into a context delta, what that means is for each term in the context delta, we could derive that from the context gamma. This is important mainly for, this is how we do substitution rules in the category of semantics. To give a bit more background on this, in case you're unfamiliar with it, a type in some context is a specific class of maps called projections from this term right here, gamma.a into gamma. So this says that A is a type in the context gamma. If you're wondering about what we mean by projections here, this is formalized specifically in C systems, which sort of clarifies how we can actually talk about gamma.a, because that is purely syntax. That does not actually correspond to some sort of product or concatenation operation in the category. We have terms. So a term of a type A in a context gamma is a section of a projection. And the reason for this is we want, in our type theory at least, terms to only have one single type. And this works because sections are only sections of a single projection, which is nice. And then to do substitution, we're also going to do pullback along projections. We'll see an example of this later, but we can do similar things for all the different structural rules in type theory. All right, so our strategy is enrich the categories and then read the type 3 from there in the same way that we would read the type 3 from the standard category. So we're going to let V equal the category fuzzy sets, and this will be a monoid because it's sort of just taking sets and then applying the interval category, which is a monoid in itself. We're using the less than or equal to relation because we want this to be ordered. So objects are going to be pairs. So objects in V are going to be pairs of a set and then an evaluation of each element in that set to some fuzziness value. And then morphisms are going to be order preserving set functions. And the hope here is that we can work between fuzzy type 3s and V categories. And we're going to understand this by looking at the standard way categorical semantics are used, and then trying to get fuzzy type 3 from there. Okay, so some reasons to do this is we're trying to model opinion dynamics using this. And the way we're going to do this is have each agent in the system have their own V category, so their own category enriched over fuzzy sets. And the hope then is that context would be a set of beliefs that this agent has, and then a type in context would be a set of beliefs and it's like premises that an agent would have. And then a term of a type A would be a proof of the belief corresponding to A. And because we want definite beliefs, we're going to actually have non-fuzzy types. This was a bit of contention at the beginning. I was in favor of fuzzy types, and that turned out to be wrong. So glad we didn't do that. But now we do want fuzzy terms because we want people to be able to have different strengths of an opinion. And so we're going to try to find a way to have non-fuzzy types, but fuzzy terms. And so the way we do this, once we get to the math, is having an axiom that types are not fuzzy, which corresponds to the evaluation of every projection map to be 1. However, we quickly run into an issue. The way sections are normally defined in non-enriched settings is such that the composition with the projection is the identity. The issue here is that if we want this to hold true in our enriched case, we get that the morphism from gamma into gamma.a, which corresponds to the section, would have a fuzziness of 1, which means we don't get fuzzy terms. And that is not desirable. We do want fuzzy terms. And so this kind of section is too restrictive. So what we do is we introduce alpha sections. Alpha sections are just sections, except that we relax the requirement that the product of the evaluations is equal to 1. And instead, it's just greater than or equal to alpha. One nice thing about this is this actually gives us a nice little rule where given a term of type A with fuzziness alpha, if beta is less than or equal to alpha, we can actually derive that the term also has a fuzziness beta. And one way to think about this is if you're confident in 80% something, you're at least confident in 50% of it. So this is a nice little rule that we do use time to time because it sort of aligns with composition, because composition here isn't exactly strict. When we compose two morphisms, it doesn't actually need to be exactly the fuzziness of the resulting morphism. It just has to satisfy a less than or equal to relation. All right, so classically, the way we do substitution is using pullbacks. This does not work because in the enriched case, you need to use something more complicated called weighted pullbacks. And this is a special case of weighted limits, which is how we actually calculate the weighted pullback and what the universal property is. So as an example of what a weighted pullback is, we can actually just look at standard categories where we view them as set enriched categories. So normally with a pullback, we get this bijection right here, where we can actually view this, where we sort of view each of these objects as being mapped to by the terminal object. So it picks out a single morphism in there. And so from the perspective of weighted pullbacks, we say this is a 1-1-1 weighted pullback, where 1 is just the terminal object or the singleton set. So to try to work with fuzzy substitution, we need to find the reasonable weights for the substitution structural rule. So specifically, this will be a requirement we impose on the category. We say for this category to work, we need to have these specific pullbacks or these specific weighted pullbacks. We can't work with the terminal object. That's a bit too restrictive. But what we can do is we can work with the singleton set and then a constant evaluation map for some x in the interval. And so this actually works kind of nicely because given a morphism fuzziness alpha and a morphism with fuzziness beta, we can require the weighted pullback where the first weight is has fuzziness alpha, second weight is fuzziness 1, because that's this diagonal map. We don't particularly care about that. And then the third one is fuzziness beta. And using the whole weighted limit definition and everything, we actually get that the universal property is such that this morphism right here has this complicated weight. The important thing to realize is just that the top map delta, the fuzziness of the top map delta is divided by alpha here. And so division here is if alpha is 0, we can just ignore it. And if it's less than delta, then because of the minimization, we just get 1. So this all works out. It's all still within still within the interval. So quickly, we realize something weird happens with this. We can first take a look at this pullback. This is not anything unique. This is just kind of a double projection. And because projections are preserved by pullbacks, this is still a projection. But we do get this map with fuzziness 1. And this sort of corresponds to variable repetition. So given a term of type A, we can produce a term of type A with fuzziness 1. Essentially, we don't lose any information if we already have a term of that type, which is all standard. Like this is what we expected. However, if we then can produce a term of type A with fuzziness alpha, we can look at this specific pullback diagram and get that this morphism right here, the top diagonal one, has a fuzziness of 1, actually, because we divide alpha up here by alpha down here. And so we get this rule over here, which looks really bad. It kind of looks like fuzziness collapses. That given any term of some fuzziness, we then get a term of fuzziness 1 in that same type. This is really not good. However, Paige actually noticed a trick here is that this is not the same object as this. It is the same object when you work with projections. So in the case of the non-fuzzy categories, this is a projection. This is the same object. You can prove an isomorphism, but we can't actually do that here. And so what we can do is we can denote this object as 1.A alpha. And so this actually sort of resolves the crisis. I should have fixed that. Sorry about that. This actually resolves the crisis here because we can read this rule down here, which says given a term in type A with fuzziness alpha, we can derive a term of type A sub alpha of fuzziness 1. We can read this as given a proof of A with confidence alpha, we can prove with confidence 1 that we can prove A with confidence alpha. It's kind of complicated, but it doesn't break everything. So I much prefer that. So this is actually the full rule of fuzzy substitution. Do not read it all, please. This took us an entire afternoon to work out. It was not fun. And we had to do it twice after we found the mistake earlier before we found the resolution. So this is just everything. What we can basically say is that we can do a substitution here and we sort of carry around this alpha because given this context gamma, we have to first create a term A with fuzziness alpha, and then we can create the term in B. So this is a bit complicated here, but it does work with everything else that we need. Before, we also thought there was going to be an issue with composition, because if we derive composition from just the concatenation of from just the composition of morphisms, we'd get a different result than if we did it from the pullbacks. But actually now, because the pullback doesn't actually preserve the object, we don't have this issue. So this all works, and we're all very happy for it. So we can prove now that such a V category satisfies all the structural rules of type theory. We haven't yet done the dependent case. That is a bit more complicated because you can't just look at sections. You have to look at slice categories. But we can have categories to encode the logical system of the agents in our system, which is great. And so the dynamic that we now want to model, so we have Jacob Hansen and Robert Gerst uses cellular sheaf over vector spaces to study opinion dynamics. And then Hans Ries, which is our TA, and Robert Gerst study cellular sheaves into lattices. And so now we want to explore cellular sheaves into these sort of VCATs, where we can sort of view each agent as having their own type system, and then the region they discourse is their own type system. So this is all our feature work. We'd like to work on that. Unfortunately, we only just figured out the resolution to our issue at the end of the week, so we didn't have much time to do any of the dynamic work, but we're going to try to do that in the future. And so next, we're going to try to do enriched categorical interpretations of dependent fuzzy types, and also address definitional equality. We haven't really talked about that, but we could see, if there's any fun things we can do there. We can also replace 0 to 1 by any ordered monoid M, which is nice. I was talking to a colleague about how we could replace it with 0 to infinity, with addition and greater than or equal to as the relation, you can maybe model distance or something like that, which would be interesting. And then we're going to also explore the dynamic side more, hopefully once we get a better understanding of the dependent fuzzy types. All right, here are our references, and thank you.
Hello? Can I ask if you have thought about what you might need to add, or whether this is compatible with a probabilistic logic where you maybe talk about coproducts as disjunctions or something like that?
Yeah, so the initial idea, well, my initial understanding of the fuzzy logic was that it was just a way to do propositional logic. But you run into an issue in that probability isn't categorical, at least not like the naive way you'd think about it. Like, for example, if you know that the probability of B given A, and you know the probability of C given B, you do not know the probability of C given A. And so you need to be a bit more careful. We have been thinking about potentially modeling probability as morphisms from A to A intersection B. So in that case, you sort of maintain the context. You never run into issues where you sort of weaken, because you can't weaken in the probabilistic setting. So we've been sort of thinking about how we could add notions of probability, or maybe choose our category to begin with so that it corresponds to probability. But we don't have anything solid there yet.
Okay, thank you. That seems like a very interesting line of work. Do you have any idea how this relates to, traditionally people study this logics for belief in modal logic? There's quite a long tradition in that. Any idea at all how this is related?
Unfortunately, no. I have not much experience with modal logic besides knowing that it exists, and it's very impressive. Yes. So I don't know exactly how this would relate to it. I think the idea with trying to do fuzzy type theory was building off of fuzzy logic, which is something that exists. But we kind of tried to go at this from starting with like a specific thing and then seeing what we can get from there with like I mentioned before, making as few choices as possible. So I don't know how we would sort of, I guess, compare this to a modal logic case. It'd be very interesting to see if there is like a really nice correspondence in that. That'd be very cool.
Yeah, okay, thanks.
And I believe we can move on to group 3. You're presenting, right?
Yeah, I start and I'm saying.
Okay. So you can choose the one.
I mean, if you want to use it, you can use that. This is the.
Oh yeah, I'm going to use a whiteboard. So could you?
See the whiteboard. Okay, so Ruben is going to present categorical models. And well, I believe that's the title.
Yeah, I think that it changed over
during
the week.
The group works on time zone difficulties for first season. We have 2 speakers, one online and one in person, and Ruben is the in-person.
Yeah, thank you. So is the microphone, is that okay? Okay, great. Yeah, so the title we started with was Timed and Probabilistic Processes. But we didn't really do much with the timed part. So then it was just probabilistic processes, which is not saying that much, but so what we mainly looked at or studied was really graphs or networks of stochastic maps. So the picture then usually looked
something like this. This. Or oh, great, thank you. Yeah, maybe it's difficult to read. Okay, I think this is better. So yeah, then the pictures we often drew on the whiteboards look something like this. So where we interpret these arrows as stochastic maps, or we think of these as variables, and this A depends on B in some way. So that was the vague general idea. So there's of course like several frameworks to actually work with this and think about this. And the things we mainly looked at as were Bayesian networks, also causal networks, and that's what Tim is going to talk about. Also probabilistic automata. And well, we really started focusing on this one first, but then we sort of changed to this one. So yeah, this is the, I guess, the sort of general framework or world where we wanted to work. And then the things we were in particular interested in is composition. So yeah, that's why I drew two networks, because we want to compose them in some way. So we wanted to express that. Cycles. So with that, I mean situations like this, where there's arrows in both directions. So yeah, D depends on B and B depends on D. So we also wanted to talk about situations like that. And the third thing we were interested in, we called interventions, or are called interventions. And with that, we meant things like when, for example, this G depends on E and it depends on A, but maybe we're only interested on the dependence of A. So we sort of want to delete this dependence in some way. So we also wanted to work with that. Yeah, these frameworks do exist, but I think none of them really capture all of these. So we wanted to sort of look at a more categorical framework that does allow to think about all these things. So we wanted to write these things as string diagrams. So the networks correspond to a morphism in some monoidal category. So for that, we needed a nice monoidal category, I guess. Where our string diagrams would live. So because these arrows are all, well, sort of stochastic maps, the category really should be the Kleisli category of some probability or monads T. So yeah, what then do we mean by nice, or what are the properties we were looking, or we've been looking at? So yeah, of course it needs to be monoidal, because it should be a monoidal category. And a sufficient condition for that is for T to be commutative, which for most of the probability monads we've been looking at, this is fine. What else? Yeah, we want objects to be comonoids. So we want them to have a comonoid structure. So we want a co-multiplication, which usually looked something like this. So we send an element to the probability measure that's concentrated on this pair, which also seemed to work for all the probability monads we were interested in. We also wanted a co-unit, which is, yeah, sending every element to this direct delta. So that's concentrated on just this one element of the one element set. So yeah, this all seemed fine. But then we also sometimes needed a multiplication and a unit. And that's where things sometimes started to get more difficult or annoying. So we wanted a multiplication, which we thought should look something like this. Wait, sorry, it's the other way around, right? So when they're equal, we send it to the direct delta. That's putting all measure or all probability mass on that element, and to the zero measure otherwise. But yeah, the zero measure, of course, is not a probability measure. So then we needed to work with sub-probabilities or not general measures. If we want to look at more continuous spaces, then for this to be measurable, we also want our diagonal to be measurable, which is also not always the case. So for example, for Polish spaces, that would work, but not for a general measurable space anymore. But okay, this is sort of still okay. But then I guess the thing that seemed to be the most annoying was this unit. So that sense, oh yeah, it points at the counting measure, or that's what it really should do. So for finite sets and even countable sets, that all seems to work well. But then for more infinite sets, this counting measure is just not nice anymore, and it didn't do what we wanted it to do. So yeah, this property seemed to be not always true for the monads we were interested in. Yeah, and then finally, we also wanted this to be, this Gleisli category to be posed enriched, where then the meaning of, is that me? Yeah, I guess so. To mean F is less random than G. And we wanted to use this to talk about these interventions, because you sort of make things more random. So yeah, we spent a lot of time trying to find a balance between the things we wanted to express and the properties we had, and which we didn't need to express some things and which we definitely did need, and things like that. But I think, yeah, Pim is now going to make that more concrete and give a more detailed explanation of these causal networks.
Thanks, Ruben. Can I maybe share my screen? If that's possible at all.
You should be able to share your screen.
Yeah, great, thanks. Can you see that all right?
Yes.
All right, so thanks everyone. My name is Pim de Haan. I'm very keen to present the result of our research week. I'll tell a bit more about kind of how concretely we map between causal models and the categories that Ruben described. So a Bayesian causal network is a very standard way of non-categorically describing causes and effects. And it starts with defining a directed acyclic graph, where we later will generalize to also allow for cyclicity, with a vertex for each vertex a measurable space. And for now, let's assume that they're finite. An example is we have here 3 variables. We maybe have some genes that affect our tendency.
Seems like we lost you for a second. Are you still there? Hello?
I don't know if you can hear me, but my computer is, I think, having heat issues.
Yeah, now we
Okay.
Okay, are you there? Yes.
Can
you share?
I can sort of hear you. Is my screen still shared? I don't know.
Not really. Can you try to stop sharing? Okay, let me see. Okay, great. Okay. Can you hear? No, not anymore. Can you try to stop and share again?
I stopped sharing my screen.
Yes.
That's right. I think I'm having heat issues with my laptop. Can I try again? Can you hear me all right?
Yeah, we can hear you.
Okay, great.
Yeah, sorry.
Maybe I can share your slides.
Yes, let me try to do that again.
Okay, great. Now we see them.
Okay, great. All right, sorry for that. So yes, the idea of course a model like this is to say that we have some gene affecting whether we become smokers, and both our smoking behavior and our genes affecting whether we may get cancer. And in the Bayesian causal network, there's also for each vertex a probability distribution that's conditional on the parents. So from all the parents, we get a distribution over the variable. So for this graph, we get the distribution over G, a conditional distribution of whether we're smoking, giving our genes, and a conditional distribution of whether we get cancer given our smoking behavior and our genes. Now, our goal is to find a categorical model of these kinds of networks that, as Ruben mentioned, feature us.
I'm sorry, I think we don't hear you properly. So I have a proposal. I will share your slides. So maybe we can hear you better that way. Hello, can you hear us? Yeah, can you say something?
Yeah, test 1, 2, 3.
Okay, yeah. But now I can hear you okay.
Okay, great. Yes, we're also trying to model composition, so how to glue models together and how to model cycles. So the first step is, given our graph, we construct a syntax category. How it works is we are given this DAG, and we construct a syntax category that is symmetric monoidal, where the objects are where we have one object for each vertex in the graph, and also allow for tensor products between these objects. And then we have, which is the nice category that Ruben mentioned, which Mario called a discrete Markov restriction category, which includes the comonoid and also the multiplication operation. Then for each vertex, we create a morphism from the parents to each vertex. So in this case, we have the following additional morphisms: a morphism from the unit of the category to G, a morphism from G to S, and a morphism from G and S to C. And then we have one particular special endomorphism from G times S times C to it.
I think we're not hearing you again. I don't know why. Sorry.
I think, can we just run the slides for Pim and Pim can turn off the video?
Yeah. So I think it's probably connected. So Charlie, if you stop sharing your slides, I will share the slides for you. And maybe turn off your video or something. Where was okay, right? Can you turn off your video? Because I don't know why they maybe they try to speak now. Oh, damn it. No, we don't hear you very well.
Perhaps if you show locally and stop the sharing.
Yeah, that's what we did.
Oh, okay.
I'm sharing from here.
That's what I'm saying. Yeah.
Maybe okay. Let's do like that. We're gonna move on to the next group, and maybe we'll go back to you again later. Is that okay with you? Okay.
So Zoom has the option to call it.
Okay, sorry about this technical issue.
Sorry, can you hear me now?
Oh, now we can hear you. Yeah.
Okay, I went to an iPad.
Oh. Okay. Let's try. Let me share screen.
Yes, please.
Okay.
Okay.
Only once you move.
Test 1, 2, 3. You can hear me okay?
Yes.
Okay, great. So we have this syntax category which encodes our DAG, and we have this endomorphism that we construct as follows. And then on the next slide, we see that we also give semantics to the syntax. We have a functor that we construct from this syntax category to this Kleisli distribution, the Kleisli category of subdistribution, which Ruben introduced, which has as objects measurable spaces and as morphisms, Markov kernels, and that give measures, and they are not necessarily probability measures, but they can also have norm less or more than 1. So the functor f maps each object to an accompanying measurable space and maps the morphisms to the conditional probability distributions from the definition of the Bayesian causal network. And as Ruben said, it maps the comparator to an indicator that gives us probability 1 if the output and the 2 inputs are all equal and 0 otherwise.
Next slide, please. So now we would like to also express how we can get a joint distribution from our causal model. And we do that by adding a unit to our category, as Ruben mentioned also. The equivalent in the semantics would be that we not only allow for sub-distributions, but we allow for distributions that can have norm also more than one. And in the case of finite sets, we then just get the category of matrices. So where the morphisms are matrices with non-negative elements. The unit in that category will be just a constant one factor. Then if we take our causal model, as we see on the top left, and in the top left of the figure, of that figure, then if we pre-compose that with the unit, and then we apply the axioms of our category, then what we get is a morphism from the unit to G times S times C. And this is equivalent to a joint probability distribution over these variables. And this formalism coincides with what Brendan Fong did in his master thesis of his model of causal, categorical causal models. But in the next slide, we see that we can also elegantly model interventions because we put a 2-cell in our category by saying that the comparator is less than throwing the left input away and keeping only the right input. So if you were to apply that to our causal model, and then we apply it to the middle comparator, we see that rather than comparing the input S with the output of G, we just take the input of S. And then after some rewriting, we see that the morphism of G disappeared from our causal network. If we were then to look again at such a solution, taking as by pre-composing it with the unit and post-composing it with the discard for all variables but the ones that we like to take as input and output, and then we apply our axioms, then we get a conditional distribution over the probability to get cancer given smoking behavior. And this corresponds to an intervention. This corresponds to if we were to take a random person, intervene and force this person to become or stop being a smoker, and then measure the distribution over getting the disease, then this conditional probability distribution will be the outcome of this hypothetical experiment. So here we see that we can model such interventions in our formalism by looking at 2 cells between morphisms. Next slide, please. We can also compose these causal models in an elegant way, because if we were to do our intervention and then compose our model with a different model that just says that the smoking behavior is given by the genes, but maybe by in a different way with a conditional probability distribution G prime, and we compose that with the intervened model, what we get is a joint distribution over G, S, and C that corresponds to a soft intervention, meaning that we have changed the model by not cutting the dependence of S on G, but by changing the value of the conditional probability distribution. So these and other kinds of compositions allow us to flexibly glue together different subcausal models into larger ones. Next slide, please. And we also allow for cycles, which I'll briefly touch on here. So we could imagine a causal model in which we have supply and demand, and these are mediated through a price of a certain product. And then we have some noise variables that say epsilon S and epsilon D, that say something about the sensitivity of the supply and demand to price. But the price also changes if the supply and demand changes. So this is a cyclic causal model. And this is quite rarely modeled in the causal literature, but in our construction, we allow for that. So if we apply our procedure of translating DAG or the graph into a string diagram, then we get a string diagrams in the middle, which has a cyclic dependency, and then we define a solution of this to be any morphism any morphism from epsilon S and epsilon D to the supply, price, and demand. We say that this is a distribution if this solution function does not contain a comparator or monoidal unit, so that we can kind of read it off in a forward direction. And and the solution function on the right-hand side constitutes a joint probability distribution. And you would see that if the maps F, G, and H are deterministic, then the solution functions will be a uniform distribution over the fixed points of the functions F, G, and H combined. So we also allow for cycles. And on the next slide, we have some open questions. We really like to implement these discrete restriction Markov categories via probabilistic programming, so that we can directly implement these models. But we have some open questions like how to take conditionals and maybe how to make normalization part of this formalism. Then we like to formalize a notion of solutions generalized to infinite spaces, further explore the bicategorical structures that we can put on stochastic maps, and connect this closer to the do calculus and causal inference, such as in the reference causal inference via string diagram surgery. Thank you very much for listening. And sorry for the technical issues.
Are there any questions? Yes.
Hello. What's the true cells for this do operation in the model? Is it a purely syntactic entity, or is it like pointwise comparison of distributions?
Thanks. That's so syntactically. So it's syntactically we defined it just as is, but we also map this to subdistribution, and we're not quite sure which kind of poset, like a local poset enrichment we can put on subdistributions. But one of the ones that we can do is to say that one stochastic map is more than the other if for all inputs on finite sets, if for all inputs and for all outputs, the probability is larger. And this would be consistent with the syntactic two-cell.
Cool, thank you.
Any other questions? I think we're ready for time, so let's thank you. Last group, and they're going to talk about Venn diagrams. It's three of us. Okay, so just today presenting Phoebe, Nathan, and Ralph. If you want more mic.
Yeah, can I just hold it?
Yeah.
I guess I'll do it over there. Hi, everyone.
Sorry, if the camera's like that, we should pause this.
Okay. Pause.
Maybe you can forward it.
Okay.
This one goes to the internet.
Okay. All right. Hi, everyone. We're group 4. Broadly, our topic was to look at algebraic structures of logic and relations, and okay. And we're going to talk about what we did during the research week last week, which is what are called tape diagrams. We'll give an introduction to it today.
I'll see what I can do. All right. So give an introduction to tape diagrams, which we worked on last week. My name is Nathan. This is Phoebe and Ralph, and Rowan's online watching. We'd like to thank Filippo, who was the mentor, Chad, if he's around somewhere, and the organizers too, because this has been a fun event. Oh no. If there's just stay close. Okay, so if there's a lesson to take away for tape diagrams today, it's that they kind of serve as string diagrams for string diagrams. So when I show you this example, string diagrams kind of live on the surface of these tapes, and then there's further equations for how these tapes behave. I'll give just an introduction to it, and then we'll give just some examples of how this works, and this will result in a little program in tape diagrams that we'll talk about. So what's the motivation? Well, we have these two monoidal products in REL, the Cartesian product and the disjoint union. And so we're going to look at the model, I guess, or generalize the Cartesian product by using string diagrams for Cartesian bicategories of relations. And I think some of you will already know a lot of these, but we have just commutativity and associativity and unitality. And then we have these inequations along the bottom that are kind of like primitive inference rules. And what we're going to do for this, I guess for the plus here, we're going to have a category with finite biproducts. And a lot of these rules are going to be overlap. So we're going to have these tapes now, this red wire, or this red ribbon, I guess. They obey commutativity and associativity and these unit laws. It's hard to see the units, but the unit of the tape here is kind of rounded compared to square. And one difference is that we have, instead of the inequations on the bottom along the tapes, so I guess the wires just keep track of objects. So what we're trying to actually look at here is the structure of the tape, right? But for the tape, the direction of the inequations changes. So we reverse the direction of the inequalities. And then because of naturality, this no longer laxly holds, but it actually holds up to equality. And so these gives us the equations for the version of the tape. And the way to think about these is that these string diagrams for Cartesian bicategories of relations live on the surface. And then the other product lives in the space between these ribbons, or these tapes. So here's a simple example. So in Cartesian bicategories of relations, the intersection is represented by the graph, I guess on the left. Think of this as if you're moving along the wire, you go, it's kind of like conjunction, right? You now go to R and S, right? But in the case of the tape on the right for join, you now kind of have a choice. So this is like disjunction, right? So when you move along the tape and it splits, you can now choose whether you go to one relation or the other. So the way that, as is known, I guess, the Cartesian bicategories of relations corresponds to what's called regular logic. And so you can think of these finite biproducts as corresponding to having this underlying logic of coherent logic. So we're going to turn towards programming now. We're going to add a bit to this.
So we wanted to do programming with the tapes. So I'm going to have to explain a few things we need for programming, and then Phoebe will actually write the program and prove something about the program. So one thing we need with programs first is the if statements and the while statement. In particular, what they have in common is the conditional. So when you do an if and when you do while, you have if Boolean is true or stuff like that, and while also has a while Boolean is true. So you want to first do some kind of predicate, and with relations we can do predicates. So a predicate is like a relation on that square. If you can draw it either on the middle or on the right. You can draw it as a box with only input wires or only output wires. This is how you think of predicates. However, when we're going to use them inside programs, we want them to let the information pass through. So they're going to have inputs, and then they're going to check if the inputs satisfy the property, and then live them out. And so diagrammatically, we can write it as the one on the left, and it's equal to either one on these guys. The complement of P is also really nice. So we're going to use this because if you want to do if something is true, then something, then if this same thing is false, then you do the other thing. And these are equations that are satisfied by the complement. We're going to use multiple properties of coreflexivity that they have that are nice to use, but I don't want to show them to you. We're just going to use them and explain it and tell them that we're using them. So how do we do the if? For example, the if here is gonna. So I'm going to do if P then C1 else C2. And what happens is that if you read this diagram as these two inputs coming in, so X and Y, then you're going to go inside here. You have a choice. Either you go here, but if you go here, you have to satisfy P. Otherwise, you don't go out. And if you go here, you have to not satisfy P. Otherwise, you don't go out. So this is effectively either you go here and satisfy P and do C1, or you go here and satisfy not P and you go execute C2. So this is really how you do an if statement using tape diagrams. Last ingredient that we want. So I'm not going to show you. So this is for the while loop. So we want to do iteration, which is something that we use a lot in programming languages. And so this is going to be iteration. So again, I'm going to read it to you, but we're going to do, if R is a relation, it's just a relation, we're going to do R star, which is the cleanest star or the reflexive transitive closure of R. And how you read this is if you have X coming in inside here, then here, when you go inside here, you cannot go here up top because you're always going in this way. But if you go here, you can either choose to go up or to go down. If you go down, that's it, you stay X. But if you go up top, you do R of X. And then you loop around and you come back and you have the choice to do this again. And you're either you go back again and you're just R of X, or you go on top and you do R squared of X. And this is basically R or R squared or a third and so on, and that's R star. Now, how do you do this loop? This is not something that we have in the syntax yet. This is called a trace. And so this is the trace of the plus operation, the trace of the tapes, not of the strings inside the tapes. And we have some things that the trace must satisfy, some standard equations, but we want to point out one equation that we really need. And this is, we found this during the week in a paper of Sillinger, which said, who told us that this is called uniform trace. It's something that's akin to induction, and we find that it is, but not completely. And so we used it, but we're not so completely satisfied with it, but it's still cool. So basically, how to do this, how to use this, if you want to prove that these two things are equal with a trace inside, you can remove the top. So we call this the tops off equation because we're in Glasgow. And then you have an H here, which is going to take the role of an invariant. And you just have to prove this, right? So if you want to prove something with a trace, you can remove the trace, add an invariant that will be on either side. And if you prove this, you have proven this. So here, we're going to do this. So Phoebe is going to prove something about this program. It's going to be the Euclid's algorithm. So I don't know if you know it, but this is the program is inside the middle. So it's the while loop here. We're going to use it. We don't need to read it right now. But then we have two conditions on top, and this is for whole logic stuff. So basically, this is a precondition. This is saying at the start of the program, you should satisfy X equals A and Y equals B. And at the end of the program, you should satisfy X equals Y equals the MCD of AB or GCD of AB. MCD and GCD are the same thing. And we want to prove that this is true. So we want to prove that this code actually takes two inputs that satisfy X equals Y and Y equals B and gives out two outputs that satisfy X equals Y equals MCD AB. The key property that we're going to use is this key property of the GCD is that GCD of VW, when V equals W, it's equal to V. When V is bigger than W, it's equal to the GCD of V minus W. And when it's when V is smaller than VW, it's equal to GCD of V, W minus V. And you see that we have to do some kind of iteration because when you do GCD, you also have to apply GCD again. These equations are going to be used as string diagrams. So I just present them to you, but you don't need to actually read them. If you want to read them, that's cool. And now we get the program. So the program, you can read it again. So the input is X and Y, and here you go here. Either you go down here, but if you go down here, this is a coreflexive or a predicate that tells you that X must be equal to Y because they must join them together. So if you go down here, that means that X equals to Y. So you're out of the loop and you're good. But if you go up top, you assume that X is not equal to Y. Then you have two choices. Either you compare, so one of them is bigger than the other, and you do the minus here, and you do the you're going to loop again. So you're basically doing the GCD again, or you go on the bottom, and it's the other way around, but you flip and then you do the GCD again. So that is our program. Yes, this is the program. So this is only this part. The last thing I need to do is to give you the P and the Q. So I also defined the bigger or equal, but it's not okay. It's not so much if you don't know what it is. But the P here, we said it's when you start the program, you should have X equals A and Y equals B. So we're going to write them as trig diagrams like this. So X is equal to A and Y is equal to B. And the Q one was that X equals Y equals GCD of AB. And this is also X equals Y equals GCD of AB. And you go down. With this, all of these ingredients, 3B will be able to prove that this is actually the good algorithm for the GCD.
Okay, this is kind of delicate. Okay. Thanks to Nathan and Ralph for doing all the hard work. And now we can see this stuff in action. Okay. Cool. Oh, wait, how do I move this? Okay. All right, so we had this program, which Ralph just walked through, which calculates, hopefully, the GCD of our two inputs. And now we'd like to actually say for sure whether or not that's the case. All right, so how are we going to do this? We talked some about propositions. So we have this proposition at the beginning, which is P, which just asserts that X is equal to A and B is equal to Y. This is how we're going to kind of keep track of the values that we started with. And then at the end, hopefully we can show that those two inputs evaluate when the program is done to X, which is equal to the actual GCD or MCD of A and B. So when we compose with our propositions, we're kind of asking or asserting, okay, if we start with this, what do we end up with? Also, this is how we would encode that in string diagrams. Okay, so this is what we want to show on the bottom part. And how are we going to do that? This is where the uniformity of trace comes in. So Ralph discussed if we can show that kind of when you take the tops off of the thing, given this special H, which comes in on this side for this guy and this guy over here. So this would be, the rest of this would be F and G and that equation we saw earlier. Then we can conclude that this bottom inequality also holds. So working backwards, given this, there's a kind of natural choice for this guy with the top off to be equal to F and this guy with the top off to be equal to G. And now all we have to do is choose H so that this works out nicely. All right, so the clever choice for this is this I. And why it's clever is because it's going to be invariant. Unfortunately, there's no like general way of seeing that this is invariant in diagrammatic form, but that's what makes it clever. So we're going to substitute this in for H in our equations that we had before. And just to briefly give some intuition for what this I is. So this I is then saying, given A and B, X and Y coming in on those wires, we want the MCD of A and B to be equal to the MCD of X and Y. So when we compare them here, this copy asserts that this then becomes the same thing. Sorry, decopy. Okay, so this is our new formulation. You can see we've got I here where the H's were, and then we're also substituting I in for where P was before. This is just how we're going to do the proof. And the reason we can do this is because P is less than or equal to I. So we know that if this holds, then certainly the same thing would hold for P. And just to give some intuition for why P would be less than or equal to I, P is again the proposition that just X is equal to A and B is equal to Y, whereas I is asking the MCD of A and B to be equal to the MCD of X and Y. So it's kind of asking for less. Okay, so now for the fun stuff. So we start off with this guy. And the first thing we're going to use, also just for simplicity's sake, we didn't write in all of the I's everywhere. You can kind of trust me that this works. So we're going to use the naturality of decopy here to push I into the middle. And then we're going to use the same trick to push it back out to the two rightmost branches. All right. And then the next thing we'd like to do is kind of flip I and this evaluation, this proposition which evaluates whether or not those two inputs are equal to each other. And we can do this because they're both propositions, which means in these diagrams, the terms are co-reflexive. So they play nicely with each other and we can indeed just swap them around. All right, and then we've got them swapped, and then we use the naturality again, so we can push I into these two separate branches. And then we want to switch I and C1 and C2. So we're moving towards this picture where we want I on the outside here on the top rightmost corner, trying to push it through all the way. All right, so now we want to flip I with these two C1 and C2. And we can do this because of the invariance property, which is why we chose this clever I. So if you do this out in full string diagram notation, this is just the choice of I, which works best, so we can swap these two. All right, and then we finally push them through I here using the naturality of tcopy again to the outside. And then the last bit here is trying to think through, given I on this bottom branch, remember we want to end up with Q on the bottom right-hand side. So just to give some intuition for how this works out, again, you can just do this kind of using the machinery of the string diagrams. But what I is asking is that for the MCD of A and B, we want that to be equal to the MCD of X and Y. We know our while loop has finished here. So X and Y are, without the while loop, we still know that X and Y at this point are not going to be equal. Will be equal. So we have X and Y equal. We want to evaluate whether or not Q is asking whether or not the GCD of X and of A and B is equal to X. And so given all of these in combination with our GCD equation, which says that when X and Y are equal, the GCD is equal to X, we have exactly what we need to push this through and get Q on the outside. And that's what we wanted. All right. And now we're going to wrap up by talking about some future directions.
So we proved stuff using iteration, but we were not really successful in proving really lots of stuff. We just proved one thing that was nice, and that's it. That's what the example we gave you. We tried lots of stuff. We weren't really successful. And so one thing I would like to do is, because iteration is about, or induction is about this really strong property of SR, which is that it's the least fixed point of this function. And we haven't tried yet, but maybe we could try to prove this using the uniformity of the trace that star actually satisfies this property. And that's something I would like to prove.
I also suggested that the underlying logic for these tape diagrams was coherent logic. And so there's either a very close connection to that to distributive allegories. That's one thing I'd like to look at. And then extend it to other logics. So I put division allegories if you have residuation here. I'm not sure if you can actually get that out of the syntax, but it's a natural, nice next step. So.
Okay, and then lastly, we played around with choosing terms and equations to comprise our signature for our theories, such that we ended up with the natural numbers being our only model up to isomorphism. And the reason we did that is it seemed like a simple model to try first when you want things like induction. This wasn't super fruitful, so we might try different signatures and equations such that they might be more interesting. All right, I think that's it.
Thank you very much. One quick question.
Hi, really nice talk. This idea that you have like this if and else, and also the iteration reminds me a lot of PDL, positional dynamic logic. Have you looked at this also? Maybe to get some, to steal some stuff also from its experimentation or something?
No, I haven't.
I don't think so.
Something to look at. Because, I think it's
yeah, sounds good. Thanks.
We can thank the last speaker.
Thanks, everyone. Thanks for those really interesting talks. I'll just introduce myself quickly. I'm Brendan Fong, and together with Daniel Scala at the University of New Haven, we're the steering committee for the academic score. think the talks this year have been really interesting, and I'm looking forward to seeing the blog posts and the papers emerge in the coming months. Just a few words of thanks to close the session. So firstly, the adjoint school is run off the volunteer effort of all of the teaching staff, and we're really grateful that year after year, senior members of the community and postdocs and graduate students get involved to help out and build this, run this important event and build this community that we hold dear. So this year, I just like to acknowledge and thank the mentors and the TAs. So from Spencer Breiner and Joe Mola and Owen Lynch from the first group, Paige North and Hans Rees from the second group, and Nicoletta Sabatini and Mario Román, and then Filippo Bonchi and Chet Nestor. So thank you all for your effort. And then the lion's share of the work each year is done by the organizing team, and they do so much, starting from a whole year's worth of work to design the curriculum, to recruit mentors, to advertise and help select participants, to attracting funding. And this year we're very grateful to be funded by the NSF as well as the sponsors, portion of the sponsorship for this year's ACT conference. And then of course to run the 4-month online teaching program and coordinate all the activities of the in-person school, which has been made even more sort of challenging than usual due to COVID this year. So I'd like to acknowledge the 4 organizers. First, Elena and Angeline, and then the senior organizers for this year, Sophie, who unfortunately can't be here, and then David there. The organizers so 2-year terms, so we're very lucky to have Elena and Angelina returning next year to organize again. But of course, we're always looking for new involvement at all levels, from the mentors to the TAs to new organizers. And so if you're interested in being involved and contributing to this program, please do get in touch with any of us. And thank you.
Yes, I just have a short announcement about the dinner again. So just to mention now, I think it's 5:40. So we're scheduled to start the conference dinner at 7 o'clock sharp in a place that's just a few minutes away from here. I've posted away the location on Zulip chat on the ACP, but you can also ask us, and I assume some people might be here to chat. So the name is the Daba. Yeah. Yes, I don't know if I have DHABBA, I believe. Yes, we can share the map and show it. Yes, well, yes, let's do both. Great. That's really all. Is there anything else I'm forgetting about this? Yes.
We have plenty of COVID tests left outside. I would personally feel more confident if many of us tested before we all go and sit in one big room together. So if you haven't tested today, I would encourage you to use the test outside, and then we can all feel safer. I think that's it. There's plenty of masks if you want a new mask.
Okay. Are these art masks?
Yes, thank you.
Oh, wow. Are they all black?
They have some white.
That's okay.
Yes, I know this. The equation.
I read the it's like,
Oh, no, it's one. It's almost like one, so A will come out, which is a fuzz. Like it's like a fuzzy. Exactly. I should have made this point. But then you did. Well, then you got it. Yes. The non-existence and then reappearance of fuzzy types. The thing is, they showed up. Yeah. Yes. That's fine. Yeah, that's fine. I think so. Yes, and that's fine. Because I was thinking about something else before, where like I had script types and then manage that was like me like saying, oh, I sometimes I can add it to other methods like comments.
Maybe another couple of tests.
Yeah. That's fine. Yes, that's fine.
Yeah, I mean, it was very last.
So one of the cool things is actually I think
So that in the rate, like on the drawing board. Like white isotopic loops, which are nonsensical.
Yeah. Oh, in the beginning, I saw.
Right? You have a scalar. X. Then isotopic to X. That implies that X plus 1 is equal to 1 this is not anything to do with it. So it's the you see what I mean though? Yeah.
I mean, that's a subject.
Yeah.
I'm very lucky.
I also.
Oh, okay.
Oh, I'm alive. Also.
The general thing is like it's on top of that.
Yeah.
which is how it's supposed to, the diagram is supposed to just go up and copy the house. So we don't want them to spend well, yeah. But they do a great job. Yeah. Unfortunately, with the text. Yeah. Right. So I was just saying that we should go. So, and that's what we were just talking about. So okay. So all I want to say is that last year, that's why I'm saying this. Yeah, yeah. So last year, by the time we got you all on board, right? And that was good. Yeah. And then the Memphis slowed down, and then by December. So I think this year and last year. How many years before yeah, move on to within the past few years it's pretty good. That way it still feels good, but it's which is going to just well, although I will say, like, if this is why I don't have them. Obviously, I think there'll be something else for them to do. Actually, no, nothing before. Everyone's like, yeah. We want to do something. Like, it's Joe's also not going. Try and find all the people who are doing something. Okay. Yeah. Okay. I don't know how to do that. I don't know. I don't know how to organize. I don't know how to do it. I'm the pilot. Okay.